predictable. As I said, I want to trace those intended behavior, so we can read those source code and say what can happen and what can happen. So at Tencent, we are using the latency as the root metrics I will talk about later. And the effective children matrix has some characteristic being clear cut, and it can have a preset threshold. It can be composed of one or multiple metrics and something like that. I believe I'm running out of time, so I will talk about it later if someone posted any questions about it. So from my perspective, latency is everything. It directly affects the user space, and it directly have a side effect of user experience. So these metrics can be found in the kernel source. They are predictable. I rephrase it. They are only part of metrics that we should care about, like the SKB allocation in the TCP layer or some RTO or something like that. So they are enumerated. And what we've done in production and Tencent in these 2 years are, the first one is the performance, that is about the latency, and the second one is the TCP reset. As some of you may find, I'm pushing so hard in the ATF to add some payload at the end of the RCD packet, so that we can easily understand why we are receiving this RCD packet. And the third one is the ping delay, because it can effectively know the status of the RTT in between two servers. And the practice. Let me revisit a little bit why we are building this platform. We want to run this platform continuously, and I want it suitable for other kernels, and I want zero code intrusion, bring less overhead, and address the real world issues. And this is how those figures are about some children metric that I just mentioned. They are record different latency from the kernel side. It only brings less than 1 or 2%, 100% overhead, so it's totally acceptable. This is the BPF timestamping. This platform has used a kernel module like the BPF timestamping. I proposed this feature in the first half of the year. The motivation of this BPF timestamping is that I don't want to any application trying to modify their own kernel. Prior to that, there is a feature named the socket timestamping that can tell users or administrators what area can cause the latency problem. But it requires many modifications in the user space. I don't want to that, so that is why I proposed the BPF timestamping. We have a very similar one that is kernel module at Tencent. Oh, I already gave a talk in Zagreb about this. And there are 3 steps we should care about. The first one is hook approach. There's some hook approaches, but they have different numbers. I extracted some numbers from this link. That is the recent work from my friend, and we can see the F entry is super good. But for the kernel module, what I can use is the F trace, but I think it's okay. And the second portion, second part is the process. How can we deal with those information, or what kind of information that we want to extract from the socket and the SKB? And the be cautious because we cannot do many calculations in the kernel module because it will definitely affect the whole system performance. And the third one is how can we transfer the data from the kernel side to the user space? We use the relay FS, which is not actually a file system, which is a tunnel that can put those information from the kernel side into a shared memory, so the user space can directly read this kind of information out and calculate it in the user space, so that will minimize the effect of the kernel module. Oh, I nearly forgot to say that BPF time stepping has the one good feature is it has absolute isolation. Because supposing there are 10,000 flows running in parallel in production, and you only want to chase one of them, but it is evident that nearly rest of them suffer from the impact. Okay, I will. The last slide is, do we have any common consensus on how to on those functions that to be chased in the kernel? Because Brenner ever proposed that we can have a stable function, and so that we can chase them. Yeah. Without that, some developers will argue that some functions that they chase will be inlined or will get removed in the latest kernel. So, can we have a standard spec about that? So, thank you. Thanks for listening to this.
Okay, real quick. So I like the idea of root latency. Computers are getting more complicated. I want to be able to solve anything in 5 days. Any metric which tells me this is a direct measure of pain, that's what I think you're doing,
yes, is
easy for the customers to interpret. TCP already has some, like the client-bound, server-bound stuff that I use, but adding more of these I think helps us all solve issues in 5 days. Rather than here's metrics, you figure out what to do with it. I haven't heard the term root latency metrics before, but I like it, because I think that helps us accomplish that goal. So any place we can add things that are directly proportional to pain and actionable is going to help customers. Your other concern about trace points and stability, of course, I love trace points, and I would argue that I don't mind if they do sometimes break, like once every 10 years. Aren't we able to trace inline functions now with BTF in the kernel so that things can change, but you can still find where those instruction offsets are? I'd have to look into it. But I think that's something we might have fixed. But adding more trace points, I'll certainly use them.
It would be super great if we can add as many as trace points in the kernel, but some maintainers argues about that because it hurts a little bit in the hot parts. So in the hot parts in the networking area, we carefully examine the whole code over and over again, so that we can avoid some unnecessary things like that stuff. So from my perspective, it'd be super cool if we can. But so that's the reason why I want to call for the common sense of it, because after we have a common sense of what kind of functions we are going to chase, then we have the strong evidence that we can insert this trace point in the certain functions. Yeah. Okay, thank you. I will be around the conference. Please feel free to ask any questions. Thank you.
Boa sorte, velho.
Obrigado, viu? Bruna, como é que eu baixo a página? Como é que eu troco a página? Tipo, page down. Frente, trás?
É.
Ah, eu tô apertando pra baixo. Deu certo? Trocou? Ok. Hey. Let me try here.
Hello, it's fine, the audio? I guess, right? So first of all, thank you folks for the attention, for having me here, right? Thanks Breno and Usama for organizing the MC. We'll be talking about the proactive and crash time data collection on Steam Deck. I'm Guilherme. First of all, a bit from myself. I'm a mathematician, and after that, I decided computers are more experimental and funny, so moved areas. I started in IBM, Linux Technology Center, work with hardware, software interactions, PowerPC, etc., low-level stuff, and then moved to Canonical to work with sustain engineering, which is more customer-focused, right? And eventually, I started at Igalia in 21, which is a quite special place. It's a cooperative based on free software. It's the focus is free software and upstream. It's a very nice place with ethics and quality of life as focus, right? And then I started working with P-Store, KDump, hardware enablement, and it was my first contact with gaming world on Linux. Starting to work and involve the Steam Deck. So this is the summary. We'll talk about the Steam Deck, the kind of the data collection we want to do, and the ways we do the data collection, like P-Store, KDump, the kernel infrastructure for that, right? And some system events, some metrics we collect, and how we aggregate that data and provide to the user a way of seeing that, like statistics, metrics. So first of all, a bit of the Steam Deck game console. It's a handheld. Most of you probably know that, but it's a handheld based on Linux. It's an AMD APU, 8 cores, 16 gigs. And the interesting piece here is the distro, which is an Arch Linux, it's called SteamOS 3. It's an Arch Linux-based distro, immutable one with A/B partitioning, and have a sophisticated stack for games. It's called Proton. Basically, you have Windows games running there, and you need translate APIs for Windows, DirectX, Vulkan, etc. And Igalia is working in many fronts, not only the data collection, but also graphics, Visual Space graphics, GPUs. We work in FACSEMU, which is a translator ARM to x86 to ARM binary translator, and also in the Steam Frame, which is the new VR hardware from Valve. Right? And the ideals of data collection is that we have two different classes of data, basically. The breakages and the regular information. The people that are working in fixing stuff, they would like to see when the bug happens, collect data, right? And the developers working optimizations, they will be more focused on metrics, not crashes, for example. But we also have two realms of data collection. We can collect system information, kernel, firmware, etc., and also user land, the more upper level things. The focus here is infrastructure, the system part of data collection, kernel specifically. But game issues could be also unveiled based on that, because if a game is crashing the kernel all the time, you can check the message, for example, and based on that, you can observe what's going on in games, right? And we have information metrics, the split locks, out of memory. We can collect out of memory data. That's very important for checking how the device is going to optimize things, right? And then the visualization stuff. We have a tool for that called SLS, SteamOS Log Submitter, which accumulates and sends data to Valve server. We have like Steam, it's a systemd service with hooks. It's modular, right? And it collects the crashes, metrics. We'll talk more about that later. And then finally, we have the visualization aggregation part, the telemetry. So in case of Valve is Sentry. We have a Sentry instance that gets the data from SLS and exposes to the users, like in a graphical form. So it's important to mention that all of that is opt-in. So if the user wish, they can enable that, and it helps a lot, right? But if it's not the default, the user must want to collect the data. So let's talk first about the bugs and then metrics. The most severe type of bug that we all know here is the kernel crash, right? Many reasons for that. Could be hardware issue, no pointers. SteamOS is configured to crash on OOPS and soft and hard lookups. The tooling that is used for interact with the kernel infrastructure is called KDump. That's the tool we work at. It's Arch Linux package. And we have the SKL, which is SteamOS kdumps layer. This is a layer, a thin glue, right, on top of the kdumps that is used to set some tunings. For example, the type of crashes, etc. We have the pstore and kdump as the kernel infrastructures, right, on that are used. So let's dive a bit in the technologies. Mainly,
I'm just curious about the reason. Like, could you explain the reason for crashing on soft lockups?
soft lookups.
Reason behind it?
Yeah, because they will impair the experience of the user, right? So soft lookup it's kind of a severe failure, not so much as the hard lookups, but still it's one of them that we want to collect. Different from hung tasks, for example. Hung tasks are more, the user can exist while the user play a game, for example, but the soft lookup is impossible, right? To work with. So we decided to crash on that. Okay, so the kdump, about kdump, most of you already know that, likely. It's a KZEC basic procedure. So the kernel that is broken jumps to a fresh kernel that can collect the data, memory mapping from the first kernel. So there's a huge amount of information, Vim core, for example. Breno, can you get my water, please? Yes, thank you. I forgot. So yeah, let me just. Great. So the pros of kdump. First of all, it's a huge amount of information, right? We have a VM core collected, a full memory image. So this is the main method of debugging production kernels, etc. But we have a bunch of cons. So the first one is the pre-reserved memory amount we need. Lately in the recent kernels is a bit big, is 200 megabytes. Go.
We at Meta are doing something very interesting. There's a patch set on 6.18 from SUSE where you can leverage CMA memory as crash memory. So we are kind of decreasing the crash kernel, or we are planning to, because we are leveraging CMA. So the kdump environment could be used by user space. You don't need that at like crash time. It's kind of like not completely lost memory.
Yeah. I would mention that later here in the thing. Yes, no, it's very fine. This is good, but you still need some memory reserved, right, to put the kernel in initrd. So not maybe 200, but at least half of it or a bit less, and then you can leverage the memory later. It's one of the improvements lately, right? But that's not the only con. We have many like the size of Vim core. But I know that there's alternatives. For example, you can read stuff and not collect the full Vim core. You can filter that, right, on the collection time. But you have privacy issues. Imagine for the gaming users, you collect the full memory. The Vim core is a full memory image. So basically, it's something here. And risks, because since my background is hardware and PowerPC, plenty of risks in the KZEC procedure. Like PCI devices might misbehave. We can have OMs if not properly configure the memory amount, etc. Right? So there is a lightweight way, which is pstore. Pstore comes from persistent storage. So this works by you have front ends and back ends, right? The front ends decides it's about what type of the data you want to collect, like traces or the message, or even user data is possible to collect. And then you have the back end, which is the component that saves, in fact, the logs into some persistent storage, right? Could be RAM, could be UEFI data or ACPI, and one could also argue that RAM is not persistent, is volatile. But most firmwares, they don't retrain the memory or mess with that. So it is the case of the Steam Deck. So we can collect in RAM, and in a soft reboot, the data is there, right? The pros of pstore is that it's quite fast and hopefully a transparent process. It does not require a memory reservation. Of course, if you are using the RAM as a backend, you need some memory there. But it's like you collected the message, so 5 megabytes, I don't know, 10 megabytes. is way less than 200 megabytes, right? And we have multiple front ends, like Chrome OS, it collects also the console, for example. And no KZEC support is required. That's important, especially in the embedded world. P-Store is used a lot in embedded because it's easier than the KZEC. A Qualcomm firmware, for example, that has security features that usually might not allow the KZEC. But we also have cons. We have less information collected, basically only logs. By the way, there's a presentation later. Eugene, he has proposals to change that, maybe to collect more than only logs. And we have risks as well, like the crash logs are collected after the panic notifiers. That's a risk. We will talk a bit more about that because that's one of the topics we can improve. And the firmware might corrupt the RAM. It's not the case on Steam Deck, but in regular machines, that could happen. So, okay, the SteamOS approach. Why not both? Because of some x86 alignment stuff, we observed that Steam Deck was kind of wasting around 16 megabytes of memory. So it's there for free. So we can use P-Store. And since the hardware is controlled by Valve, the firmware as well, the firmware does not mess with that memory. It's the same case of Chromebooks, basically. But also, the user might want to collect the vMcore eventually. So we have both approaches. Default is P-Store, but we also support KDump. The tool that we worked for that is KDumpst, which is, as I said, Arch Linux package. Now is on the Arch Linux AUR repo, but in the beginning was only SteamOS, and it's tricky that to default to P-Store in Arch Linux. We do that, but usually the tool fails and fallbacks to KDump because regular users would need to manually set up the P-Store RAM area, right? And then we have the SKL, which is the layer, the thing layer. It moves logs and changes some defaults. For example, the soft lookup and hard lookup, we decide to panic on oops, only that. And we show extra information on panic time, basically memory, task state, timers, CPU backtraces. We use the panic print and crash KZEC post notifiers as a mean to collect more data in the deck, right? So interesting bits now, what we can improve. First of all, the panic notifiers, they could be a problem that's for a long time in the kernel not solved yet. Notifiers are callbacks that you have some places in the kernel that they are called and run in a sequence. So any driver or architecture could program a callback to run that. And panic notifiers, they execute in panic time. But the thing is, you have plenty of complex stuff done in panic time, and the machine is not in a great state. So running that is very tricky. And we proposed a bunch of fixes, like there was some notifiers doing mutexes during the panic time, which is not great, so we changed that. But the main refactor that was proposed a while ago was to split that in lists of the most simple ones and necessary ones to run versus the ones that are more dangerous or not so necessary. And it was a big discussion, a really big discussion. And we had a presentation KR, kernel recipes about that, some ideas. But then I moved to different projects and stopped a bit to work on that. But it's still a pending issue in the panic time. Remoops, we have also things to improve there. First of all, it was tricky to reserve the memory, but Steve improved that with a parameter, reserve man. But still, we don't know if it works. Maybe the user configures that and the firmware breaks the memory, like corrupt the memory. So I'm considering implementing a test in Remoops. So it's easy to test if it's reliable as a backend. We have problems also in the related to graphics on panic time, because it's a very difficult it's very difficult to show graphics when the machine is panicked. It was improved by Jocelyn recently with the ARM panic handler, but still is difficult to do in AMD GPU or Intel, the sophisticated cards, right? And there was an idea for the deck specifically to have a UEFI notifier to notify the UEFI, the firmware, that a panic happens, and then the firmware could change the boot's logo. But that was not really well accepted by ARD, this notifier, but it's a simple idea, right? So back to the bugs, we have also collected in the deck the GPU resets, The GPU can provide data, but it's a very complex topic because it's not super easy to map the problems that happened in the user land part of the graphics, like Mesa, etc., with what happened in the GPU. So it's an ongoing work for like André and Siqueira at Igalia and a lot of MD folks. It's limited scope, but also collected. And then we have other metrics, not the crash part, but metrics for optimization. So two interesting ones from Valve, they requested that all out of memory and split locks. So there is no kernel event sender for OMs. And for split locks, it was first supported only in Intel, but now in AMD, right? It's a buzz lock condition if you have atomic access on split cache lines, right? So I'll be a bit faster here because we have not much time. We decided to leverage the tracing infrastructure on the deck to collect that. OM has an event that's interesting. And split lock, we are doing function-based. We just have an ftrace instance there, checking for the function, split lock detect, something like that. And we collect that using the trace pipe blocked read. There's a bunch of events. Okay. There's a bunch of events, so if they feel to add, it's very simple, the tool is there. Also, there is another part of interesting data collection, which is the peripherals, right? So we have the SteamOS system report tool that is used to collect data like LPC, USB, all the network, etc., the displays that are connected to the deck. And all of that is collected by this other tool. It's not my work, but it's a very interesting thing as well. And we have core dumps and mini dumps also collected. Mini dumps are a form of core dump used by Steam. It's a bit different format. And GPU traces, finally. There's yet another tool collecting GPU traces, Mesa and GameScope, which is the compositor. And so we have plenty of tools collecting a bunch of data. And all of that is different formats. We might have core dumps and textual stuff. So the aggregation is done by the log submitter, right, called SLS. This is work from Vicky at Valve. It's a Python tool that has hooks. So each of the tools, like KDumps, has its own connection with the hook. So it provides data to move logs, and so the SteamOS log submit can collect them, summarize, and there's an API. So SLS communicates with the Valve servers, with Sentry, and then it is provided to the ones debugging as a visual thing, statistics, alarms, etc. So that's it, basically. Thanks for the attention. If you have questions, topics.
Thanks for a good presentation. And
Thank you.
It looks like you have invented so many great tools, and seems like some of those are very optimized for SteamOS. And I want to use that, but I'm not using SteamOS. So I'm wondering how much dependencies the tools are having on SteamOS, and whether you have planned to make it more general and less dependent to SteamOS.
Thank you. It's a very interesting question. Basically, KDumps is the main tool here, right? It's ready for Arch Linux. It's in the AUR. It's the same tool in SteamOS and Arch Linux. The difference is the capabilities of the SteamOS as we control the firmware, so it's easy to set pstore. If you want to use in your system, KDumps you can use right now, but it probably will fall back to KZEC. You'll need to set the pstore automatically. It's difficult to do that for generic systems. It requires manual intervention. But for KDump, it works. That said, there's some missing pieces in KDumps. I have issues open there that I need to work. One of them is that we don't support, for example, other backends, because UEFI would be easier to set than a run backend. So I have a patch kind of ready. It's not so great form. I need to polish that and put it on the tool. Another one is that we only support grub if we go automatically setting the KDump. You can also set by yourself, but the tool does that automatically, as other KDump tooling like Debian 1, etc. but we only support grub right now. So I plan to add support for systemd. But basically, pstore and kdump stuff, they are kernel technologies. It's present in Arch Linux and kdumps as well. So you can use as is. The only piece here that is exclusive, kernel-wise talking, is the SKL, which is the glue. But that basically changes some tunings that you can also change yourself, right? Now, to the other part, collecting GPU traces and the SteamOS report stuff for peripherals, that is specific for SteamOS. And then it's basically to collect data from that device. But regarding the crash collection, is basically the same in Arch Linux and SteamOS.
Thank you.
Thank you. Okay, thank you, folks.
Yeah, it's just right and left.
I think it's
Up and down.
yeah, it's left and right. I know I had a mistake too.
Okay.
Yeah, luckily I uploaded my talk to the thing because I couldn't use it anywhere. Here.
All right. Good morning, everyone. So I'm really excited to talk about BPF trace today. And it's amazing because it was already mentioned in a couple presentations. This is really good. So people have context already. So obligatory intro slide. I'm Aiden, this is Jordan. We both work at Meta. Meta uses BPF extensively, obviously, and also uses BPF trace quite a lot. Although, I recognize most people are interested in kernel topics. BPF trace does have applicability beyond the kernel. It's used by a lot of service owners, a lot of automated profiling tools, a lot of exciting things, and we're really excited about where we're going with it. I forgot to mention, we're both current maintainers of BPF trace. Jordan's been working on it for a couple of years. I'm more recent. I started working on it when I joined Meta. So I'm going to speed run a 1-minute introduction to BPF trace and runtime coupled together. It is used for all kinds of tracing, whatever your heart's desire. The easiest way to understand what you can do with it is just to look at a simple example. So this is looking at page faults that occur. It's sampling at a rate of 1, which means for every one event, this probe will fire. And it's storing in an associative array or map, basically by thread name, the count of the number of events that it sees. So if you were to run this script, you would basically just see a big output that shows you the number of page faults that occur per thread name. But it can do more than simple things. There's lots of advanced cases that BPF trace can cover. So general system observability, how do you interact with a kernel system calls, very useful thing to look at. I personally turn to strace all the time to debug everything. BPF trace is like strace on super steroids. You can do anything synchronously in the path. So this is an example where you're measuring the latency of every single system call. And the thing that I'll point out is BPF trace has a bunch of built-in utilities like histograms and things for measuring or aggregating statistics. So this is printing the histogram per syscall name in that kind of map, showing you the latency, sampling whatever time period, whatever process you're running it with. You can do deeper dives with it. So this is an example of a performance deep dive. I'm looking at lock contention. You can do fun tricks. The built-in here that I'll point out is you're doing aggregation based on 5 frames of the kernel stack. So you have an associative array based on that, and you can sort of see where that contention is occurring. And that's all, fairly easy, straightforward, just a line or two. All those identifiers are built in. You can also do more sophisticated things than, just tracking a count of things. You can traverse structures. You can look at different types in the kernel. You can walk things. All of that is automatically inferred based on BTF and other things. So you can do. I didn't want to fit in too much into the left side here because I wanted it to be readable, but you can actually look at structures and sort of do more sophisticated debugging. And of course, for us, it also helps with your BPF addiction. So you can even trace, BPF programs if you want to. So this is tracing the entry into all of these BPF probes firing and counting based on probe name. And the right side here, I think, is me running it for like a second on my workstation. So you can see there truly is a BPF addiction there. So the point of all that is it can actually do a lot. It's very flexible. There's many different probe types. You can traverse all these structures. You have a lot of different features that I didn't talk about or mention at all, right? There's automatic loops, there's variables, there's different aggregations. Even AI, I think this was mentioned earlier as well, right? So AI is capable of generating BPF trace scripts. It doesn't do a great job, to be clear. It generates scripts that are kind of clunky and don't use any sort of more modern features, but it's impressive that it can do it, in my opinion.
So this brings us to the core of this presentation. Like, okay, so why don't we, if it's so amazing, why don't we have, big scripts and community tools and all these things built around BPF trace? If you look at GitHub, I sort of tried to find all the BPF trace script examples that I could. They're all very, very small in general. There's very few. I think the largest example that I saw was an implementation of Tetris in BPF trace, which is pretty funny, but it's also a little bit sad that's the largest script that's out there. In fact, I only found about 10,000 unique lines of BPF trace scripts on GitHub, so it's a fairly small sample. And I think this is a criticism completely out of love for the tool and what it can do, so don't misinterpret it in any way. But I think it's really easy to hit a wall when you're using BPF trace, in the sense that you'll find you need to reach for some feature, or you want some K-Funk, or hey, there's this type of map now, can I use this type of map? And you just can't do that. And we want to support all these things, we want to do them, but unfortunately we have to turn a lot of people away and say like, no, not right now, you can't do it, you have to do this clunky way. Oh, I want to do a multi-arch script, or I want to like tweak this one little line, like just copy and have a second script that you name differently for that other arch. Like that's kind of a clunky answer that we don't like to have to give. And I think the reason for this, again, out of love, is that BPF trace has been around for quite a while and has a long history. It was created before a lot of the technologies in the BPF ecosystem were really standardized and that have made that ecosystem a lot better. So, BTF and CoRE, all these things came after BPF trace was initially built up and had a lot of features and functionality. It's also had different maintainers that were active at different times. It's had a lot of features that, were kind of half finished or 80% finished, and then move on to the next feature and do things. I don't think this is uncommon. It's not a bad thing. It's just standard big open source project, how it works. But one of the other big things that's missing is there's no escape hatches in BPF trace. So if you hit one of those walls, it's like, what can I do? Well, you just have to add it to BPF. You have to add the feature that you need to BPF trace itself. And this is not an easy journey either. So just to give an example, start with that initial script we had where we're using com, right, the thread name. Now we want to use cgroup. We want to aggregate by cgroup for these functions. Okay, how do I go and build this? Can't be that hard, right? Pretty straightforward. So first challenge there is that everything is kind of a language feature. It's a very, very flat implementation. And so all of these tokens like com is actually like a lexer token that you read this in and say like, oh, this is a built-in, this is a call. All those things are encoded directly in the lexer. So immediately when you're adding something, okay, now I have parser tests and I'm like doing all this extra lifting. The second thing is, God help you if you need new types or you want to provide some new type to the user. Those are sort of a laundry list of all the types that are hard-coded. And so you're adding something to that list. You're adding support for all those types to a bunch of different passes. You're adding rules around implicit casts from all those types. It's pretty complicated. It's a pretty big lift. And then you get to cogen if you're adding a new call, for example. And this is all writing a lot of C++ to generate LLVM IR. And this is like a huge barrier to someone that just wants to call a K-Funk, right? Like, doesn't seem like it should be that complicated. And of course, there's the rest of the OWL, right? There's all these other tie-ins with the rest of BPF trace itself. Like, for example, I'm adding a new K-Funk. I need to ensure that K-Funk works in all these different attach points and all the checking, and all the user error messages surface pretty correctly. But it's a pretty high lift for adding fairly simple features. So when I first joined the project, one of the questions that I had unrelated is, hey, this has been around for 7-8 years at this point. Like, why is it not 1.0, right? Why is it still 0.22? And there's no answer for that. And so I think what we've tried to do is assemble a list of some of these things we want to fix to make the tool and language more maintainable, not strip things out, but make it more composable, work better together, provide those escape hatches, something that we can support for a long period of time without having to go back and bolt on every single feature separately, and call that 1.0. So this journey is underway. We've been adding a lot of these features to sort of make it more composable, and Jordan's going to talk about a few examples of these.
So yeah, just to sort of iterate that context, like in all these examples, I want to reiterate what Aiden said, that we are trying to reduce the internal code of BPF trace. So again, he pointed out that he found about like 10,000 lines of code on GitHub. Well, BPF trace itself is like 30,000 lines, right? At least, right? So that's like, quite a big difference between the amount of, scripts that exist and the size of the code base. So we want to like invert that a little bit. Much more scripts, much longer lines, smaller BPF trace code. And we want to enable more features to the users. So we want to like provide escape hatches and ways for them to unblock themselves so they don't hit a wall. So that's what I'm going to be talking about, the features that do this. So it was a long time coming. We didn't really have a way in BPF trace to like factor out common code. We're still playing around this idea of like callable functions, but we first went with something really simple, and that is macros. So simple text replacement. You can define a macro in BPF trace, and then this just like spits out, you know, what the actual text is in the macro, right? So add one, you pass an expression add one, and then it adds one to it. And of course, this predictably prints two, right? Very exciting. Well, we already have like much more complicated macros in trunk of BPF trace that do all sorts of stuff. So we have like, you know, variables in those macros, we have asserts, and then we have like, you know, function calls. And I'm going to talk a little bit more about how we use these macros to develop more of a standard library for BPF trace. So macros come in 3 different flavors. So you can pass like sort of like it's like a raw identifier as the first argument to add one. And then you also have the ability to pass like variables and maps. And the reason that we have this distinction in BPF trace is because we want these macros to be hygienic. This is like a concept we sort of stole from Rust, who I'm sure stole from somebody else. But the idea being that you can't mutate variables that you pass into macros unless you explicitly pass them in, right? This is sort of to prevent foot guns. In order to reference X, you know, which may be defined above, you have to like sort of pass it in. Same thing true for BPF trace maps. And you can see that like they're being mutated there. And another big part of this is like the ability to import things into a BPF trace script. So that Tetris script that Aiden mentioned is all like one giant blob of BPF trace code in one file, right? Well, there's no reason why that needs to be the case. So we added the ability to import other BPF trace scripts. So here is that like, you know, trivial add one macro. You know, I put it in a library and you're importing the library and we're calling it. Simple, simple. But the really exciting part of imports is the ability to import C files. So this was a much larger lift, and this is something we're still working on, but it's the escape hatch that Aiden was talking about, right? Like you no longer need to wait for someone or yourself to like write the BPF trace code, commit it, you know, have it reviewed, wait for the release every like, couple times a year, have your distro like update it, right? Like here you can just create a bpf.c file with a function. Maybe it's a call to a kfunc, like anything else. Like you can just call this and have it return some value and have it like interop with the BPF trace variables, and it just works. Like there are still some rough edges here, but this is essentially like the power that we're unlocking with like being able to import BPF-C files. And we already have extensive usage of this in trunk, right? So here is something that somebody actually added into our like standard library. It's the bpf.c program that, you know, is used to get the thread name from a particular task, and you have to pass in the PID, right? So here we have like some extern definitions to see whether or not those functions or kfuncs are actually available in the kernel. And if they are, it calls it and calls the correct kfuncs to, you know, perform this operation. So this is already working and in trunk, and it's pretty cool. One thing I sort of like, I'm glossing over a little bit is that because BPF trace writes basically all of its BPF code in LLVM IR. Like we need LLVM. We ship LLVM with BPF trace, which makes BPF trace a very large binary. And we're working on like steps to reduce it. But like we sort of leaned in a bit with this, right? So here we have this bpf.c code and we're actually compiling it on the fly and linking it in when we like create our BPF trace LLVM IR code. So as a user, like, why should you care about this? So I sort of talked about this a little bit already, but like this is the escape hatch, right? Like you don't have to wait for BPF trace for cool new features. It also makes it a lot easier to contribute to BPF trace. Like you don't, like when I first started on BPF trace, I remember looking at the LLVM IR code and just being sort of sad and terrified because I didn't really know assembly that well. I still don't. But, you know, new contributors can now like add new things to the standard library and just have like an easier time contributing to BPF trace. And so you get all the powers and the heartache of C with this feature, right? And, you know, just faster development of BPF core features. the other key set of features to enable this is compile time features. So to reduce not only like bespoke LLVM IR code in BPF trace, but bespoke C++ code where you have like big switch statements, for things where if it's the right probe type or the right architecture or all sorts of stuff, we want to pull that out of the core and like move it into the standard library and be able to write these things in BPF trace, right? So we're starting to use a lot of like, these tried and true compiler methods in order to do this. So we have like constant folding, branch pruning, and type introspection, and I'm going to go over those. Here is a macro for the signal function in BPF trace. And the newest built-in that I'll call out is this comp time built-in. And this is something we stole from Zig. It's very similar to const verb, but basically the expression on the right has to be evaluated at compile time. And if it is, it enables a bunch of other things. So for example, if this is true at compile time, if the probe type, which is usually kprobe or begin probe or whatever equals kprobe, then this fail function gets called. And fail is also a compile time feature. Basically, if we figure out that fail is reachable at runtime, it's like a compilation fail. It's like a static assert kind of. And this enables us to, again, pull things out of like, the core BPF trace code base and into like these BPF trace macros. So yeah, this is sort of like a very simplified version of how comp time works. And if you've ever used const expert, like it's very, it makes perfect sense. And this is sort of like how like branch pruning relates, right? So in the script where you're calling signal intervals, the probe type, it's obviously, going to be true because it doesn't equal kprobe, then fail gets called. And this works the opposite way, right? Like if interval, or if the probe type is kprobe, then this whole fail branch gets pruned and you're good. Like this whole thing gets removed at runtime. And type introspection. This was the other key part to moving things into the standard library. We want to be able to introspect types, at compile time. So we have things like isString and isInteger. And they are, basically macros under the hood, which call this other built-in called type info. And this gives you, like a tuple of like their like underlying BPF trace types under the hood, so you can like match against them at compile time and do things like checks. Running out of time here, but like Aiden called out, you can't do an architecture. You have to like have two scripts. If they're going to run on different architectures, well, not anymore, right? You can write a comp time check if an architecture equals something, take this branch. If it's not, take this other one else. So now you can write a script that works on both architectures perfectly well, done. And this will be true for a lot of other things in BPF trace that you want to be able to do conditional checking on. Yeah, and all this is going toward a standard library for BPF trace. This is something we haven't had before, really. We sort of had just like hodgepodge of like functions and built-ins. Well, we're now like creating much better documentation for both users and developers. We're trying to make composable primitives that are much more powerful and just, again, lean less on core code and less LLVM IR. Just quick shout outs. We launched a new BPF trace website this year. So please go to it. It has, tutorials, labs, like a bunch of blog posts about what we were just talking about. And actually we recently added a BPF trace playground, which is really neat. So you can like test your BPF trace scripts. This is still a work in progress, but it's getting there and it's already pretty cool. And here's some links. We have a new Discord chat. So come talk about BPF trace. And that's about it.
Hey, Jordan. Hey, Aiden. Cool work. So you mean I learned LLVM IR for nothing? I could have been doing this. Anyway, so I see it direct uses for things like I want to do IPv6 stringification. I just write it once and it's in the library and then I can refer to it if it's not already a helper or an action. That's pretty cool. My question is, one of the bigger challenges with maintaining, these days I try to write very short BPF trace scripts with 1 kprobe only just because of maintenance. Because in my distant past, I wrote these very long dtrace scripts that were super brittle as the kernel changed. If this can plug into, say, synthetic events, that Stephen's been working on, I could imagine those libraries make it easier to do synthetic events in BPF trace. And then the library can say, if it's this kernel version, here's the, you're basically exposing one synthetic trace point, but you can go and play with the implementation in the BPF trace library file. And then if the kernel breaks, we just fix it in user space because we can just update the library file. I think that would be super cool. I mean, it is going to be ugly because we'll have these library files that say, if Linux 6.3 do this, if Linux 6.18, but at least we're putting that into a central library file and not scattering it around BPF trace scripts. So I think that would be a super cool use case. Don't know if you've thought of it.
Oh.
Yeah, I mean, I think that's the idea of centralizing is a big part of this, right? Like you want to have those checks, but you want them to all be in that one implementation of the function that's like, okay, we'll handle this, we'll fix this break. I think there are features. So BPF trace, one of the principles is you try to make it simple and understandable for users so you can have those short little scripts. And I think that's really valuable. And so having this model of the standard library be the place where we can put a lot of that complexity and handle that, I think that's really what we're shooting for here. The kernel version is this whole extra level of complexity where we have this comp time feature, right? But like we're trying to figure out the way to materialize support for the kernel version isn't strictly comp time, right? Like the Arch is comp time, but you could imagine ahead of time compiling a script, loading on different things. So some of these will take different shapes and different forms, but we want that to all be in one place where like you have to make those decisions. I think that's really what we're going for.
And you could also prototype trace. If you have an idea for a trace point and say, I think this trace point will be very useful, as part of convincing the maintainer to accept it, you first do a BPF trace script, you do a synthetic event, you get a use study, a use case in production, you get other people to try it out, and then you've got all this collateral. We've been using it for years, is this user space defined BPF trace synthetic event. Now it's time to integrate it into the kernel. So there'll be a good staging ground.
Nice. And like, the standard library, we haven't really talked about this, but right, like it doesn't have to be tied to the core code. Like if like something happens in the kernel upstream and you don't want to wait for a BPF trace release, like you could just sort of patch your version of the standard library. It could be like a separate thing that like gets built and deployed separately and it just sort of gets updated,
Yes. In fact, you can have libraries shipped with runtime. You could have a Java BPF trace library that says, oh, here's a stack walker for Java, put it in Ruby and Python. Yeah. And so all those communities can say, well, we like BPF trace, but it doesn't understand our runtime. So here's our macros. That'd be super cool.
Yeah. Thank you.
Only have a 6-minute break. So.
Hey, GP. This one, right?
Okay. Oh, it's all good for me here?
Yeah, you need to use this one.
This, right? I don't need it. Okay.
You need this one. So you go right and left here.
That works. That works. No problem.
Is that okay?
Yeah.
Just left and right.
All right. Cool. Thanks. Hi, everyone. I guess we're running a little bit late, so I'll just start right away. My name is JP Copeland. I'm working on the kernel team at Meta. And so, yeah, I wanted to talk about C group stat efficiency, especially when it comes to reading memory C group and possibly other C group types as well. So, yeah, we collect C group stats across our fleet continuously. One of the popular tools we have is below. If you haven't used it, it's actually really nice. We run it on our servers. It collects data, stores it. So remotely, you can view historical stats, jump back in time. So if there's a problem, you can look at what happened possibly before that problem occurred. And so with that said, collecting all these stats adds up over a large enough fleet. So the scalability aspect is kind of critical. The header here, the program doesn't use cat, but I just wrote cat there just because I want everybody to kind of see what it's like to read that file. Historically, there was some delays, a pretty bad delay. We looked into, why it took so long just to get CPU stat. It was kind of known in the community for a while, but we'll focus on that first. There was some work done earlier this year that helped that situation. There's also some patches pending upstream to help the situation where we're fetching memory C group stats. And also, I'd like to also talk about something in progress that I think could be a nice paradigm shift in the way that we're reading stats that could be valuable to us as a company and also people in the community. So, so the cost of memory C group in terms of reading CPU stats, if you look at the top flame graph there, you'll see the three separate stacks above the system call are the memory stat show on the right. In the middle, we have CPU stat and also IO stat on the left. The most interesting thing is that on the top of the first two stacks, you'll see memory C group CSS R stat flush. So it meant that anytime we read CPU stat or IO stat, we're flushing memory C group. And then on the right side is memory stat of its own. So fortunately, we landed a series upstream earlier this year that created a separation between the way that C group stats were structured on a per CPU type of basis. And so now when we flush stats, we only flush our own subsystems. So on the bottom flame graph here, we can see CPU stat show no longer has memory C group, and IO stat no longer has memory C group. And this was actually a really big win for us. If you're collecting stats over your fleet, it could be a win for you too. It saved us a lot, something on the order of like over $1 million. And let's see. So yeah, and that landed in 616. So while doing that work, we noticed on the memory side, a significant amount of time was spent in the actual formatting of the of the stats. So let's see if I can get a pointer here. If we look, no, maybe not. If we look basically at the small stack, the small red and yellow stack where it just is like an M with the ellipses, that's the flush. That's it. The rest of it is all string formatting, and the double under S is sequence put S. Zoomed in here. That's this area here that we were interested in. So we said to ourselves, like, look at all we're spending formatting these stats. We're barely spending any time doing the flush. So we wanted to try and tackle that problem. And so, right. So, and this is the work that's pending upstream right now. So we said to ourselves, can we go from this, right? Because when you dump those stat files, they're strings in user space, right? So then you have to use the user space program to kind of parse the key value pairs there. So you're going from kernel numeric to string, and then in user space you're going back from string to numeric. Then you can work with your information. So, but what we were wondering about is, can we do something like this, where we just eliminate that middle part completely, right? Because we don't like it. It's expensive, and we could probably do better than that. And so it makes you wonder, like, if you're going to map memory from the kernel to user space, there has to be some sort of binary agreement between the two. That was another thing we wanted to avoid, and so we said, can we use BPF? And it looks like we can. So the work that's pending upstream are some new K-funcs. The type of BPF program that we're using here, the C group iterator, this already exists, but the K-funcs are new, and they're pointed out here. So up top we have, well, the topmost arrow is just the C group iterator program, but we have the acquire and release K-funcs, which are the things that can allow us to get a handle on the memory C group and then control the reference counting as we're doing that. And we also have a means of flushing the stats. So anytime we want to read, we invoke this C group iterator program, and then we flush the stats. Now we have the latest stuff ready to go. And then here, this group of functions here are the stat fetching functions that we can do now in the BPF program. So there's two different types, right? There's one for events and the other one's for the page state stats. And the nice thing about it here is that it can be very specific about what stats we want to get. Whereas previously when we're dumping all of the stats, you have to go through them all and do some filtering. But we effectively map, sorry, we effectively map the memory from kernel to user space through the use of that data section variable up top. So in the user space program, we now have access to those fields. So you can see in the bullet second from the bottom through like the skeleton pointer, you can access these fields there. So using that variable, we now have that mapped memory bridge that we were looking for. And so the benchmarks that we had on this look very good. If I remember correctly, I think it reduced kernel time by something on the order of like 90%. And so, but it does take tailoring, right? So your program where it was previously reading those stats and parsing the strings, now you just have to set up a BPF program within your program to get these stats, any stats you want really. And this is just a small subset that the program below was using. Oh, and just want to mention these K-funcs have become part of the I worked with Roman on his these patches are now part of Roman's BPF series since he needed to make use of them as well. Okay, so now the third topic. Thinking about just reading stats in general. So like we come across these situations where some like users at our company report some latency contention actually while reading CPU stats specifically. So the main thing to point out is that whenever you are, if you have different programs that are reading in parallel, you can only go as far as to they all contend on the same spin lock for flushing within a subsystem, right? So you can see in the graph there where the delays would kick in, right? So one's already a flush in progress, and a new reader comes in at the root. The wait will begin, and you'll see in the call stack, spin lock slow path. And then there's right. So there's three different programs here as an example. Building on this, it's rare that we have programs just doing like a one-off read. If it's a one-off read, usually that's a user logged in doing it. But the programs that we have want to fetch stats periodically. So for each of those programs, it's likely that these stats are fetched continuously. So we end up with a program that does something like this. So over time, it will just read one C group and then proceed to the next and onward. And then usually what happens is at the point where you finish reading all your C groups of interest, then you might just like sleep or wait till the next cycle because you typically want to sample them at a fixed rate. And so it led us to think about this possible paradigm shift. And this is something that I wanted to present to everybody here and kind of get feedback on is the core concept is what if, so we have programs that collect stats periodically. We could say that for all of those programs, there is a minimum frequency that we want to have these stats refreshed at. So whatever program you have that's sampling stats at the highest frequency, what if we let the kernel just flush at that frequency? And then readers could then come in each time that flush is finished and then just do the work of the format, getting information to user space one way or another, right? So that top bar there now is the kernel doing the flush, and the readers come in sequentially just like before because they want to go one at a time, but they are no longer, the readers are no longer paying the cost of the flush. That's the main thing to point out. And so how would we actually, how does that actually work? What does it look like? Pretty much, the work in progress that I have right now, and it seems to work pretty well. The paradigm changes from reading to sleep and then reading over and over to instead letting the kernel wake us. So when we read and we finish, we're just going to pull and wait for IO to become available again, and then the kernel will wake us up, and we'll read our next stat just like that. So we still achieve the same that same action of fetching our stats, going to sleep and waking back up. It's just we invert the situation where the user mode program schedules itself to letting the kernel wake us up. So having the flush done asynchronously in the background, and then we synchronize the readers with a sequence number and wait notify. So the thought was, the concept is 2 new C group files. The first one is something called, that I was calling, and I'm just using CPUs as an example here. I think it could apply to other C groups as well. But the first one I have here is CPU stat stream interval. All right, so writing to this file, you set the number of milliseconds you want to put between the time between the kernel flushing stats, right? And so we put that action onto a work queue. We schedule that at that interval continuously, so the flush occurs periodically. Each time the flush occurs, the kernel increments that writer sequence number, and then proceeds to notify any waiters if there are any waiters there. And the other file, right, and that's just a control file for setting the frequency. The other file that we have, or that I'd like to add, is just like the CPU stat stream, right? And I call it stream because we're kind of like streaming the telemetry now, right? We're just waiting for the kernel to give us the next value while we're just continuously polling and reading. And so in here, so when that file is open, the main thing is the reader sequence number is set to 0, and then we know we're going to wait until the writer sequence becomes greater than the actual reader sequence number. Once that happens, we'll be woken up, and then we can dump the stats and get them just as we did before. So the action is all the same. It's just we shift the work of the flushing to a background to async work on a work queue, and then we still are able to wake up and sleep. Wake up once that data becomes ready. And then in terms of like, could this help anybody here? I've seen a couple of patches from the community not too long ago. One that stands out the most is, well, there's 2 actually that stand out the most. One was about a desire to add a capability for manually flushing memory stats. So somebody wanted to add a feature, an extra memory control file, so that if you write to it, you just flush the memory stat on demand. And then there was another one I saw where somebody wanted to solve that situation where there was contention among parallel CPU stat readers. In that situation, somebody had proposed to change CPU stats to atomic, but I think there was some issues with that, and it never moved forward. So this is something that we think could help us. And so, yeah, I wanted to just present this part as to what we're thinking about next, and ask for feedback. If anybody has any thoughts on that, I'd be happy to talk about it.
Hi, JP. So for this part where we kind of expect reads to be happening at a fixed interval, maybe this is a super naive idea, but would just simply rate limiting the flushes be sufficient for this use case?
Well, yeah, I mean, the thing with the rate limiting is that, right, you're not necessarily getting the latest stats, right? Because in our case, we want to collect stats faster than we're doing right now. And so this is part of what can help that work, right? So if we do rate limit, yes, we will effectively reduce the cost of flushes across the board. But the thing is, we're not going to be getting the latest stats like we want to. So yeah.
Hey, just in terms of ABI, I wonder, have you considered like an alternative approach with fcontrol? Like that's one of the ways we've done some of these in some other parts of the kernel, as opposed to, because I can kind of see, okay, we got CPU stat stream, then eventually you want to do something for IO, and you also have like one for IO, and then it kind of doesn't necessarily end very well. So I wonder whether maybe the opener can do something with fcontrol, like in terms of ABI.
Yeah, like this was just an example. Like I did CPU just because we wanted to respond to reports of CPU contention recently in our fleet, but I don't see this as a specific design for CPU stats. Like I think the general design could be taken out and also applied for both IO and memory. But the files themselves would be independent, but the infrastructure.
I guess I'm trying to work out why the file should be independent. Like for some other parts, we put some of the impetus to do it like on the reader, right? So the reader declares, I want this style of reading through like fcontrol or something like that. That's one of the ways we've done it in other places. The main reason I worry about that is one of the things we were pretty insistent about, like on some of the C group previous API discussions, was even just like having a lot of files is kind of a problem. Like it can become kind of problematic. And you know, we had the rstat problems with io.stat. We had a lot of stuff. I can imagine it kind of going everywhere, right? So if the problem is like we don't want to like vastly expand the file space in every single C group, which has its own problems as well, not only in terms of like semantics, but also in terms of perf. Like I think it probably makes sense to think about whether there are ways that the reader can indicate like, I want this method of reading, as opposed to, hey, here's a different file you should read maybe.
Yeah, I get your point. I should also clarify I didn't note it here in the slide, but it's worth calling out. I should have made a note there. The file the stat stream interval, I envision that only for the root C group, and so because I wouldn't want there to be. I wanted it to be simple, so I don't see that as something where every C group you can set some sort of interval. Really, what I'm doing here with that stream interval on the root C group, I set that, and when I flush, I actually flushed from the root, so I flushed the whole tree. And so the second file, though, would be unique for every C group. So if I want to read a specific C group, I would get the stats just for that C group. But yeah, I wouldn't give control to every C group to flush at a frequency, just the root C group, because the programs that we have, I think one flush, at least in our cases, the telemetry case, right? One flush is enough, and then one flush is good enough, then you're going to read X number of C groups that you're interested in. Yeah.
Hi, JP. Yeah, back to the rate limiting idea. So your readers are already in BPF. And it looks like you're calling flush right now, but MemCG already has or had a rate limited rstats flushing. So what if you just specify in your BPF reader like a latency value that will cause the flush to be skipped until you're past that time value?
Yeah. It just it really just goes back to, you know, how fresh of stats do you really want? I think so.
But you could specify that like on a per reader basis to whatever value you want. It wouldn't be baked in anywhere except for the BPF program.
Yeah. It is a good point. Yeah, the memory C group currently has that ability, and there's a flush that happens every 2 seconds for memory C groups. So yeah, if we were to rate limit that, I guess we could explore that as an alternative.
And then you don't need the C group FS files, the kfunc, right? Could be a kfunc.
Well, yeah. It's just it makes me think, right? Because that background flush, the way like it's going on every 2 seconds. When you're about to read again, it's also possible that even if you're over a threshold, the flush could kick in, right? So whatever time interval you're set, it's possible that some C group stat or one or more C group stats have been saturated to the point where now you have to do a flush. So the thought here was, could there be something that works with CPU stat and then could maybe be generalized to
But just one sentence. So mainly, I think that here it's the main point is
reduce the cost at the system level, how we can make it coordinated. So rather each one going separately, independently, flushing their own things, can we coordinate and reduce the overall system cost as well?
Yeah. And the second thing I want to talk about is that exact thing. So, okay.
Thanks, everyone. We are going to be back in 5 minutes.
The screen's super small, isn't it?
Yes,
Thanks
I
for
was using that. Yeah, thank you.
Why I'm really doing this. How about you? Pô, dá para aqui o negócio de organizar, né, cara? Tá meio com medo, cara. Essas tecnologias aí. Eu não consigo esse streaming, né?
Yeah, no, I know that.
Right.
So I think your question is same thing, right? It's really like doing switching this too much, it's causing some issues.
Yeah, we did.
So I just want to do this without setting.
It's fine if you're disabled for a short period, but right now you're disabled for like 10 minutes.
That's the thing. So anything for very long. There's a easier to make it like for this, because this one also was having a legacy. So what they did was disable to reduce the drone for each one. Yes. Like exactly.
Yeah.
So you're saying that it should be or the older one? Yeah. So I think that's the question.
Yeah, by the way, I went to this one last time. I like this.
High level.
We're barely flushing mostly.
Oh, thanks for letting me know. I will upload.
Yeah. Yeah, I guess it's the original idea is more thinking about it's just like
Five like virtual
Yeah, yeah, I mean, there's Really? No, I think yeah, awesome. Yeah. But I think the other person is the other one. Yeah, yeah. That's the first thing you're talking about. This one, right? Yep. Gotcha. I think you got to start. Right. Right. Otherwise, it's going to get everyone late. Yep. Because I changed the orders. Sorry? What's SJ?
Benjamin.
I know. I want you to show this. And people are going to borrow.
At the moment, David, not the next day one.
Are you still looking at the
You're right. Yeah. That should be a part of my work. Yeah. I'm no, I joined only 1 month ago. But I'm currently more focusing on making some workflows and tools and observing. Oops. Can you hear me? Okay. Thank you for joining. Let's get started. So my name is Sungjae Park, and I'm working in Crusoe. So in this talk, I will discuss about why we need data access pattern observability and introduce daemon in a very brief way, and then introduce some available access pattern formats that we can use at the moment and do some discussions. So why data access pattern is needed? That's what we can see by right here. That is, there are restricted seats, and there could be various audiences and various sessions that someone's more interested than other, and therefore we are now having so many empty seats here. Can we do that better, organizers? And so I can say this because I can show the seats right now, and in case of memory, if we cannot show the access patterns, then we cannot know whether we are doing well or not, wasting resources or need some more resources, etc. So to get some kind of such an actionable insight that we can make some benefit with it. So let me introduce daemon in a nutshell. So daemon is a Linux kernel subsystem that does spawn a worker kernel thread that sees if each page of the memory is accessed or not every 5 milliseconds by default, and then inform users the findings of the access pattern for every page every 100 milliseconds by default, and the time intervals can be tuned by user or auto-tuned by the kernel. So what it is providing is a kind of information for the access, including location, where the access has made, frequency, how frequently the access is being made to the location of the memory, and how stable the access frequency is for the location. And that means that frequency and stability means that we can also know the recency of the access pattern on each memory. And the overhead and accuracy is of daemon is something that very lightweight and very highly accurate because we are utilizing a kind of adaptive sampling and aggregation mechanism. I will not go dive deep into this, but what I can say at the moment is that on some real workloads, we were using daemon and we were observing that it is consuming only 0.0x% single CPU time. So in short, I would say that daemon is light, accurate, and scalable and automated. And it is available on 5.15 upstream kernels and enabled on most distro kernels except Ubuntu and the upstream default configs I tried, and Linus Torvalds has rebutted that. And also it is being used on some products and researchers. And one more thing is a second phase of daemon called Deimos. It is something interesting, but out of the scope of this talk, so I will just skip. In short, daemon in one sentence is that daemon is a Linux kernel subsystem for efficient data access pattern monitoring and access over system operations, like project reclaim pages that not accessed for 2 or more minutes. And we have some community, so if you have any questions or comments, please come to us. And that was the brief introduction. And then let's talk about the data access pattern format. So using daemon, we can get the data access pattern information in lightweight and accurate and scalable way. However, just having data or being able to collect data does nothing, right? People should read it and get some insight and make some actions. And having a good format is some kind of very challenging part because it means that we need to convince human, not machines, and that's not something that we programmers can do well in many cases. But I was trying, and I want to show what kind of format I was trying to make and get your input about the current available format and possible future formats. So the first approach was very straightforward or very lazy approach that trying to format or showing all daemon information, the location, frequency, stability, and recency. Namely, heat map and snapshot are the two formats. The first format is called heat map. The x-axis is showing the time of the recorded data access pattern. The y-axis is showing the address
space of the memory. And the color is showing the frequency. This is very kind of intuitive, and sometimes it is very useful, especially when it is being used on virtual order space. But I don't know how you are feeling about this graph. Some people might find it is very useful, and some people might think it is just noisy. Believe it or not, this is something that good part, I believe, compared to some more noisy things. And the noisy things coming from wrong scoping of the access pattern, time and address space to show. Anyway, it is sometimes useful, but sometimes people just say that it looks like noisy. The second format is called snapshot, which is just one time slice of the heat map. It is more lightweight to get and easier to get some insight from it, like how long specific memory was cold or hot. But again, the scoping is still the thing here. And the second approach was that, okay, maybe we are not getting good insights because Daemon is providing only limited data, and therefore we want you to augment the data that we can see in addition to what Daemon provided. So in this approach, we were trying to use it together with some more additional tools like trace points and memory information like meminfo file and the RSS data, and then show them all together as time series data. That is like this, and I now realize that I cannot show some demo here, so please forgive me of the bad example screenshot, but the screenshot is showing that the data access pattern in heat map and the virtual allocated memory and RSS and working set size of the process and what functions are hot functions at the moment so that we can know which functions are probably making the current access pattern. And then the third approach was, rather than adding more data, reducing the data to show. That is, Daemon's data is just good for machines to operate on. Machines can understand the data in very efficient way, but it is kind of too much for human in some cases, and therefore we try to visualize those information after dropping some information, specifically the location data. So we just refine the heat map and snapshot in this way. That is, sorting the information based on hotness, not the real location of the memory. That gives us this visualization. The left side is maybe a little bit looks noisy, but right side is sorted, the data sorted by the access frequency, and it shows something that easier to digest, I believe. I don't know how you feel, but that's better to see what is the size of the working set size and what size of memory the system really need. For example, in this example, the record was made on 1 terabyte memory that having some kind of heterogeneous memory called some faster memory and slower memory, and we were able to show if this workload can fit on the large machine while keeping the cold memory on the slower memory. And same applies to the snapshot. By sorting the access pattern based on hotness, again, we can better show how much of memory is really hot and how much of the memory is really cold. And the fourth approach was to making it more coarse-grained. That is, we were thinking that it is not only the kind of the data, but the granularity is too fine for human eyes. The lines that we have shown before are very informative and allows us to have some creative interpretation of the information, but it also makes some different interpretation, and therefore we wanted to have some discrete numbers that more alarmable or easier to aggregate on multiple machines like fleet. And therefore, we invented one format called idle time percentiles. Idle time is a term for representing how long of memory was not accessed, and the percentile is that of statistics. I believe that you know what it means. So when we have a snapshot, we can sort it by the access frequency, and then by finding the point of the line that showing the 50% of the memory, we can get the P50 idle time at the x-axis, and 75 and P99 idle time, and going on. And how it looks like on real world, we captured this data from a kind of 4 different real world workloads, and then visualized the information in idle time percentiles like this. And we were able to see that there are some common patterns and different patterns on different workloads. And cold memory tail, it is just a same visualization, that's same to the idle time percentiles, but just converting the x-axis and y-axis. That is, x-axis is showing the idle time, and y-axis is showing the size of the memory of the idle time. In that way, because we assume that most of the workloads would have very small amount of very hot data, and then the access frequency would go exponentially cold, we can assume that there would be long tail of cold memory. And this is, again, the visualization of the real-world access pattern we collected from 4 different workloads. And again, we can show that there are some common patterns and different patterns based on different workloads. And finally, if we can, so we made the coarse-grained data points with the idle time percentiles and the cold memory tail. But if we can, what if we can further make it reduced to just one number, that is the estimated memory bandwidth? Because Damon snapshot is showing how much of the memory is having how much of the access frequency, we can convert that to just single number estimated memory bandwidth. For example, if there is 1 gigabyte of memory region that seems to have accessed at least 10 times per second, then we can say it is consuming 10 gigabytes of memory bandwidth. And this can be a very simple number that can compare different workloads, whether they are memory intensive or not. And finally, okay, I thought that was the final, but there is one more. Okay, in case of some brave people, some people are just turning on daemon-based operations like, hey, daemon, find some pages that not accessed at all for a long time, and then reclaim those proactively, aiming some level of memory pressure or whatever. And then just deploy that to the fleet and then see if someone else. Surprisingly, this is one most successful use case. To be honest, they didn't do that in this way. They have done some experiment on their realistic workload, and then after that, they have deployed that, but they are having no real monitoring of the access pattern, but just deployed that to the service. And surprisingly, nobody has yet. So to wrap up, Daemon provides access information, and there are more than 2 ways to show that effectively. It is maybe a good thing for fans of oysters that having pulse inside, but some people wouldn't like that. Well, at least I'm not yet finding the real good thing. So discussion time. Do you have any input or comments about?
Thanks. Have you thought about emitting a metric for the working set size? Because I've done some working set size tools in the past, and they were experimental. They did the page access bit flushing, but they got sucked into Prometheus as an agent, and then people using it by default and then causing performance issues because there's a demand for this. There's a demand to be able to track working set size. I think in that situation, people wanted to know it for containers. So they were sizing C groups. So have you thought of, because I know you've said P50 and P75, someone needs to put a stake in the ground and say, this is this is the number for working set size, and then we can all agree that that's as good as it gets.
Yeah, thank you for a great question. So yes, we have considered about finding the working set size. However, the question that really difficult to answer is, so what is the duration of the access to determine that as a working set? You just got the real point. P75, P50, P25, what is the real point that's showing real working set size? I think there could be, however, I think that there could be some different approach. That is the brave people, because in Meta, it is well known that Meta is running proactive reclamation called Senpai or TMO, transparent memory offloading, that is finding cold memory and reclaim those proactively as long as the memory pressure stored time of the system is on the dangerous level. In that way, by running that, the whole memory utilization of the system becomes a kind of real working set size. And therefore, similarly, using Daemon, we can also do the similar proactive reclamation, and then remaining allocated memory on the DRAM would be real working set size. Of course, this again gives us a question. So what level of memory pressure store time? Meta is using 0.01% or 0.05% according to the paper, if I remember correctly. So it is still remaining question. In short, I also want to find the working set size and just show that, but I find no good way to determine what is the working set size yet. So I'm just unresponsibly offloading that to users. Any other questions or inputs? Thank you very much.
Daniel, hey, pleased to meet you. Nice to meet you. Is it okay to use this laptop?
Yes, but I just uploaded 10 minutes ago the slides.
I can
Okay. It's a, yeah, I mean, slightly.
Can you check this is the latest version?
No, it's not. No, that's not it.
Let's see if it is the new version now. Center. I think it should be this one. Left and right, yes.
Yes, it is. Thank you. I'm sorry. Hi, everyone. I guess, yeah, my name is Daniel Gomez. I'm working with Samsung at the COS team. I'm part of the kernel team, and yeah, today I'm going to talk about what I've been using eBPF for in regards to error injection, and basically my knowledge and research regarding how error injection frameworks, what are the error injection frameworks we have currently in the kernel, kind of a bit the status of it as my understanding. So please, if there is anything wrong, of course, correct me. And yeah, how are we using this in the module subsystems? So I think as the fault injection framework was introduced back in 2006. Basically, you have a should fail function where you just inject in any arbitrary point on the kernel where do you want to fail in that particular function. It's using debug FS in order to control your injection points. And some of the examples you may find, it's the NVMe driver and also the slab allocator, where you may be able to, make this fault under certain conditions that these different subsystems and provide. Later, a decade later, basically was introduced the BPF error injection with that was Joseph Bathig. They call it, they introduced a macro, which was BPF _ allow error injection, which introduced the concept of or tagging a specific function and then using BPF override return helper to ensure, so to actually, make sure that that function injects any error that that function may be able to return. So I think the claims were that they were not predictable, the previous framework that the kernel had. And with that, you could have a very deterministic approach of introducing errors. First was only supported with kprobes, and the first user, of course, it was Btrfs, because that was the Joseph Bathig domain. Later, a month later or so, it was renamed, and now it was not only exclusive to BPF, and it was integrated to the fault injection framework, and it was generalized somehow. So now, instead of using BPF and or eBPF code, you would just use again debug FS for controlling in a generic way if your function needs to be error injected or not. So it's very easy to annotate like a function and make it error injectable. It just requires you to do these changes, right? This is an example for the file map that was added also from Btrfs side, which introduces this ability of error injection in the file map at page cache. What are the requirements that you need as to make this possible? They are very basic. It's just, of course, the error injection. The error needs to be checked. That's from the fault injection framework. There's nothing from the BPF side when this was introduced. I guess it was somehow normalized, and everybody agreed in that sense. Yeah, the second requirement is that the code, of course, cannot change any state before you do the error injection. If that's the case, I guess you can always refactor your function and make it error injectable. So why was introduced? I already mentioned, right? Part of it, but testing is hard, in my opinion, in the sense that it's difficult to test or to replicate some specific environments, and may require you to go into production and then run your testing there, or maybe just try to simulate it in a manner. So my assumption is that error injections or error paths may be under-tested, may not occur in your normal testing scenarios. And for sure, you wanna make it deterministic and reproducible, right? You wanna inject an error, and every time you do and go through that path, then it's reproducible. So in that case, you can make sure that the error path is properly handled, and you don't break things, or things are behaving the way you want. So in summary, we have different frameworks. I would say maybe the fault injection framework was, as it was first introduced in 2 decades ago. We have the specific one with should fail, which basically you have debug generating this syskernel debug and whatever you are exposing there. And the generic one, which was based originally on the BPF approach, and you just get a fail function in debugfs, and then you just inject there what function do you want to inject your error, and then to just use the normal debugfs fault injection features. So the fault injection, it's using debugfs, and it requires kernel code, changes in your code, in your sources, and arbitrary points that may or not you want to test. And that led, in some cases, this is an example from a colleague that tried to upstream error injection using this approach, and it was considered like it was polluting the sources, right? All of a sudden now you have code that leaves between what you want to do and what you want to test. So this was rejected, and but still, the error injection is useful, and some others are using it, right? So some of the examples I already said, and even the fault injection framework provides you some utilities. It's very feature-rich. You get all these phase lab and page allocation and so on. You get features like, okay, I want to fail under a specific condition, like GFP flags, whether my function was called with that flag or not. So you invoke under certain conditions, but again, you're using this kind of way of controlling that it's in the kernel together with your sources. So may not be convenient unless you are willing to accept that. So yeah, then we have the generic one, which is based on what I said, that it's using the same features that it provides all of the specific ones, but using the fail function part. And then we get the BPF approach, which is using the only the annotated allow error injection tag, and then you get your code that it's living in a standalone tool, separated from everyone else, right? I think this is a convenient way of having your error path being tested and whatever you want to test, your real code that doesn't need to be mixed. Then we have XFS error tag. That's something I personally discovered, that they have a custom error injection framework, also via debugfs, but they don't use the as far as I know, the fault injection. So yeah, definitely there are uses in the kernel, but what is the tooling at the moment? It's like we have the memory management, the NVMe, but I don't know what they are using. I know, for example, the XE driver, Intel XE driver, it's using because they reply. They are using a specific test suite. XFS test uses its own framework, of course. But what about BPF? So I know we have all these users, the driver, Btrfs, the Intel XE driver, Btrfs, Microsoft Surface, FileMap. But where is the tool? How can I use it? if I want to make sure, right, that something is not broken after my changes. So we have like more than I would say 100 users of this tag. Not 100, but only the ones that are using allow error injections are around 60. So it's definitely spreading across the kernel. But my understanding was that not everybody was actually aware of how this thing was. So I started a tool called, which I called it mod error, which was intended to add another tool for error injection using BPF. BPF because of the convenience of having the tool and the code living in a standalone manner, right? So in this case, I put an example where I invoke mod error under a specific error, in this case 22, and then for a specific function that I want to inject, and then just the output that I get for that particular one. And in this case, I added a feature, right, that I can, because of eBPF, I can just access to any of the arguments that the function has. And in this case, I'm interested in the name of the module that I'm trying to load and only that particular module. So I add that feature, that's mod name. In this case, it's triggered by the BRD driver module. So I added these initial error injection points, all these three, for different reasons. The module loading mechanism is basically a state machine, and it's interested in checking what happens in between the states. So I added these points. Later on, we found that there was a memory leak problem that was also interested to track. So we added an error injection point there. So we have these use cases where we use the tool for one for read-only data after initialization. The module driver initialization would go and specifically configure some of the else sections as raw data, but it may fail. And that was a code that was not tested properly. So we ended up using eBPF for testing what would happen when the module initialization failed. And what happened is that, of course, you couldn't recover from that. So we ended up with trying to find a solution. But it was convenient for using this for just not, going to the sources and modifying your code, just using a convenient tool for that. Another one is the memory leak problem that I mentioned. You find, I tried using KMM leak, but there was a part that is basically ignoring all the allocations that module initialization had. So I use reinjection again in move module in this case to validate a specific problem that a container reported, and basically again a convenient way to test it. Otherwise, it would require to have modify your sources, which is what he ended up doing at the beginning, and then I managed to replicate it easily with this. So now you can have it in a CI manner, right, and make sure that you don't introduce the bug again. So I try upstreaming the tool, but the feedback that I got was, okay, it's a valuable tool, but I'm not sure basically if there's any value to have it in tree. If there is any a specific error injection point that you are making is not clear, at least for the one who was reporting this. And yeah, the error injection points in this case, they need to be difficult for testing. I don't know how would you test it if you don't have it without BPF or error injection. I cannot make reproducible error frameworks without this. So for me, this is not clear. On the other side, I got like, it's useful. We do add random tools. That's what we have in self-test. Whether they are based on BPF or not, I don't think they care. Well, we care in the self-test framework folder. So the suggestion was to go under that path, right? So not clear feedback. Or clear, but contradictory in some manner. Then the XC maintainer was interested in having it generic, so make it generic and then I may be able to use it. I don't care where it is, but I think it's convenient to have it in the kernel. Maybe we can use it in the K-mode project, but that's gonna be very specific. So yeah, I have a lot of questions like, what do we do with this? Shall we make it a generic approach? Another alternative is the inject Pi in the IOVisor project, but it's more like an eBPF tool generator. It's using the deprecated Python version of eBPF BCC. And I try using eBPF because that's what you are supposed to do. So what are the other uses of allow error injection do? I don't know. If you guys have any feedback, please reach out to me, maybe in the hallway or whatever, because we are running out of time. So we can make it already, mod error is already almost generic. We can make it, but there is like some hard-coded points that I don't like it. And if we are willing to move it to or promote it as a generic, we need to fix them. So happy to get some feedback on the pull request that I send. Maybe I'll send later an update on that during the conference. So we need to scale, and for that we need to make it a way to make this function discovery. Of course, leveraging a BPF, maybe porting some of the fault injection features back to the tool, and using maybe stack trace analysis where you could just also get, your points and your conditions. But I had all these specific hard-coded ways of parsing what I intend basically to error inject, and I need basically feedback on that. But of course, the problem is the original feedback was it's valid, it's not, I'm not sure. It's not clear for me. What do we do? This is a specific examples that I think it may be solvable and still make it generic, but also specific to subsystems to add specific features. But where do we put this if we are willing to move this forward? We have a very fragmented system, in my opinion, with fault injection and tooling and around. Maybe it would be nice to have a common tool across the kernel. IOVisor, I try upstreaming a block line for a few years, no feedback at all. So I don't think IOVisor is the proper home for it. Kernel sources, I got this BPF code tooling, no, and recently they got removed. Some of the tools got removed. Unclear. Maybe we can put it in gitkernel.org and have a specific error injection that people may reach out and find the tooling. So I put here a specific roadmap, but I don't want to enter in details because there's enough questions. I think already I launched. We can make it generic. It's just that where to find the home. It's I think the first place. Naming is of course important, but what do we do? What do you guys? Do you have feedback? Is it useful? Is it not?
Thanks. So I think there's a small number of storage nerds and memory nerds who will use it as part of kernel self-tests. The bigger potential area of uses is zero-day vulnerability patching. Similar to how SystemTap has done this for a long time, where as part of a CVE, it's like, here's a SystemTap script you can run right now to dynamically patch the kernel. And Canonical's got its own thing as well. So I think if you went down that path, you'd suddenly find that it's super important to the security space, although the tool that you've been generating looks a bit too restrictive, because if I want to do a zero-day kernel vulnerability patch, it's going to be algorithmic. It'll be like this kprobe, if this argument equals this, then return not allowed or permission denied. So I think if you go down that path, you might find it either needs to be more dynamic or you turn it into a BPF trace thing.
To make it dynamic, I know the inject tool that we have in BCC IOVisor, it's using predicates, which I think it allows you to access all these arguments in your function signature and then make it customizable somehow. then it may be flexible enough for doing this thing. Is that the way would you go with?
Yeah, so iAdvisor is the old name. It's now eBPF Foundation. And I just think the stuff you saw in BCC, there's just so few people who are actually doing the dynamic error testing. That's why you might see there hasn't been a commit for a year. It's super important if I'm doing storage IO, how am I going to simulate all these NVMe errors? So I need it. But like all the people in the world that would use that tool would fit into a quarter of this room. But if you make it do CVEs, 0 days, you've got thousands of people need it.
Okay, thank you.
Just a question, like I still find it, I mean, maybe the ecosystem is lacking here, like to annotate a function so I can fault inject with eBPF, I still need to recompile the kernel. Is that correct?
That's actually a good question, and perhaps Brendan can answer, because as far as I know, not everybody is using enabling error injection framework in their production systems, because that's a thing you don't want to have it in production. As far as I know,
Moreover, we use like kernel hardening features with disable debug FS. So
yeah, but debug FS would not be able. This is going through the BPF path, so you don't need debug FS, but you still need the fault injection features in the kernel to be enabled, which may not be available in your production
my also point is like for a debugging case, the whole point of having a predefined injection points is kind of fails, and because in the debugging case, like, yeah, I agree with security case, you kind of like want to patch this, but in the debugging case, I don't know where I want to inject the fault before I actually see the problem. It's like, oh, if I could simulate a fault here, then I could debug this problem. But if that function at this point in time is not annotated, it kind of makes it useless for me, right? So like maybe there is a way to have like, oh, I want every function in the kernel to be fault injectable or something.
I think that's a security problem, making everything like injectable. What people do with just find an error and then, okay, I need this function to be error injectable, and then they will replace it. They will do the code. Yeah, I'm running time. Yeah.
I have a question. So I find this tool very useful. First of all, and great talk. So the issues that we have faced in our work is that the function fails at some midpoint, like for example in the module driver or driver initialization functions, and then you have to write or fix the bugs where you left halfway in the initialization process, and there are a couple of memory lying around. So right now, is this tool in the stage where you can annote somewhere in the middle of the function, not like the function as a whole?
You are not typically you don't annotate. I mean, unless you use the old framework. You just want like a production code and then make it real. Like okay, now if I have an error in this particular path, then I get an error. So you can do it in the middle, but not you need to have a function that is annotated. So in that case, you would need to refactor a little bit your code if you want to make it happen in the middle. But I think for that you use the fault injection framework.
Right. Okay.
Hello. Hello, everyone. My name is Vlad. I work at Meta, and I'm working at Meta on doing kernel release. So why am I talking here? We developed a few things at Meta for looking at kernel health, and I think it's interesting to share this with the community. On the other hand, I want feedback. We want to know if we're doing something obviously stupid, because no one has all the answers, and we might be doing something very stupid. And also, I'm curious what others are doing. So, what is the actual problem here? So, we have millions of servers. We release kernels very quickly. We try to stay very close to the latest upstream. version, major. Also, we have a lot of hardware types. So things fail in different ways based on the hardware. And we usually, like, the question that we're trying to ask is this a hardware bug? Is this a gamma ray or something? Or is it just a kernel bug that we discovered? Obviously, we have different services. We have services that do a lot of memory allocations. We have services that do I/O. We have services that abuse the various kernel subsystems in different ways. So each one of them will fail in a different way. The other problem, obviously, is that we hire a lot of very smart people, but we only know about 1% of the kernel code. We don't know a lot about anything else. This talk is not about measuring performance. It's about metrics and observability that we use for releasing new kernels. Why it's not about performance is because if you think about it, performance at the high level is about what the service does. Do we get enough requests per second for Instagram? Do we get enough, like, is the latency small enough for displaying an ad somewhere? Obviously, that would translate at some point to a kernel metric. But at the high level, we're not interested in the kernel metrics when we release, but we are interested in the top line metric, which would be the service. Right now, for example, we're running the latest kernel that we have in the fleet is 6.16. We're preparing to work on 6.19 when it starts to appear, or it already appeared upstream. So, but we're going to wait a few weeks. We're taking vacation now and coming to Japan and doing other stuff. You'll see on the right side, there are things that I mentioned in the presentation that are maybe not, I don't really have time to talk about in the presentation, but if you're curious about them, please stop me and ask me about them. Okay, so you're going to see this diagram a few times in the presentation. It's about what we do and gives you an idea of what is the next thing that we're talking about. It obviously starts with Net Console. So there is Net Console, probably everyone uses that or knows about it. Kernel log stuff, it goes on the network. For us, it goes on a virtual IP that is we have a listener for it, which is netconst, which listens on this virtual IP. In every region, there is a cluster of these listeners. We do this for reliability purposes. Basically, if in one of the regions the netconst fails for some reason, the messages are still kept. They go to a different region. They're received there. Then netconst sends this to our logging infra and stores them in a table. We do something interesting here. For every host, we add user data. Net Console has this feature called user data, which allows you to add stuff on the host. That stuff could be the kernel version for every message. It could be the scheduler that you're using. It could be some information about the hardware type. We codify the hardware types. We have like 10 groups, T1 to T11, let's say. And we add these to every message so that we can we don't need to do a complicated and expensive join at some point, because that data exists in other places. But if you have to query it, you'll get a join of millions of rows by millions of rows, and it's expensive. So what do we do with this information from Net Console? We extract crashes, and we extract what we call alarms. And I'm going to talk about what these are. obviously, for crashes, I heard it already 2 or 3 times earlier today, we use kdump. We have a kdump kernel. It has a very small init ramfs where we run the make dump file. We store it locally on the disk. There are some problems here. Obviously, we need to load the kdump kernel. So if the kernel crashes before we reach that point where we load the kdump kernel, we are not able to capture the crash. We're thinking of ways to capture those crashes as well. I heard a few ideas today. pstore, maybe that's an option. After the dump is made on the local disk, then the next problem is how do we analyze it? We developed a tool internally. Doesn't matter the name. We're preparing to open source. This probably is going to change name. But basically, it orchestrates a few existing tools like Dragon, LLDB, a few others to extract information from the crash. We get a huge JSON file with all this information gathered. Again, it contains hardware type and maybe obviously the stack traces, the CPU states, a lot of structures, a lot of kernel structures, adds them to this JSON file and sends it to our logging infra. Our kdump kernel doesn't have a network stack, so we can't do that. We can't send it directly from kdump. The reason for that is that it will become too big, and also it's not very stable. We want something that we can rely on, and it's simpler if we rely on less things. So the other part of what we do is look at what we call alarms. What is an alarm? Basically, it's a message that we discover in net console in the kernel log that tells us, hey, maybe you should look at this. What's going on here? And these are quite interesting because they don't necessarily tell us there's a problem, but they tell us that we should look at something. We classify these things using, basically, we have a set of matchers that tell us, hey, this message means that there's a problem with Btrfs. This message means there's a problem with RCU. This message means there's, I don't know, something else. The other thing that we do with these messages is, for example, if it's a stack trace, netcons sends messages one by one. Obviously, a stack trace is not line by line. You can't do anything with it if you look at it line by line. So what we have this receiver, this netcons D, which tries to look at messages and tries to create some context of, oh, okay, we're starting a stack trace here. Let's look at the stack trace. Let's gather all the lines and combine them together. So coming back to crashes, how do we deal with a crash? Basically, what we want, like we have millions of hosts, so probably we'll have thousands of these crashes per day. We want to know what's common. And in a way, what's common is the stack trace. So that becomes our classifier, our classifying key. We hash parts of that key and basically group together all the stack traces that are related to that. Obviously, we have all the information. So we have the kernel major, we have the version, we have some internal versioning system as well on top of what's upstream. And we get events which represent a group of things that happened with with the kernel. So, for example, we'll have this key, and then we'll have maybe 20 instances, 5 that happened on 613, 10 that happened on 616, and another 5 that happened on various other kernel majors that we have running in our fleet. The other thing that we do here is we're trying to normalize this because, okay, we have 200 of these crashes per day of a particular stack trace that happens per day. Is that a lot? Is it a lot? Is it not a lot? How do you know that? And the only way to know that is by counting how many of those kernels are actually running, or how many of the hosts are actually running that particular version of the kernel, or are running on a particular type of hardware. For example, we're looking at ARM versus x86. Is it happen like, is this crash happening mostly on ARM? Is it happening mostly on x86? Is the percentage on ARM higher than the percentage on x86? So basically, what I'm trying to say here is that the metric that we have in the end is crashes or alerts or something per 1,000 hosts. We chose this 1,000 as a normalizing number. The problem here, and we still didn't solve this well, is that we like small numbers. So for example, if I release a new kernel, that kernel is going to be on 20 machines. Does the fact that it crashes on one host, is that bad or not? It's 5%. So technically speaking, it's a lot. But realistically, maybe I'm just unlucky. So this problem we didn't really solve. We don't really know right now how to look at small numbers. We know how to look at big numbers. So if it crashes on 5% of the host, that's a big problem. But it's a big problem at the fleet level, not at small chunks. Here we're kind of saving, like we're trying to cut corners because we can't look at all the problems that we discover. So we kind of have a limit of number of crashes until we start an investigation, which is normal. We chose a number. I was telling you earlier about this tool that helps us create events and group them together. So we call this tool LogView, and basically it's the same tool that allows us to do triage. Because once you add an event in this LogView, you have all the data, and then for the events you can add multiple dimensions. And these dimensions are going to be maybe what systemd version you're running, what scheduler you're running, what type of hardware you're running on. So it allows you to split the data by all these dimensions and see if there is a correlation, if you see a pattern, like is it crashing on this hardware type more than on other hardware types. And it basically guides the investigation in a certain direction. Now, in the end, we're releasing a kernel, so we need to make a decision. And in order to make this decision, we're going to base that decision on actual numbers, right? So the fact that it crashes more or less on some workloads, on others, is not a number. It's not, you can't put your finger on it and say, yes, this is the problem. So what we do, we build this table, which is a complete denormalization of all the data that we have about kernel. And we call this kernel health. So we look at about 10-ish metrics. Host crashes, process crashes, BPF failures, container failures, host connectivity. This is actually an important one. Like someone said earlier, it's pretty hard to look at all the network metrics. So we look at one top line metric, which is, can we connect to the host? If you can connect to the host, then it means that the host can connect to us, probably. So we get all this data from all these sources, we combine them, and then we explode the state by giving information about this type of metric applies to this group of hosts, to this kernel major, to this arch, so that we can then split the data and decide if it's relevant for particular groups that we might be interested in. Last, like I said, kernel performance is not really a huge thing, but we're still, in a way, it's a much simpler problem because service owners can own those metrics, they understand their services, and they can actually give us an idea. What is not clear and what we didn't solve yet is at which point in the kernel release we start bringing in performance as a release blocking measure. Do we start early? Do we get some information and we stop? Or do we get the information and then we don't stop and get more information later? I was hoping we don't get here, but no, I was hoping we don't get here because you stopped me in the what I was presenting, not because I don't like questions.
The question comment. I'm actually just your counterpart in Cloudflare, have exactly the same problems, and we roughly do exactly same solutions. So you're probably either we both do something stupid or maybe there's something into it. Like specifically what we use, I just wanted to share. We kind of have a similar, what you mentioned as logview. We call this kernel events, a small daemon that just reads a dmask, not dmask, but the dev k message, so it's easier to read. And we parse the stack traces and we literally convert them to Sentry messages and send them everything to Sentry. And I found that Sentry is quite a convenient, and then you add the metadata, as I said, like kernel version, hardware version. And once you send all of them to Sentry, Sentry is actually very convenient. Then you can slice and dice. So like I can see these type of issue, like in these types of hardware, in this type of deployment. The trick part is that we still haven't figured out how to properly group these events into issues. Like sometimes you get like different stack traces, especially in networking, for the same issue. So how do you actually encode that information into your daemon to say like, no, this is kind of the same issue. So Sentry expects you to kind of like group the issues yourself according to your context. And I would be happy to kind of like collaborate on that, understand how to do it better, because it doesn't help if it goes to different.
It's still kind of manual for us as well. But we rely on subject matter experts to help us say, yeah, these two things are kind of the same. Let's group them together. And maybe we add some of this information to the tooling that does creates these tasks and these investigations for us.
The other thing I found inconvenient is the actual kernel message parsing is a little bit iffy because the kernel itself doesn't have a good hygiene on how to produce consistent outputs. It's like for different error types, like KSAN have one format, like somebody added for a TPM hardware error, another format, and it's like you have to encode all these differences. It'd be nice if it was like XKCD, like one standard for all, so you can write easy parsing tools for that.
Yeah.
On that topic, is there, you mentioned that you had something that goes through and collects the printk multi-line messages. Do you have any good solution for interleaved messages? You interleave
what? Sorry?
Interleaved messages. So say you have two or three or five things that all happen at the same time and they all generate stack traces. I know you can use printk caller, but that depends on whether you have that config.
I added something on that console that prints the CPU that is printing the message, so you can split by that. That's the way we found. So for every net console message, we have a bunch of information. One of them is like what CPU is printing that message. So if it is interleaved, it's not.
For memory allocation profiling, we just drop them.
Sounds like a good problem solve.
Yeah, so this is how we decouple messages. So if you have a proper kernel config, you get either the CPU or a task that does the print. So if you get an interleaved, you can like separate them by task or CPU. I think so, yeah. But like you basically see it in the message. You have a column. It's kind of like if it's in kernel, it's CPU one, or if it's in a task context, it will like task ID number one.
Thank you very much.
What is the name of this? Yeah, that's right. Yes.
Just testing. Can you hear me? Yeah, okay. Can I go ahead?
Yes.
Okay. I read the text now. Sorry. Thank you. So, hello everyone. I hope you're doing well and enjoying the conference. I am Mauricio, a kernel engineer at Galia, and today I'm going to talk about improving page owner for profiling and monitoring memory usage per allocation stack trace. I'm going to rush a little bit, so please stay with me. The agenda for today is what is page owner with some usage and examples. Then we're going to talk about profiling and monitoring with page owner, go through some definitions and issues I found with that. And then finally, improving page owner, basically its output format and support for swap space, and then some discussion. So what is page owner? Page owner is a debug feature for memory allocation or memory usage, depending on how you look at it. It stores the stack trace and some more information of the memory allocation for every page in the system. It does that by combining hooks in the page allocation code, the page extension mechanism, stack depot, and debugfs. In this diagram at the center, you have struct pages, which describe, struct page, which describes every page allocated in the system, and struct page extension, which provides additional information to it, which can be used by other parts of the code. In the page allocation function, we have hooks that call into page owner. Page owner is going to ask stack depot to store that stack trace of the memory allocation. For example, a system call that called into VFS that called an actual file system, then the memory management code and the page allocation function. And page owner is going to store a reference to that stack trace in stack depot in the page extension information for the particular page that was just allocated. All this information is available in the debugfs, so you can just read that with cat, for example. Page owner then, it provides a system-wide snapshot of the memory allocations per page and per stack trace in the system. And you can use it to answer questions like, what stack trace allocated this particular page? Its owner, I guess that's where the name page owner comes from. And how many pages are allocated by this particular stack trace? A use case example of mine is to profile the system-wide memory usage over time with swap team, and then monitor the top memory consumers. How you use it? You build your kernel with config page owner, boot with page owner equals on, and then you have two files in debugfs. You have page owner, which is going to give you the allocation stack trace of every page in the system, and you also have show stacks, which gives you how many pages each stack trace has allocated. Some examples. First, for the question, what stack trace allocated this page? In the first line, we are using the dd command to allocate 256 megs in TeamPFS. That's in memory. And then we, on the second line, read the page owner file, which gives you the stack of every page. We can see a snippet here for one page. The file lists all pages. You'll see the order of the allocation, the GFP flags, the PID, thread group ID, common name, timestamp of the allocation. On the second line, you have the page frame number, some page flags, and more. In green, you have the stack trace, of course, and the members group it's been charted to. We can just use that file to calculate how many pages have been allocated by DD, and it's 65K pages, and that converts to 256 megs again, which is what we originally allocated. And another example for the other question, which is how many pages are allocated by this stack trace. Same thing, DD allocating 256 megs on memory. We just read the show stacks file. It gives you the stack trace and its number of pages. Converting that back to megabytes, it's 256 again. Okay, so how we use it to do profiling and monitoring? Just some definitions. Sampling with page owner. Page owner gives you system-wide snapshots of the memory allocations, the number of pages per stack trace. For profiling, we are basically addressing the question, how many pages are used by each memory allocation stack trace? For example, we can analyze memory usage and identify the top memory consumers. And for monitoring, we are addressing the question, how many pages are used by some memory allocation stack traces? For example, you want to test a code change to make sure that it's not consuming more memory than it consumed before, or something changed. Or you want to verify memory constraint cases. So you have an application and want to make sure that whatever it calls in the kernel is not going to use more than a specific amount of memory, and keep an eye on that. And okay, how do we implement that? For sampling, we're just going to read the show stacks file. And for profiling, we have to do a few things for every sample. We have to calculate a unique identifier, like a key or a hash, for every stack trace in that sample. And then you have to store the number of pages used by each stack trace, accumulates the total, and finally calculates the percentages for each stack trace. Monitoring is similar. You just have to calculate the key or hash again for every stack trace, filter some of those which are interested in monitoring, and check the number of pages they use. This is computationally expensive, particularly because for both profiling and monitoring, for every sample, you have to calculate this unique identifier for every stack trace. That comes from the output format of the show stacks file. It prints the stack trace, a bunch of text, and the number of base pages. So the issue there is that, as I mentioned, profiling and monitoring, they have to calculate this unique identifier for every stack trace, and there might be hundreds or even thousands of different stack traces in the system, depending on how long it's been running and how many different programs it has run. And that's for every sample, every 5 seconds or less, depending on the frequency that you want to profile. And this process is very wasteful. It repeats the same calculation and achieves the same result for all these calculations for the non-stack traces on the samples. It's even worse for monitoring, because for monitoring, you must calculate all the unique identifiers of each stack trace, but you're only going to use a few of those. So the idea there is, what if the unique identifiers for those stack traces were provided by the kernel instead of being calculated, for example, at user space? If that is cheap, it all will become cheap. So we created this other file, which is show handles. It has the stack traces handle number instead of the stack trace text, and its number of base pages. The implementation is quite simple. It just uses stack depot, which already has unique identifiers per stack trace, what's called the handle number. So we have a different debugfs file now, which is show handles. In this example, you can see we're just checking what's the handle for the number of base pages that we got in the previous example. And the handle number is this number in blue here. That leads to the question, okay, now where's the stack trace for this number of pages? Then we have had to come up with this other file, which is show stacks handles. It has a particular handle number and its stack trace text. So now you can resolve a particular handle number to an actual stack trace. It's a different debugfs file, and here's a command to just query what's the stack trace for a particular handle number. In this case, the one from the previous example, and you get the stack trace in green. The result of this is that the sampling is now very efficient. You just have to read show handles, which makes the kernel print a lot less text than the stack traces again. It just print numbers. It's a lot faster, and there's a lot less copying to user space. And then at the end, you can just resolve the handles to stacks by reading this other file just once, instead of repeatedly calculating the identifiers all over the sampling phase. Here's an example with the output format of the 3 files. Again, same thing, just dd writing 256 megs to memory. Then we read the show stacks file, which is the original one. You get a stack trace and the number of pages it uses. Here in the middle, you have the first new file, which is show handles. We're creating the handle number for a particular amount of pages, just to use the previous example. You'll get the handle number, and then you can resolve the handle number to a stack trace using show stacks handles, as shown here. Oh, and those changes have been merged for 6.19 last week. Second improvement is swap space support, because currently PageOwner, it does not support pages in swap space. And so profiling and monitoring are incomplete and broken when you have swapping. The issue there is that on swap out, the page which is being swapped out is freed, and another memory allocation is going to use it. So you have a different stack trace, which is going to override the initial stack trace of the memory allocation of that page. So profiling is not going to see that page anymore. It becomes invisible. Sorry, it's not going to see that particular page use this stack trace. It becomes invisible. And monitoring is not going to find it anymore. And at swap in, another page is going to be allocated to receive the contents loaded from the swap device. And this is a different stack trace than the initial memory allocation stack trace, because this page allocation happens at the swap in code path. So it's a totally different stack trace from whatever code allocated the page in the first place. So the idea there is to store and load the stack trace of this initial memory allocation at swap out and swap in. How we did that? The implementation is based on these swap hooks that we see in ARM64 memory tagging extension. The implementation is fully based on it. We have a swap out hook in which we store a copy of the allocation stack trace and some more information like the process and timestamps. And in the swap in hook, we just load this copy back, overriding the allocation that has been performed at swap in. In the diagram, it's similar to the first one. You can see struct pages, page extensions, and the swap out and swap in functions. They have hooks which call into PageOwner. PageOwner is going to create a copy of some of the information in the page extension struct and index it in an X-ray. It's going to index that by the swap entry. And then at swap in, it's going to query that swap entry from the X-ray and copy that data over the page extension structure, overriding some of the information that is there. And again, all this information is available in the debugfs. So how do you use it? There's this RFC patch set I sent out last Friday. So you build your kernel with config swap PageOwner now, boot with PageOwner equals on, just append a comma swap to enable this different behavior. Now the original file, you're going to find lines that have a trailing swapped at it to report whether a page has been swapped in, and you know that its stack trace has been overridden from what was stored by PageOwner. And then you have a new file, which is swap PageOwner, which is going to report to you the pages that are in swap space, just like PageOwner does for pages in memory. Example here showing this new file. Okay, same thing, allocating 256 megs with DD. Here we're going to use an uppercase DD just to, okay, thanks for the warning. Just allocate some more memory to push the original 256 megs to swap. Then we can see that the page is allocated by DD in the swap page owner file. It has the PID, thread group ID, timestamp, swap entry number, and the stack trace. We can also, just like we did before for page owner, we can search in swap page owner for all the pages allocated by DD and count it. It's again 65K pages, and you see it. It's 254 megs. So almost all of the file went to swap. The second example is a before and after. Before these patches, we're going to see that the initial allocation stack and information is lost during swapping. It's a little bit more complex, but it's similar to what we saw before. Again, allocate 256 megs, check it's assigned to DD before we do the swapping. Use uppercase DD to push this original memory out to swap. And then we're going to use cat to read that file created by DD again. And check the memory used by DD and cat. We can see that DD now uses 1.6 megs, now in yellow, and cat has been assigned 258 megs. So the information that was originally assigned to DD is now assigned to cat. And after the patch set, we'll see that this information is maintained. We just do the same initial steps, and then when we check the memory assigned to DD and cat, DD still has 256 megs, and cat only has 7.8 megs. That's it. Questions? Did you like the colors of the terminal? Just kidding, but I hope it helps to follow, the different pieces of information in case you haven't seen PageOwner in a while. Questions I'm interested in is whether you think this work may be useful to you, whether you're doing profiling and monitoring, or just noted that the lack of support for swap space in PageOwner complicates your life, or if you see any issues or potential problems with these changes, or if you have suggestions or enhancements or any other questions. If you have a chance, please comment on the RFC. And just before I leave for open for questions, I'm not attending the conference in person, and I'm on a different time zone, so I cannot kind of stay in the chat. So please just send me an email. You have my email address in the first slide or in the RFC, and I'll be happy to answer that. That's it. We have questions.
So what is the cost of, memory cost and the performance cost of running this in production?
I have not measured it. I don't know. I recall that from the page owner description in the kconfig file, it mentions it has very high overhead. So I'm not exactly sure that the swap side of it is going to complicate things. Actually, for profiling and monitoring, at least the efficiency of using that information is improved, but I have not compared, the memory usage and performance impact, say in CPU cycles of running with and without PageOwner enabled. I can take a look at that. That's an interesting data point. Thanks for the question.
No, you're right. I work in Qualcomm, so it's more mobiles and stuff. So we don't enable PageOwner, and PageOwner is only for our debugging purpose, because it's pretty much, even though let's say I have 5,000 devices under test, it's kind of disturbs the whole testing and slows down some of the use cases. So we get a crisis, and then we suspect that, okay, let's get some extra information, get another build out and do it. And the question for you is that, is it like tested also with ZRAM based configuration, or I don't know, what's your testing environment? Is it like desktops or is it embedded systems?
I have initially tested on ZRAM for the test platform I was using. And now I'm just testing on a VM for development purposes.
Okay, thank you.
Thank you.
I have a question. So the PageOwner, when we build a kernel to enable the PageOwner, it doesn't support the swap, right? So should we disable the swap?
To enable swap, you have to, sorry, if I got your question right, in order to enable swap support, you have to apply this patch series that I sent out last Friday in this link, and then use the commands in the previous, some previous slide. I'm gonna go, yeah, here you go. The slides are attached in the talks page in the LPC website. And you can just send me an email and I'll be happy to help.
Thank you.
No, thank you.
Thanks.
Thanks, everyone.
Take presenter. And what is the name of that presentation again?
Hello. Yeah.
Guider. Which one?
Can I get presentation authority?
Okay. And
Should be presented now.
Can I share my screen?
No, it's done through the system over here. So I think you should be in presenter mode now, and you should be able to switch slides.
It's okay. Okay, let me start. Hello, I'm P3. Today I'm going to introduce Guido's features, including lightweight performance data collection and remote APIs to serve the collected data and its embedded commands. This is the presentation contents. Now let's talk about why Guido is needed and how it provides real-time monitoring, automation, and remote APIs to solve these problems. Today's embedded Linux systems, including Android, are more complicated than ever. So we run heavier apps, many background services, and even real-time tasks on hardware that's still quite limited. Because of this, we face three common problems. First, it's very hard to catch performance issues at the exact moment they happen. Many issues appear for just a brief moment and disappear before we can open any tool. Second, even if we capture something, the information is scattered. Log, trace, and kernel events, everything comes from different places, and putting them together takes a huge amount of time. Third, a lot of performance issues only appear sometimes and then disappear again. So they don't always happen. They are hard to reproduce and without continuous monitoring. So they are almost impossible to diagnose. So now tools are like AppTrace, Perp, and ATrace are extremely useful, but using them usually requires a lot of manual work, turning on multiple trace points and collecting data from different tools and combining everything afterward. The data is everywhere and analyzing it still depends heavily on human effort. So there is almost no automation. For example, Android does offer Puppeteer, and it's great framework, but it's not lightweight. It's complex, heavy to run all time, and not good fit for embedded devices or common Linux platforms. So Guido is a self-contained open source performance analysis toolkit designed especially for embedded and custom Linux platforms. It packages a broad set of capabilities into a single tool with 183 built-in commands covering monitoring, tracing, profiling, and various utility functions. Guider works across the entire stack from system-level metrics down to function level and even instruction-level analysis. It leverages existing kernel infrastructure such as ftrace, atrace, ptrace, kproof, uproof, dwarf, debug file system, and proc file system, but wraps them with a unified and easy-to-use interface. One of the core design goals is minimal dependency. It runs on Android, Azure, Tigen, WebOS, and a wide range of custom Linux distros without requiring heavy runtime libraries or external services. This makes it suitable for constrained embedded environments where adding large components is simply not practical. Guider provides both command line interfaces for direct usage and a remote API layer over TCP or Unix domain sockets. The protocol is intentionally simple, just JSON over sockets, which makes it easy for apps or external tools to control Guider. And importantly, the remote APIs are designed for multi-process and multi-device scenarios, enabling automated systems and CI tools or in-built labs to run profiling and monitoring workflows at a scale. Guider provides a real-time resource monitoring feature similar to Linux Top, but significantly more comprehensive. It continuously gathers a wide range of system performance metrics from proc file system, debug file system, sysfile system, and pub syscalls, and kernel exposed files with minimal overhead. So as you can see in the right-hand image, Guider shows all major system resources or task statistics in a single view. CPU, memory, I/O, scheduler events, and interrupts, PSI, and thermal information. Everything is updated in real time. And when certain statistics become abnormal, Guider automatically highlights them with color, and making anomalies immediately noticeable without requiring deep inspection. Everything shown on the screen can also be saved as output files. Guider stores all collected metrics in a structured format, enabling later replay or analysis. Using these stored files, Guider can generate visualized graphs like the ones shown on the left. It supports stacked graphs, rate chart, and various time series visualization that makes it easy to interpret long-term monitoring data. This combination of real-time analysis and post-capture visualization makes Guider particularly efficient for diagnosing issues that occur over long durations or only user-specific, hard-to-reproduce conditions. Guider also provides a function-level monitoring engine built on ptrace. This means Guider can monitor any Linux thread, including Android, without needing special system libraries, external SDKs, or instrumentation tools. Because it uses ptrace, the overhead is a little bit higher than kernel tracing, but the big advantage is that it works anywhere, even on very limited embedded systems or very old systems. Guider also includes its own dwarf parser, so it also can read symbols, line information, and stack frames by itself without depending on external tools or libraries. And it can analyze JIT-compiled function, including Android ART, Python, Node.js using self-implemented interpreter parser. On the left side of the slide, you can see how Guider samples thread and show functions it spends the most time in, along with their full course text. This data can be saved and later converted into a frame graph, like the one on the right, using Guider's built-in converter. In addition to sampling, Guider supports breakpoint-based monitoring. This lets you count exactly times a specific function is called, which is helpful for checking unexpected behavior or confirming performance regulations. Overall, these features give developers deep insight into how each thread behaves at the function level, even on embedded devices with very limited resources. So, Guider also expands its ptrace engine to provide breakpoint-based tracing systems. So this allows us to trace the actual function call flow of any tasks at runtime. In the top left image, you can see Guider displaying a sequence of a specific task. Whenever a function of interest is called, Guider can extract and show its parameters, register values, or even the contents of a specific memory address. There is a dedicated set of tracing commands for this, all documented in the Guider help system. On the right side, the two images showing something more unique. Guider can trace not only native C, C++ functions, but also languages that run on the interpreters or JIT compiler, such as AS and Python. Even though these runtimes do not expose function calls through traditional kernel mechanisms, so Guider can still track their execution path using a combination of breakpoints and symbol resolution. Guider also works closely with ptrace, which let us analyze system-wide behavior, things like syscalls, file I/O, and schedule activity, and many other kernel events. These are areas where user space tracing alone isn't enough, and ptrace gives us very detailed and low overhead information directly from the kernel. So this feature is often used together with other profiling tools, but it comes especially powerful when you need to connect system-wide kernel activity with application-level problems. So Guider also provides a fully automated real-time monitoring framework. Instead of manually checking system metrics or waiting for issues to appear, Guider continuously watches system behavior from boot and reacts automatically. At the core of this mechanism is a JSON-based configuration, as shown in the table on the right. Each entry defines a specific monitoring item, its threshold value, and the commands to run when that threshold is exceeded. This makes the system highly flexible and easy to adapt to different devices or performance targets. The automation workflow consists of 4 main stages. First, Guider loads the configuration file. Inside this file are threshold definitions for each monitoring item, CPU usage, memory, I/O latency, thermal limits, and many others. Second, Guider interprets these rules and begin monitoring the required kernel or user-level metrics continuously. This happens in the background with minimal overhead. And third, when any metrics crosses its defined threshold, Guider automatically executes the associated handling commands. This can range from logging, taking snapshots, and running analysis tools, or even triggering application-level recovery actions. And finally, in the fourth stage, Guider generates a structured report based on all collected traces and metrics. This report includes the data needed to diagnose all issues, runtime statistics, and flame graph, and historical traces, and resource summaries without requiring any manual intervention. This end-to-end automation allows system to detect, capture, and analysis performance anomalies as they happen, even in long-running embedded environments where issues are infrequent or hard to reproduce. In addition, the table in the upper right corner shows the items used to be defined thresholds. Each item can have threshold configured at the system level or for specific tasks or devices. So you can also define which commands should be executed automatically when each threshold condition is met. In the example, the save command generates the report file, and additional commands is shown for performing function profiling. So the upper side section shows the definitions of the commands available in the configuration file. By defining these commands in advance, they can be directly reused inside the configuration file. The lower right section shows examples of automatically generated report files. Each report follows the consistent naming scheme, allowing users to easily identify when and under which conditions each report file is generated automatically. So this page shows the contents of each report file. A variety of system information is included by default. As shown in the bottom right figure, the collected intervals provide time segmented usage data for system level or task device level resources and stats. In addition, as seen in the bottom right figure, each time interval includes detailed information about the corresponding state. Finally, each report file can be converted into a visualization, such as the stacked line graph shown in the top right. This visualization method is highly effective for analyzing reports generated from long-term stored data. Next, this page shows the visualization feature that merges previously generated report files with system log files. Using Kernel, Journal, ftrace, D8, or Android logs, Guider can display events directly on the line graph. By using Guider's command options, you can filter logs that match specific keyword, and these logs entire are visualized among with timeline with their corresponding timestamp. Automatically generated report files can accumulate over time, and once they are collected from devices to the server, analyzing them one by one becomes impractical. So this page introduced the bulk analysis figure, which allows large volumes of report files to be analyzed. On the far right, you can see a table that summarizes task group ranking per resource across many report files. Using this table, you can easily understand the threshold statistics of each task group and the overall frequency of occurrence for each resource. Additionally, parameters such as the number of tasks in each group, threshold values, and average values can all be tuned. With this feature, you can quickly identify which task combinations are primarily responsible for issues related to the specific resources or statistics across a large fleet of devices on the server side. As introduced earlier, Guider run continuously from the moment system boot.
Can you hear me? There's just 1 minute left. I think it might be good to open it for discussion, if possible.
Yeah. It's okay.
Does anyone have any questions?
What is your profile I have one question. What do you provide for block device and networking device?
Excuse me? I couldn't hear well.
Sorry, what do you profile for the storage device and the networking device?
For storage and
Because you
network.
mentioned in the target, you mentioned there could be block device and networking device.
Yes, right. Just gather profile system data for networking and storage data.
It's for the bandwidth or any other information.
Could you explain more?
What information does a guider collect for the, for example, networking device? Is it bandwidth or any other information?
There are some stats in profile system. For each TCP or UDP or Unix domain sockets about. So guider collects all stats in profile system.
Also, it's per connection stats.
Connection? That's right, yeah. Including connection, including connection, including connection and network bandwidth and storage usage and busy stats and some usage and free stats like this one.
Thank you.
Yeah.
Any last question? Thank you very much for the presentation.
Yeah.
Valeu aí. Parabéns. Very much. It was pretty good. It's there. Right here. Here's my box. Anyone there? You want to go with us? The Meta office for lunch?
Oh,
Just across the corner.
okay. Can I join them? Cool.
No, USB. No way. Yes. I thought you were like virtualization. There's a presentation. Do we need to close it? Or no. It's going to, there will be another session. Actually, make no way. Nice. Okay, the way Brenda's voice went down, disappointment was sudden. We did that one idea, right? How much?
So we run multiple in the kernel concurrently without virtualization. Yeah.
Another, I like unique kernels.
Yeah.
That's like okay, unique kernel, multi-kernel.
Yeah.
So we actually typically get interviews. Your multi-kernel runs on the.
That's okay. No, not at all.
I'm joking.
Because unique kernel still build on virtualization. Yeah, article different. So you wish to which unique kernel do you want? Unicorn.
Unicorn.
Oh. Yeah, because there are multiple ones.
What's the OS6 or OS3 stuff?
I understand.
Unicorn. Based. That looks like research. Like, too quick. I was just talking about research. It's like actually super through research to happen before I can do the next step. So I'm used to it. What's the benefit of just for resource sharing?
It's the opposite. Resource optimization.
That's what you guys. That's what.
Yeah. Oh.
That's so much.
So the compare with virtual machine, I don't have virtualization overhead, and I don't use virtualization step. And compare with the container, I don't have no issue. Yeah, and I have better performance. It's kind of easy.
Cause is
Exactly. Yes, and same for other data resources. Yes.
What is attached to?
Exactly.
That's and now
对，这样，咱俩目标一样，而且还得自动化。那当然必须。对。你这个最终的产出是啥？就是你看到这个你这个结果是 怎么知道你出来？我的意思是，那你从这儿到这儿，你得做了一个优化，做了什么？哦，所以你是调的菜。哦，你直接用原物。
太老了，没有我现在有的目标是，所以我当时问嘛，就是他这个就是目的是在内部的看到，的确他的一个原因是因为他说他没有帮助这个监控 networking 性质的一点，或者监控性的一点，大部分都造成了效果。就是你在线上我说可以。
不，他的线上是相册。
对，对，后来才明白，后来才明白。但是当时讲了几个理由，他不这样做，你必须要去了解当时
所以就是你说的，你的模板你是最终手写。你说的啊。
然后我不拿 VPN 可以去给特定的仓库去放了东西，不放的时候，你看看，哎，我也设置了，但如果没设置，会不会正常路径？会影响你的路径性呢？你就说带的这个 isolation 隔离，我有1000个流量，1000个消费者，我只需要监控1个消费者。我正常如果花一个 VPN，或者一些固定上，那你就是大家都是我的同样流量，对吧？那这个点，你要去监控什么监控权、USBT，是你在 QX 那个游戏大家都会受到影响，但是因为它在那个时候，它就会任何的东西做一个判断，往点上，它就会有很多东西，这个如果设置高级的设置这个 flag，就意味着我们要注意 flag。它就会跑另外一个东西去，然后你混合在另外一个东西上，这样子凡是普通的流量就不需要去 trace 的，它不仅是一个 else 你去做的是这样子，所以啊，要去监控是这样子，所以你只要监控这一块，你就能避免到对普通流量的任何影响，一点都不影响。所以我当时我还是蛮推荐的，我还没想到你有这种东西我想做的事。
我想做的是自动化。就是你比如说，你把你采集的这些数据拿过来，然后假设它有一个工具能把 kernel 这些参数自动调，这个是我想要的自动。
对，但是这里面会牵扯很多工作。那为什么？这个是
它要是
大事情，
它要是一个简单的事儿，我就不拿出来了。
对，它并不是说什么，我觉得完全说什么搞几个算法调节 U，其实对，你要去能有观测能力，然后我调完之后也有观测对比能力，然后我能看我的效果到底，因为没有好的观测能力的话，对吧？你就因为你调的时候，你这个结果到底够不够准？对，所以我为什么现在基本上这块价格不管了，现在我进入在切。
对，很好。我觉得那可以聊聊，我觉得。对啊，这个 Mali kernel 肯定有用啊，因为 Mali kernel 它是每个 kernel 起不同的。这样的话，我这个 kernel 如果能把优化只针对这一个，它就是最好。对，有用。它不就和立马匹配的？
如果我给每个 container 的每个 container 里面它也有不同的东西，那我比如 container 里面是有去过。
是，但是你 container 有些东西它是可以开的对，我的这个是全可以的。你这个 kernel 该怎么把握这个？
可以做完各个地方。
完全可以，你编不同的 kernel。就是我甚至想，比如说是你拿过来这个，我重新给你编一个不同的 kernel。 这是最优的。这两个要的哦，只受限于你的应用。
它其实就是个隔离性更强的一个。哦，那这个设计就很有意义了。你推销的对，都不知道这个事情调不了，一调全部。对，全部都是一条。啊，有意思了。对啊，明白了。明白了。对。还是说，你要是想去，反正我觉得我这个路子，我觉得还是可行的。你可以去，对，这个大方向不错，但是看法。对，怎么做？对，相对上来说，要用地域。
lovely room. It's a lovely room. It's okay. So happy with your system routine?
Yeah, people showed up.
That is your bar? I think you could.
Well, there's several bars. Like people show up and people interact. That's sort of the important part.
And I have to say, I mean, I was only there for like the first three sessions. I loved how much actually there was. I was a bit scared at the beginning, then they all started like doing like the slides, doing the talk and so on.
Yeah.
I was like, okay, this is not what it should be, right?
It's really hard. I mean, there's two parts, right? You need someone who's really trying to engage the audience, and then you need an audience that's engaging.
But also you need someone who actually has questions. Because often enough, I mean, there's a lot of these submissions I got for embedded. I was also like, yeah, I want to talk about that. No, that's good, but that's not the case here. That's like, you come here if you have like specific questions, and you are the person who needs to make sure that the key stakeholders you're having in mind show up as well.
I know, it's hard in build
It's very
systems.
difficult.
Yeah, it's really hard in build systems. Because a lot of people that, I mean, build systems are classic plumbing.
Yeah. But I mean, you had the guy from that was there, the people from there. So that was all actually good enough, because before it was very.
I know, I had to yell at, I had to yell at people.
Yeah.
Yes. We know what to do, but we need to talk to these other people, and they need to talk to us, and it's getting that culture of, because everyone in distribution will start signing. So,
I mean, you saw that. I just smiled about that the guy. I don't know. Like talking about like, you need the Microsoft keys in there. Or you don't. No, but you need that for all the other things. Yeah, for use case, I fully agree. You need that. That is like your number one use case. But if you have full control of the whole thing, and you know your own program, you know your own keys and everything, you are the one who can do all that.
Yeah, no, I mean, I think it's interesting to see their mentality, because they're sort of trying to get into embedded spaces, and you're just sort of laughing at them. It's like, what's transmitting? Yeah, but I mean, you know what I mean? It's like you come from one world. I mean, for going into desktop distros is really bad for us, because there's a lot of stuff we don't understand.
I mean, I looked at let me have all the stuff in Samsung and Python and so on. We started from the other side, right? A really small media scope of things and so on. But then they said to like, oh, but you also want to go on the desktop.
Yeah.
So, but before they taught us, oh no, you need to shrink down window management functionality. So you started, for example, the graphics part, the library. So it has all the best bits that you wanted, right? But they also, we need to shrink it down. It need to be like very simple window, so full screen, that's all. And then they come back, oh no, we need multiple windows and everything like that.
I should put the sponsor slide up. Have you been briefed on how this works?
Yeah, I've been there this morning from Stephen. I think it's, basically the same as every year. So how did you decide how to hand out these speaker gifts?
I don't know. I think I have 2 bowls.
You have 2 bowls.
Yeah.
And 3.
Because I don't think either of my co-hosts want them. What am I looking at?
If you scroll down, I think that is the. Maybe you need to refresh.
Yeah.
There you go. Join session.
Yeah, okay. Refresh again.
You never know.
Yeah, I don't know what to do. I only got 2.
Why is that?
I don't know. I think there was a decoupling between the people handing out the bowls.
Yeah.
And the people, I mean, because Steve had to cover, I had to ask him.
Okay, now because for me, she handed me out like 3 bowls and that.
Maybe they had extras by the time you picked yours.
I have no idea. I mean, at one time it was an umbrella or something, and nobody really wanted to have it. It was like, I think we ended up with like throwing them away because like none of the speakers, none of the organizers wanted. It was like, meh. These ones are at least okay. So, if you like join the audio,
Don't
just
join the audio.
yeah. So because that is like the
Yeah,
piping that
audio
in.
is completely separate from this.
Okay.
I mean, these look like they might be useful. I'm going to open yours real quick. I have mine in my bag.
They look nice. I mean, they're not looking that. I mean, normally we'd expect like the handcrafted stuff in Japan and so on. It's more about the branding, the Linux Plumber thing being put on that one. So, yeah, that looks nice.
Yeah.
The rest is like, no, that's okay.
I mean, so they're annoying because they won't go in the dishwasher.
Yeah, I agree. That's my number one thing. If I buy this anything, it need to fit. It need to survive.
It needs to survive the dishwasher. But they might be nice for special occasions.
I think it's more like for, not for anything food related or something, but more like putting your keys or something.
Yeah, well, I think it's designed to sort of, you put rice in it and then the food on it.
Okay, let's see if I can upload this.
Yeah, I don't think we got our Chromebook until 5 minutes before we started. So we were kind of nervous.
I mean, being the first session of the morning is always funny.
All right, I've done my part. I put the sponsor slide up that you're supposed to thank your sponsors.
Now I need also thank you for like setting up this slide.
Yeah.
There's a lot of thank yous going on.
Yeah.
Where do I see if I'm a rectangle or a circle?
I'm half tempted to go take the afternoon.
Good. Good. Oh, so they have all the old slides here.
I'm gonna go sit in the back of the room.
Go to sleep.
See what my schedule for the next 2.5 days.
So my schedule tomorrow is LPC, and Saturday I'm going on the Shinkansen bullet train all the way up to the north, Hokkaido. And on Sunday I will stand on a snowboard, go down the, hopefully, we'll see about that. But, and then on Monday I fly to home. So it's one day, but I wanted to do that. I was
So Brian Mass, do you know Brian Mass?
Yeah, he's actually talking to you in the.
Yeah, so he's going skiing as well.
Oh,
and he asked me if I wanted to go, and I just had a lot going on, doing research, and I would have had to bump.
And now you're regretting it.
Yeah.
Because I remember you always go skiing around Austin time, right?
March usually. But yeah, it was, I mean, the problem to go skiing is I would have had to carry extra clothes.
Yeah, so I only mean you can rent everything there.
I know, but just the clothes I would wear.
Yeah, but you can even rent that.
Oh, okay.
They have like everything there. So I brought, to be fair, but I also brought my pants.
Yeah.
And the normal jacket I have, I used like for snowboarding. So that's fine. But you could rent everything there. So I pay. So there's a really nice. I can't pronounce it. Anyway, there's one really great ski resort over there, but there you would need to have like an additional 2 hours of train ride or so. I go directly to Sapporo. You can go by train, and they have like a smaller resort next to the city. There you can just go. There's a bus goes there, like it picks you up at the hotel or something. Goes the bus, like 20-minute bus ride, then go there, everything's rented, get a ticket and everything, and I think I pay for everything like 120 or so. That's like ski ticket, rental, bus, and so on. So it's like
I mean, I have a pass that works at some of the resorts. I mean, I just.
Well, you're considering going? Or?
No.
Because that would be like.
I mean, so the other things, I've never been to Japan before, so I've never been to Tokyo, so there's plenty of things I should look at in Tokyo.
I agree.
Right, there's plenty of stuff to look at. And, you know.
I mean, for me, it's the second time, so I still would need a lot more time in Tokyo, but I so heavily wanted to, first of all, ride the Shinkansen.
Yeah.
And go snowboarding in Kaido. I was like, okay, I need to mix these two together, and so I was like, yeah.
I went skiing at the end of October in Colorado because I had to go out there and tinker with a condo we have out there.
I haven't been snowboarding for like 5 or 6 years.
Oh, wow. Well, that's going to be fun.
Nice way of putting it, right? I will go the bunny slopes.
Yeah.
I don't know. It didn't really work out all the time, so yeah.
Yeah.
So that was very high on my list when it was clear for me that I will go here. That was like, I want to figure that out. But to be fair, I just today bought the tickets for the train because it's difficult to do that online. It's like, I don't know, it's very hard to do that if you're not on speech. You need to know all the details about that. So I went to a ticket office to do that. And I was actually, when I come here, I was wondering if I really do that or not because of the earthquake being in the northeast. Yeah. It was in that direction. So I wasn't sure like it's the best idea, but they put down tsunami warnings and everything. There might be some more quakes coming, but maybe not that high. So I was like, okay, let's try now. And actually, there's been a lot of like thought put into how to make sure that the bullet trains are not going off rails with an earthquake coming and so on, because that would be very inconvenient to have.
Yeah, I was actually awake when the earthquake happened.
Oh, you have been here already? Ah, okay.
It was very weird.
Okay, I can imagine.
It's like my building starts to sway.
Okay, and now imagine how it must be in the north, right? Where it was really like.
Apparently, I'm on the 12th floor, and apparently if you're lower to the ground, it's more, because the building sort of absorbs some of the shock.
Mm-hmm.
And somebody told me that, and I started to think about it, and I realized that the lower floors, things might have been a bit more jumpy. And like there was weird noises in the building. I mean, it was very unsettling.
I mean, especially if you come, I mean, for example, I have never experienced one. So I wouldn't even know how, I mean, if you expect it, that's one thing. But if you're not, it's like, what the fuck is going on? How should I behave, actually?
I've done a small one in California a long time ago.
So is California prone to earthquakes or? Yes. It is, okay.
Yeah, basically at some point, California's going to fall off. I mean, if
you mean it falls off the flat earth, or?
Well,
no, I just joke about the falling off part. So.
Yeah. There's the major fault goes through Los Angeles and San Francisco.
Okay.
It's actually a problem.
Gosh, Kasim, so much text. Okay. In any case, the slides are uploaded. That's looking good. So good. That's all. I'm done. I only need to say, these are the sponsors. Please be nice. Use a good contact. And now, I have to throw around the microphone.
Yeah.
Jan said he will do most of the note taking and so on. He will make it here. So.
Yeah. I mean, we had a guy show up for Joshua Watts' SBOM talk who was interested from a confidential computing kind of view. And so basically, Joshua's got to go to his talk at noon tomorrow. I mean, that for me is a win.
Yeah, it is.
Right. You know, and having Leonard show up and talk about, you know, how.
Did you talk about this in the first session from Frank? He didn't say anything. I think
No, I think he was hanging around for Bean's talk, where Bean was
for the
talking about saving
the
shit.
system config, something.
Yeah, and how do you make config persist across upgrades and crap like that?
Yeah, I need to talk to Bean about that, because he might want that and might as well.
Yeah, no, I mean.
Lightspeed is like far away.
Yeah, I mean, that for me is the win, is people from different silos realizing they have to talk to other people.
Yeah.
Realize that, you know, it's like the confidential commuting people care about SMART late adjacent stuff.
There are so many things that are overlapping, right? You, for example, CCA. So you have like, they want to have like something small image that can securely boot. That sounds somehow familiar,
exactly
right? So you put it like that. So it's like, yeah, there are different mechanisms for that.
Yeah.
But in general, it's like the same concepts.
We worry about a lot of the same things in different ways.
I mean, you don't have like all the infusion and finding server stuff and so on. We don't have that.
Yeah. But there are a lot of people about understanding what exactly they're securely booting.
Oh, I need to talk to some of my colleagues. They do a lot of CCA stuff, but I have no idea on that one.
Yeah, that is so much crap. I can't figure any of it out. All I know is a little bit about a lot of things.
Sometimes that's enough. Sometimes that's actually the best, because you know a broader range of things, then maybe drill down if you need to.
Or more to the point, I know who to. You need to talk to this person.
I mean, it depends, right? If you're more like in a position where you make sure things are moving along, but if you want to learn, then at some point you need to learn. But
I mean, my current
orchestrating, then
I mean, my hobby project at the moment is having GitLab CI run LabGrid jobs.
So that's a hobby project.
Yeah.
That's fun.
That's because it's, well, it's useful.
Okay. Yeah.
You know, I'm basically running the GNU Radio self-tests on a Zinc board. So I make a change to the layer stack.
Then like LabGrid is what kind of hardware to run on the board? Or is it directly? So how have you given any like tests set up?
I mean, I've got a Raspberry Pi that's my controller.
Okay, so that's the
exporter.
Okay, so that's the, then we have like just hot wires the cables to the board.
Yeah.
And that device on.
Yeah, so I have a ZCU 104. I think I've got another Xilinx board, and I want to get a Beagle 5 Fire once I figure out how to reset it. And
yeah, that's I mean that's what I'm asking, right? Because that's the annoying part, like how do you like make sure that the device is actually restarting.
yeah, I mean the ZCU 104 is pretty easy because I can just cycle power on it. And I can reflash it with an SD mux.
Yeah, but I mean, again, at that point you have an external hardware component that you might already like doing that.
Yeah, I mean all of that's hanging off this Raspberry Pi that I had lying around, so that I don't have to depend on my desktop computer working.
Yeah.
So that's pretty cool.
Now, normally Ian is traveling around with LA. Did he show it already, or?
His test thing. I think I
He's always
saw
traveling
it.
around with that one.
Yeah, I saw it in Amsterdam.
Yeah.
Yeah, very proud of that.
Like a lot of like printing for all the cases. So.
Yeah, when you got a 3D printer, every problem is solved by 3D printing something.
Not everything's in there just because you're a it doesn't work like that. I agree. I mean, and it has come a long way. I remember that together with Daniel, I looked into some 3D printing stuff. I mean, so here's the printer I was just going on for the ride. But that was like, we didn't start in Samsung, it must be like 2012. So it was like, we were talking about RepRap, right? Really like building your own printer basically from the starting point. But nowadays, like the quality is so amazing. If you see, like if you get one off the shelf, even not the highest priciest one or something, but something below that, and still really good quality, really like on the line. You barely can see all the different like layers going on top of it.
Yeah.
Yeah, my son was at some point. So he was at a kid's birthday party. The dad actually had a 3D printer, and he printed some toys and then to give the kids away. My son came back home like, we need to 3D print. And I was like, no, we don't. You was like really, he was arguing with me to get one. And I was the one who saying, like, I mean, the things I see.
Being an adult is hard.
Yes. Yes. I mean, I could buy one, couldn't put it somewhere, but the things, he would be just like going on nerves, like, oh, I want this, I want this, but he would not like go ahead and like, oh, how can I do that? But that would be good for me. If he would have like this inclination, that would be nice. I don't think that's I woke up at 4:30.
I got
Not bad. But
yeah,
I
I'm sort of stuck on the get up at 5. And I'm sort of every day I've been sleeping a little bit later, but it's going really slowly.
I mean, I only arrived yesterday, so
Yeah.
4:30. So I mean, I had 6 hours of sleep, so that was actually quite good. I just feel a bit exhausted, but not jet lag, so I'm good. But
Yeah. I mean, I'm sort of getting enough sleep, but it's not bad waking up then because I can get stuff done in the morning. But the problem is I get really tired at night.
Yeah, I'm wondering what I'm going to do after the session, if I go to the social event or not.
I don't want to go to the social event just because I see something other than the immediate neighborhood. And the one on Saturday, oh, you're going to miss that. Oh my God, you have to read the Google review for the venue.
Right, so good though.
Okay,
that was not sounding promising.
You can't eat architecture. Apparently it's a bit of a tourist trap. But apparently it's a spectacular building. And the guys like, go in, take a selfie.
Okay. I'm missing that anyway.
You're missing it anyway, yeah.
So send me a picture and then I will there.
I'll get a picture, yes, I'll get a picture.
And I'm good for that.
Apparently it's sort of a chain of restaurants and it was another location that was sort of inspired something seen in the Kill Bill as well.
Okay.
So it definitely sounds like a good place to go. And I suspect that a lot of his concerns won't really apply because we're really going as a social event, not as.
So catering would be completely.
So it really, well, no, I mean, it just doesn't, it's an explanation of that. We're not going to have fine dining. Look, Honda's gold and Toyota's only silver.
Oh. I'm not think that don't think that it's so well. Which is also gold. Is there no Panasonic?
There's no Panasonic.
Sony is also only gold.
The EVP?
Yeah, they're sponsoring quite a bit. I mean, well, they're always sponsoring Thanos. I mean, that's on track here.
Yeah. Oh, yeah. Okay. So they're on track.
I mean, I don't know how the deal is, right? I mean, is it like a conservation project or is it their own foundation?
I can't. I have to look. The Linux Foundation loves to shuffle money.
Yeah, that's the point, right? Because like Dr. is sponsoring this, and then it's always like, okay. I mean, it's good to get some branding out. I don't mind that, but it's always like if there's really the money they pay for it, I don't think so.
I go to some of those meetings.
Yeah.
Let's just say that at various times there's various levels of angst.
But on the other hand, even if it's not an explanation event, pretty sure there's like enough big companies backing them up, so they get money.
I mean, they got a track, so. They should
I mean,
have
the question is like, I mean, why they hopefully do not need to sponsor to get that, right? Hopefully it's on technical merits. I mean, to be fair, no, to be fair, I fully agree with you on like normal everything. I've seen enough there, but for LPC, at least the technical committee is completely out of the loop. So,
Yeah. Yeah, this is true. Yeah, knowing how the sausage.
Hi,
Whoa. Knowing how the sausage is.
That's scary. Someone off the office talking to us here.
Yeah.
Can you give me the Big Blue Button admin privileges?
Hi, Jan. Let me
Hi, Crofton.
see if I can. I hope you didn't hear us. We were warned about the hot mic stuff this morning.
Of course, I heard you.
Oh dear. So promote to moderator.
Yeah, that looks like it is working.
Now I actually get this the square and rectangle, the squares and circles. It's not the icons below. So if your name is a square, which is now, you should have like all the admin rights you need.
Yeah, looks like it. Did you upload the
Do you have,
presentation already?
It's already there. They're all sitting in there. I can switch them around. So that's just the default slide because you need to thank sponsors and code of conduct and so on, but everything else is in there. So for example, this one. Yes, do you have a Google Doc already for the notes? Or
No, I'll create one.
okay, cool. Because I think we should put that in the discussion channel. So how are you holding up? Like very early. I mean,
I feel jet lagged.
I guess you have been really tired when you joined the build systems MC, right?
I can't really hear you well if you're speaking in the hall without a microphone.
That's good, because we have been talking about you all the time. No, I just said you have been a lot more tired in the beginning for the micro conference for build system, right? Because that must be in like 2 a.m. for your time?
Yes. Had my alarm for 1:30.
Oh. That's something you never want to put your alarm on. So what I will do is like, I will start with like just 2 minutes or so. Welcome everybody, thanks to sponsors, remind about code of conduct. Make sure that everybody keeps in mind that that is about discussion and not about presentation. Yeah, that's basically all the notes I had. Anything from your side I should bring up? Oh, the notes actually, yeah. So if anyone wants to help with the notes, that should be something in the chat, a link to that.
I also put the link to the Google Docs in the shared notes in the BBB. But yeah.
Okay, cool.
At least in the previous session, there were not many people in the BBB.
Yeah, okay. So I have 3 speaker gifts we can hand out, basically some wooden bowls they handed out. I have no idea how to decide who to give them to. I mean, we have 6 speakers. We could go for the most interactive ones. I don't know.
Yeah, sounds good.
Okay, so let me try if I can decide based on that, and then we can see how to give it out. Oh, by the way, should I try to get a T-shirt for you or not?
I don't think so.
Okay, good, fair enough. Oh, they're there. So you can, oh, I can see. So they're streaming a big blue button, like one thing, and then I think there's also it's a meet dot. So that is just that is the schedule you're looking at. If you go to meet dot LPC dot events, that is a big blue button. There you can see all these sessions. You can join them and so on. I think there should also be some sort of like YouTube stream also. You uploaded all the slides already?
Oh, you have? Okay, that was what I was checking.
Yeah, no, I just did it. So just put it back to default for the sponsors and stuff like that.
Yes, that's the idea. Yeah. Okay. Yeah, I'm the. Sorry, Stefan. Mark.
Yeah, I think it's the same like every year, right? So yeah, I've been tomorrow this morning with Stephen with the session. So same sponsors, code of conduct, make sure discussion moves along.
Yeah, well,
speak into the mic, all the stuff.
Yeah, I was more thinking if there's like technical issues, ping me.
Okay.
That's kind of why I'm here. Is that anything goes wrong with BBB or something, then
let's hope nobody kills the sessions.
yeah. I think you shouldn't have permission.
But it sounded differently this morning. So it sounded more like everybody moderator has a chance to like kill the session, not only leading.
Right.
But I don't know. I mean, anyway. So
yeah, no, there were a lot of people who didn't have any permission at all.
Okay. No, for me it was a political point. So at least for Jan, I needed to code my host. I needed to make sure that he's actually getting moderator rights. But for me, it worked out.
Right. Okay. Yeah. No, there are a few people who got missed for whatever reason. So.
Okay.
Yeah. Anyway, as far as I'm not here, if there's anything needed. Hopefully not.
We'll let you know.
Yeah. So half the time it's the catch boxes breaking.
Oh, okay. Oh, is he the battery?
No, actually, that's the point. Yeah, get people to not make sure it doesn't like hit the wall or fall on the floor. I know it seems to be something like if it takes a big hit, then the power can get turned off.
Okay, because I remember, I don't know if it was Thomas or thing like the battery become loose.
Yeah, maybe so. I'm not sure exactly what it is, but it's when it hits or something that
I mean, that's the basic idea of this catwalk that actually can fall down.
Yeah. I think it's worse in some of the bigger rooms, and the smaller rooms that they're getting through with a bit more force. The smaller ones is not so bad. Yeah. I think there should be some regular mics if it fails.
So how would I figure out if the mic is not working?
It's supposed to get routed through the PA system.
Oh, okay, so if you don't hear that correctly, then
Yeah, and it's also for people in the room. If people must be speaking quietly, then.
Okay. Okay.
About yourself. Working openly something.
Hey, while you're waiting, can you guys hear me well?
Yes, we can.
Awesome. Okay. I'm the second speaker and I was having audio issues earlier. Saravana here, by the way.
Okay, hi, Stefan here. Yeah, we can hear you well. That's working fine. So the only thing I need to do when your session starts is make sure that you actually have the right to change the slides to go from one page to another. I can do that at that point.
Sounds good. Cool. Video is working too.
Oh, I thought this channels were per room rather than.
By the way, I sent an email to Jan or Han. I'm not sure what the right pronunciation is, but BBB was struggling to let people in. I was waiting for it to let me in for like, I don't know, 2 minutes.
Okay. Okay. Yeah, I don't think there's much you can do about it, but it's good to know. But it was it just like spinning? You need time to get to access, or is there anything else that is locked in? Because I mean, I tried from here and it worked directly. So
Okay, the
Yeah, I'm
join
also
session, once you
joined.
click that, the dot thing keeps spinning, like as if it's, and then before it asks for you to, like, if you want to listen only or mic thing, before it got there, it was waiting for a long time.
Yeah, from our side, I don't think we can really do much about it. That's hosted
But did it take
centrally
so long
by
for you as
the
well,
organization. Sorry?
Did it also take that long for you as well, or?
No, it worked fine, but I joined, I think, 20 minutes ago.
Yeah. So I joined before lunch on some other session. I didn't have any problems. I'm just kind of letting you know in case you can do something or whatever. I'm already in, so I'm not worried. But
Yeah. Not the end of the world, but so I think just one. I don't know if they changed it because it is already fairly quick. Yeah.
What makes you think it's their one?
So
So what's that you're showing me? Sorry.
okay, so
Yes. Yeah. Okay. And I think you just update that to put your. Yeah, that's editable. That's all good. Yeah. Start typing. Okay.
maybe okay, right for it.
Okay. But yeah, let's link to the things that's easier of those for me.
Well, I think you can know. I mean, you measure it. That's one of the matters. And that's coming. So
What makes you think it's, yeah, what makes you think it's a different channel? That's, what the same thing that.
Jan? Jan?
Yeah. Yes.
So the channel, the integrated matrix channel in the.
Can you go to the mic? It's hard to understand. Or take the throw thing.
Hi, we are trying to here locally try to get the integration thing fixed. So, how do you find out that it's not pointing to the embedded channel? Because you looked there and nothing showed up there, or?
Yes, and I looked in the browser console where it's showed the metrics name.
Okay.
The raw
room
name, and
we
joined
are
it
not
on
sure
from
if
the
we
other
can
side.
get that. Okay, so we're not sure if we can get that fixed here, but we can see.
I'll need to double check with the rest of the people, but I had thought this was just a channel for the room, not for the miniconf.
But I mean, it is pointing to a different minicom channel, so it
Yeah, I didn't
seems
realize there
like,
were minicom channels.
It's fine with me. I can monitor both sides, so it might be confusing for others.
We should probably fix it.
Okay, we're trying to look into it. Please have a look on the other one for now, and then we can see if we can get that fixed.
This is
Yeah. Like the last week. Okay, sounds good.
You didn't fix anything since yesterday?
Yeah, I just want to double check.
Yeah, no problem.
Oh, yeah, sure. Sure, absolutely.
Already.
I wish there was more vegetables, but they plant slowly grilled in meat fat.
Okay, so we are right on time. I hope everybody had a good lunchtime, relaxed a little bit, no jet lag anymore. Welcome. So this is the embedded IoT session we're having here. So it's like, I think the edition number 5 or 6. We started mostly initially in the initial years with like concentrating on the IoT part, a bit more on Arthur side and so on. But we, over the last years, we moved into embedded as well to make sure that we have a good area where we can actually discuss things that are interesting for many people, but only a few like really work on that. So we want to have like a common ground here to like figure out what's going on in the kernel and all the plumbing around that. That is like making problems for us at the beginning. So first of all, I want to thank all the sponsors we're having. So without them, this would not be possible to have this event here. So a lot of thanks goes to them. We have a code of conduct here for the event. So please be friendly to each other. In general, just be nice to each other. So please apply with the code of conduct here. One quick reminder for you guys, also for the speakers, this is discussion. You can come here, you can like have a deck of slides that can be a presentation, but at any point, if there comes questions or something, you stop and you talk with the people, and that is the main idea here. So whenever I talk to the speakers or so, I told them like maybe bring only like 5 slides or something, bring your questions to the audience, because as Stephen put it in the morning session, it's very clear. You come here as a speaker to get the input from the outside, from the community here, and not the other way around. So it's not a session where I transfer my knowledge to you, but it's the other way around. So just keep that in mind for the session. So if you have questions, just go ahead, interrupt the speaker at any point, and they should cope with that and work with that. So the mics are here, they're recording all the time. So when we have the breakout session later, just be sure that it's streamed into the internet all the time. So whatever you say here will be transmitted outside. Just a reminder about that. The camera there will follow the catch box. So whenever you say something in the catch box, the camera will also be pointing towards you. Yeah, that is basically. So I'm Stefan. Jan is my co-host. He's not here at the moment. Sadly, he couldn't join us. So he's just here remotely. There you go. That's the voice of God, basically coming out of the microphone. So, yeah, thanks a lot all for coming in. And with that, we have 6 sessions waiting for us. So I will start with the first one. Akhilesh, please join me here. So let me change that to the first session. There you go. And then you should go back and forth with the cursor slides. That should be perfect. Thank you.
All right. Hi, everyone. My name is Akhilesh. I work on Android systems and kernel team. I'm here today with Takaya, who work on Chrome OS and Android. So we've been driving a prefetch project together. So this talk is primarily focused on how we have improved Android boot time performance using prefetch. The talk will focus on some of the performance gains we have observed, but the core focus would be on some of the challenges and learnings we have had during the adoption of this project. So that will open up the forum for discussions. So quick recap. So prefetch is not something new. This project is not something new. Historically, it was called UReadHead on Chrome OS. This was deployed on Chrome OS successfully, and we had observed about 20% boot time improvement on Chrome OS. So the core idea of prefetch is two aspects. On Chrome OS as well as on Android, the root partition is mounted as read-only. So which means that during every boot, the IO pattern is deterministic. IO pattern is deterministic. So taking that as an advantage, we have two steps in prefetch. One is the recording step, and another is the replay step. So in recording, we use the static trace point called file map add to page cache, wherein all the disk IO activities which goes in, whenever the page is inserted to the page cache, we intercept that and we record all those things into a pack file, which is primarily a metadata file. So that is kind of determining all the IO patterns during the entire cycle of the boot. So this happens once. And during the subsequent cycle, we have the replay phase wherein we read the pack file metadata and then replay all the IOs upfront, so that the idea is that the processes which are IO bottlenecked are directly gets a page cache hit instead of going all the way to the disk activity. That's the context and the overview of what this project is all about. So we took this concept and we have adopted this to Android. In the Android boot phase, it is slightly different compared to Chrome OS or any other Debian OSs. For instance, as you see here, the boot cycle in Android is split into multiple phases. For instance, in the early init, we first mount all the read-only partitions. Then in the post-FS stage, we mount the slash data, which is the read-write partition. And then subsequent phases, we spin up all the native platform services or hardware abstraction layer services, which are critical platform services. So each of these steps are sequential in nature, and every step has a deterministic IO pattern. So on Pixel device, we observed that during the entire cycle of the boot, we read about 1 to 1.2 GB of data just from read-only file systems during the entire cycle of the boot. One important thing which we have observed is also that the boot time varies significantly across form factors. For instance, on Pixel devices, we have about 10 to 12 seconds, whereas on watches, it takes about 40 plus odd seconds, whereas on other Android TVs, it takes about 15 plus seconds. So there are various reasons for this, because, for instance, some are CPU-bound bottleneck. On watches, we just have 4 cores and with 2 gigabytes RAM. So there are, and also every OEM and vendors have their own hooks to spin up services which are not part of platform services. So there is no one-size-fits-all solution to take the prefetch project and adapt it to all. So with that in mind, we did the first phase of adoption in Android. So on Pixel Watch and on Android TVs, we did see about 6 to 8% improvement. So the concept is still the same. The prefetch runs as a daemon, and which is written in Rust. We are trying to evaluate to adopt this to other verticals. So here is a quick Perfetto trace comparing with and without prefetch. So as you see here, system server is one of the core critical system processes, platform process. This is one slice of the boot, which is about 315 odd milliseconds. So you can clearly see all these orange slices. Those are disk I/O. So about 80% of the entire runtime is bottlenecked by the I/O activity here, which is about 215 milliseconds or so. So with prefetch, the prefetch daemon runs upfront in the boot phase to bring in all the pages into the page cache. So with that being said, with prefetch, as you see, there is absolutely no disk activity at all. It's just the CPU bound. So that's the Perfetto trace. So yeah, that's all. What happened? Yeah, it's lagging. So that all sounds good. Now, these are the challenges. I think this is something which we want to discuss further and have some inputs here. So the first thing is we are using the static trace point file map at the page cache, wherein we are tracking the IO activity where the pages are getting inserted to the page cache. But the problem is that if the pages were already in the page cache, then those pages will be missed for recording purposes. So if we miss those pages which are already in page cache, then we wouldn't be able to replay those pages in the subsequent boot cycle. That's one problem we have seen. The second most important problem is when to exactly run the recording phase. Since the read-only partitions are mounted as, since the partitions are rootfs is mounted as read-only, whenever the rootfs partition is updated, which happens on OTA, that is over-the-air update, we'll have to run the recording post-OTA boot. The problem is that post-OTA boot, we also have so many other one-off services which run, which will distort the entire boot time, because post-OTA boot time is about 30 to 40% more than the actual regular boot time. So when we run the recording phase during the post-OTA boot, although we may get the IO pattern, we may not be able to run those exact replay as expected. So
sorry, Akhilesh. Is there, I mean, how device specific is that? Is that something you can record and ship with the OTA? So if you have like a gold device setup or something like that, where you do that when you're in your testing and then you ship it with the OTA and you don't have this kind of problem and then you don't need to record it at all on the custom devices, for example.
That's a good point. So that's the offline recording mechanism. We haven't explored that per se, but that is something which is on the horizon to see that we can run that in the lab experiment, pre-ship it with the OTA and send it out. That's one potential solution which we are looking at. Yeah. So that's the second issue. The third issue is the memory pressure. Now, what happens is that on low mem devices like Pixel Watch, we have about 2 gigabytes of RAM. Now, when we are doing the replay at very early stage in the boot, right, we are just going to do a burst of IO activity and get almost like 1 gigabytes of data into page cache RAM. Now, all these pages will be in LRU unreferenced. When we have a memory pressure, we notice that case of daemon will kick out all these pages, and these pages will just get evicted out. So it's just that then there will be a contention between the actual application which is running to do the disk IO and the prefetch daemon which is also doing the replay. So there is this IO contention as well. So this is significantly problematic in the cases where we have a long duration of boot, like 30 to 40 odd seconds, wherein prefetch daemon can finish off in like 3-4 seconds to bring all the data into the page cache. But then there is no way to tell that those pages have to be resident in memory. I mean, we cannot mlog those pages for a duration of the boot. So that's another challenges which we have noticed. And the last thing here is the redundant record phase. So what exactly is, so when the whole idea of running the recording is that when the IO pattern changes, we'll have to rerun the recording to make sure that we capture the new IO pattern. So this happens whenever there is an OTA update, right? But in reality, not all files have changed, meaning that between two builds, the IO pattern might be consistent. So running the recording is slightly expensive. It takes about 2 to 3% because we are consistently enabling the hooks of the static trace points. So somehow we'll have to figure out if we can continuously run both the recording and replay together to see that what files have actually changed and what files have been consistent between the two builds. So having said that, so these are the potential solutions which we are exploring right now. One is on 6.12 kernel, there are 3 new static trace points which have been added, wherein instead of monitoring the disk IO pattern, we should be monitoring the memory access pattern, not exactly memory, it's just the IO access pattern. So meaning that whenever the application maps the pages into the process address space, we should be able to see whether the pages have been referenced or not. So with these new trace points, even though if the pages are in the page cache, we should be able to record them and then replay them. So irrespective of whether it's a disk IO or not. So we have explored this for Chrome OS, and it is promising. It shows about 3% improvements in boot time, but we haven't investigated further on Android, and that is something which is on our horizon to explore further. The second aspect is, as I mentioned, instead of doing the entire burst of IO activity upfront and bringing in all the pages, we can take advantage of different stages of the Android boot, wherein the idea here is that we split the entire pack file into multiple stages of the boot, and then just bring in the working set pages to the memory as and when required. For instance, as we see here, the last final step of the Android, which is called the boot phase, is a significant IO activity. So instead of bringing all those pages upfront at the first second, we can wait and just get those working set pages at the n-1 or n-2 second. So just to make sure that the IO pattern is, the pages are significantly distributed along the cycles of the boot. So this is something which we are exploring, but that's the idea which we are looking at. The final step is doing parallel recording and replay phase. Instead of segregating the record and replay as two different phases, we can take advantage of these new trace points, wherein we can run the replay and as well as the record in parallel. And then once the boot is completed, we can then take the pack file and see what files have indeed changed and what files have been and the IO pattern has changed over that new cycle. So that's something which which seems to be promising from Chrome OS side of things, where we have seen about 3% improvement, but we don't know the overhead of enabling all these trace points during every cycle of the boot. Because, for instance, file map pages and file map fault are pretty much in the hot path. So enabling those on the we might just overflow the ftrace buffers, or enabling those buffers shouldn't impact other processes per se. So
hey, Akhilesh, I had a question.
Yeah.
I think maybe the previous slide you're talking about, or maybe this slide, the N1, N-2 stage, and splitting it up into the pack files in different stages. That seems like something that's assuming, number one, you have like the packs aren't changing each time, meaning you can have more stages added in the future. So it's not as generic enough. And the other part is if, like, say, a particular stage is pretty small, like how do you time that you're loading the next pack at the right time? Would it be possible? I don't know how difficult it is, where you can just have like a load ahead pointer that's kind of like always say 10 to 100 pages ahead of what the most recent access is. Is that something you're looking into? Is that a possible solution?
Yeah, that's
so
a good question.
Instead of having hard lines, you're just basically having like a continuous pointer, right?
Right, exactly. So when I say Android has different stages, we have triggers to say that what stage has started. So we can actually time between these stages as well. But you're right in the fact that not every stage has a significant IO activity going on. For instance, the first two stages, early init and init, the pack file should be like very, very tiny. So but having said that, yes, we can explicitly track when exactly the new stage starts off, because we have trigger mechanism through init RC scripts, similar to what systemd and Upstart is. Android has .rc scripts to start the services, so we can track those to monitor the activity.
Yeah, I guess my point is more like that having this instead of having this hard lines for stages, still have like one continuous. Think of it like one continuous list like you had before, but you have like almost like a load ahead pointer or whatever, right? Because you're tracking.
Right.
If you can track which pages are getting loaded now, or they're trying to load or start access now, then you know that okay, the next no, then it's going to take me, I don't know, half a second to read a page, so I need to load the next 100 pages ahead of time or whatever, right? The main point you're trying to do is you're trying to avoid waiting on the reads. So if you know what is being accessed now, then you know what to load now. If that
Yeah,
makes
I think
sense.
that's doable. Yeah, that's
It
something
seems like a more
which
generic
could be
solution
explored.
where you don't have to worry about stages, you don't have to worry about if it's Android or systemd, it'll just work if it's possible. But obviously I'm not implementing it, so I don't know the difficulty.
Yeah, I think we'll have to investigate that. That's a good point. The other solution which we are also thinking about related to the memory pressure is tracking the PSI matrix. For instance, if we have a certain PSI threshold, then we can inform the prefetch daemon to back off and not add more to the system pressure. Yes.
I'm just curious. So where in your current implementation, where do you actually start your prefetching?
It's in the very early stage in the boot. So if
I assume it's after SMP init.
Yes,
Okay.
exactly.
Okay.
Isn't the prefetch happening in user space, right?
Sorry?
The prefetch daemon is running in user space, right?
Yeah, it's in the user space, correct. Yeah, it's a daemon which is written in Rust. It runs in the user space, and it's one of the platform process which runs at the very early in the boot. Yeah.
Yeah. And I don't mean to diminish the work that you're doing there, but having monitored Android's boot time for years, it's always been very horrible. And this seems to be like a marginal sort of take on what we're stabbing at. Like even 10% is just not that great. And I was wondering if you'd ever looked at just hibernating the flash and then essentially just booting from the hibernated image and only rebooting in full on an OTA. And in that case, you can hit 5-10 second boot times, which would be way much better than what we have now and way much aggressive than slight single digit or even double digit.
Right, makes sense. I think that is something which we have received request, and that is on. We have to look in as a holistic feature per se. This specific project just focuses on the I/O activity.
Sure,
but
granted.
I hear.
And again, I don't. I'm not taking away any of the value of what you're doing. I'm just saying this only takes a marginal stab at the really big problem, which is way much bigger than that. Like you look at how much time Zygote takes to boot, system services start booting, and it's really sluggish.
Yeah, so there are other bottlenecks there apart from disk I/O. That is being something which we are investigating as well. But yes.
Cool. Thank you. Yep.
Is it actually that bad? Like, I don't know what phone you're using. I've seen like 10-second, 15-second boots.
So when does the record step run? Does it run on the user devices? Does it is it run before? So what the page cache, is it deployed with OTA updates or not? Is it built at runtime on the device?
So today, as of today, record is run on the device, meaning that whenever we do a OTA update, we know that the I/O pattern is going to change. So we run the record once and determine the entire I/O pattern. And then subsequent cycles of the boot, we'll run the replay.
Okay. So does it only run once after the OTA or?
Yes.
Okay.
Yes.
I have another answer for that. So Akhilesh talked about Android. On Chrome OS, we are also running the recording phase at the same time as replaying during OTA as well. So on the first boot after OTA, Chrome OS is replaying the previous version's recorded I/O pattern, but at the same time, it's recording the new pattern for the new OTA version as well. Yep.
I think that could be.
Yeah. So one thing, Akhilesh, is that I think the first boot after the receiving the OTA has a different access pattern usually. So we learn from the one after the OTA.
Yeah.
So that is the regular boot.
Right.
And
So
then the third boot after the OTA is faster. Okay.
Okay, so you mentioned earlier about the memory constrained devices where some like the pages get evicted.
Right.
Do you have in your daemon anything to evict, like to tell? I think there's a syscall that you could tell it, like an madvise one. I think you could tell it to like this is no longer needed. So like when you hit like one stage, you could have your daemon start like prefetching pages, but then when you kind of get to like one stage done,
right,
you could just say these other ones are no longer needed. And
Right.
maybe that'll minimize like thrashing of the page cache, and it can evict the right things so that new things can come in that spot.
Good point. Today we don't track at that layer, but that is something which, if we can do it, wherein if we can say that these pages have already been done, then we can run POSIX if advice don't need, and then evict those pages manually from the user process itself. Yeah.
So quick question. Is there any information that you can put in the OTA that would be useful for you for the next boot? Perhaps like run the replay, the record stage selectively or something like that?
Yeah, I think so. That's something which Stephen mentioned. I think if you can do all these on the offline in the lab and then bundle it as part of the OTA itself, then some of these could be simplified. Yes.
Hey, I was wondering, have you looked at across from run to run, how much noise there is? Like, are you prefetching pages that you recorded but then are not actually used?
Not yet. That's a good question as well. That's another challenge wherein when we record and all the page cache insertion has been done, some of these pages were brought in by the kernel read ahead as well. So which means that, let's say if the process touches 4K page, the kernel read ahead will kick in 128 KB, and all those will get inserted to the page cache. But technically, those 128 KB are just redundant. So we will have to literally dissect and figure out what necessary pages which we really have to bring in. We did some experiments wherein just disable read ahead and track only those pages which have been inserted to the page cache, but we didn't see much improvement there.
Would there be value in adding to the trace point that add the information that this was triggered by a read ahead?
Good point. I think that will be valuable. Yes, to say that if the trace point is saying that whether these pages were brought in from the read ahead instead of from the process itself. Yeah.
More questions?
I just want to touch upon one last thing. So we are also looking to integrate some of this in the virtualized environment. So Android does support running full-blown Debian OS as a guest as part of the Android virtualization framework. So it's called Linux Terminal. So we are trying to see if some of these ideas could be adopted to improve the boot time for the Debian OS as well. But unlike Android, the Debian OS root partition is read-write, so which means that the I/O pattern might be different between subsequent boots.
Well, thanks a lot, Akhilesh, for that.
All right.
There was some good interaction. There will be so I guess you're around, right? So whenever you want someone to find him or so, to discuss it further.
Yeah, please feel free to reach out in case if you have any questions. Happy to chat.
Okay.
Thank you.
So to keep Tim happy, we have another boot time optimization session. This one will be remote, so Saravana will join us remotely. I will change over the slides here. So, Saravana, can you go on the plus button and take presenter? Is that possible for you to do?
Where is the plus
in the big blue
button?
In the down left blue button with a plus
Oh,
sign.
now I see the down left. Yeah.
I've made you presenter.
Yeah, I see it now.
Okay,
Although
thank you.
it seems to be in the wrong slide. Okay. Yeah, I have
Okay.
control. Sounds good.
But you can control the slides now, right? Yeah, that's working for you.
I do.
Okay.
It's all good. Thank you.
Okay. So I will monitor here for any questions and so on, because I'm not sure if you're seeing all of that. And I will let you know when the time is running out as well. Okay. With that, hand over to Sarvana.
Cool. Thank you. Hey, I'm Saravana Kannan. Thanks for being here. This talk is about boot time optimizations that we have tried before for Android that should also apply to most embedded systems. And the goal of this is to have like a discussion. If people have questions, please interrupt me, because I'm just kind of presenting information that's already there. But the reason for this talk is that people come and talk to me like, hey, we're thinking of doing this, we're thinking of doing that to take care of this particular issue in boot time. And then I pointed out, hey, but have you looked at this other feature that's already there in the kernel? So I noticed people weren't aware of some of these features. So the goal of this is just to kind of get this into the community's mindset or memories that these things are available, that you can start using already. And hopefully we can focus on things that are not there. So yeah, the typical boot flow, this is what I'm looking at as, bootloader is going to load the kernel. Kernel goes through some initial early init calls for the core frameworks, and then it starts probing devices. You start user space, that starts running some user space stuff, and user space gets to a point where it considers that boot is completed, right? So typically a login screen or a lock screen, that would be when you would consider boot is done. So that's the part of the boot I'm talking about here. And I'll get into each one of these phases on how we can do different things to optimize, what to watch out for. By the way, can people see this cursor thingy I'm using? Yes?
Yes, we can.
Okay, cool. Thank you. The first thing we noticed for Android is make sure to recheck your decision on your compression algorithms. gzip produces like a smaller image, but it's way slower than LZ4 for decompressing. So for decompressing the kernel and for decompressing the RAM disk. So with faster storage and larger storage, the image size no longer is a bottleneck or that relevant. So double check your assumptions there. Depending on your image size and your platform, you can save, like half a second to a second. On Android, that's what we ended up saving. And yeah, so like revisit the disk at that particular point. You might be surprised. The second one is, it seems kind of obvious. Pick the right frequencies for all the hardware blocks that you use during boot, especially the CPUs. If you can max them out safely, go for it. But most of the times, if it's a high-end system, you might have thermal concerns. When you do, let's say you get into some weird boot loop, you don't want your device to burn up, right? Because early in boot, you're probably not having thermal management running. So you'll probably have like a limit on how fast you can run the CPU, but make sure you can run as fast as you can safely do. But the other key point is make sure that it's not just the CPU, right? You want to run the DDR fast because you need to read from there and run. But don't forget stuff in between. So you might have the L3, you might have the interconnects, or you might have a system level cache. Make sure you run all of them fast enough too, so that the path from CPU to DDR is not slow. But the part where it starts getting tricky is if you have some other device that's accessing DDR, and if that device and its interconnects are slow, it can cause like some kind of like a back pressure on the DDR, where the DDR is taking too long to respond to this other device because all the interconnects are slow. So if it's a display splash screen, for example, right? Like display is trying to read the splash screen, that can be so slow that you end up making the CPU wait, because like you will do one transaction at a time or like n transactions at a time, right? So make sure any other hardware block that's using memory in a significant amount, it also has its interconnect paths running fast enough. The other one, which is kind of counterintuitive, is depending on the situation, if you enable your big CPU, you can actually end up slowing down your boot time. So take, for example, let's say your big CPU is twice as performant as your little CPU, meaning DMIPS per megahertz is 2x that of a little CPU, right? Then let's say because of your system, you said, hey, you're booting the little CPU at 1800 megahertz, and you set the big CPU to 300 megahertz, right? Because of thermal pressure, thermal concerns, or because you forgot to bump it up, whatever reason. So at this particular configuration in the bootloader, your big CPU is actually only 33% as performant as the little CPU, right? Because 300 times 2, 600, 600 is 33% of 1800. And the thing to be careful about here is when the kernel is booting up and initializing, CPU freak runs only at like device init call, which is like I think the 5th or 4th init call. So there's a bunch of stuff running before it. And even in device init call, it's not like the first driver that's being probed. You have like a bunch of stuff at device init call. So until CPU freak runs, the scheduler assumes all the CPUs are at the same frequency, right? So it thinks the big CPU is more performant, and it's going to put all the threads into the big CPU. And when it's serialized, most of the threads are going to end up in the big CPU. So you're running actually, at 33% the performance that you could have gotten if you turned off the big CPU. So make sure that the bootloader configures, this actually happened on a product. So make sure that the bootloader configures like all the CPUs to be at least the same performance or higher performance as the smallest CPU. When I say smallest CPU, smallest from a perspective of DMIPS per megahertz, because that's all the scheduler is looking at early parts of the boot. The other part, I implemented firmware deviling for ordering probe dependency. So this is going to avoid, so enable firmware deviling, but it's enabled by default, but I know some people have been disabling it if it's causing some issues. Please report them upstream. I try hard to resolve all the issues that you might hit with firmware deviling. And yeah, so that enforces proper probe ordering, and that's going to avoid deferred probes. So that's going to speed it up in that sense. The other part that I want to kind of raise awareness about is for firmware deviling to work correctly, all your drivers need to use the driver core and the device driver model. So if you're using like legacy macros like OF declare or clock declare in your drivers, basically what you're doing is you're hooking in your init call for your driver, and you completely skip all the driver model, and you're directly accessing the hardware in the init calls. That's what is effectively happening. And when you do that, firmware deviling cannot enforce any dependency. So basically kind of like things are now working outside of firmware deviling, and you can be doing things in the wrong order. Like a bunch of things would be inefficient. And the other part is if you have cycles in a dependency link, firmware deviling was not enforcing ordering between those devices. But about like a year ago or maybe 2 years ago, we added a post init provider's device tree property that kind of informs firmware deviling which part of the cycle is not a real dependency. So for example, you add it to a consumer and say, hey, this particular supplier is a post init provider, meaning you don't really have a dependency on that. So that helps break cycles. So your ordering and enforcement is much better now. So try to like make sure you do all of these things so that firmware deviling can work better. Oh, and then the other part is in your init calls, every driver should only be doing driver registration. If you do any kind of driver device access, you're not properly following the driver model, number one, but it's also going to start breaking again in terms of dependency, because now your init call is starting to act like a device probe. So these are all kind of like a high level or like the surface level improvements from firmware deviling. But then you get to it has like other side effects or like, other secondary level improvements that you get from firmware deviling. This is something, again, somebody said last year, like, oh, I didn't know this was there. So the driver async probe kernel command line, if you say driver async probe equal to star, it basically enables asynchronous probing globally, right? So another way to improve boot time is just enable async probing for all your drivers. With firmware deviling, it just works if you have it actually, like, for example, if you don't have cycles, if you don't use OF declare, right? It just works. Or at least if it doesn't work, it'll be really easy to fix. So first, try driver async probes equal to star to enable it by default. If you have to have some exceptions where it's not working, you want to disable it, that's also easy to do. Just after the star, just give comma and list the driver names, XYZ. So in this particular syntax, once you give a star, all the other drivers you list, they become exclusion lists. So you'll do asynchronous probing for everything except X, Y, and Z. But there's also like a kernel command line limit. So if you make some of these drivers into modules, then another way to go about it is do module.async probe equal to 1. That again enables asynchronous probing for all the modules by default. And then you can selectively disable them by giving the module name .async probe equal to 0. So we tried this on a real phone. And so this is basically the for synchronous case, the boot time, kernel init time took 900 milliseconds. With asynchronous probing, it became 450 milliseconds. And what you see in these images here is like a heat map of all the CPUs, right? So each row here is like a CPU, and time is going from left to right. You can see how like the big CPUs are active during synchronous probing, because you're probing one device at a time. It's a big thread, gets put on the big CPU. All the other little CPUs and most of the big CPUs, they're not active. It's like serialized. But once you do asynchronous probing, you can see all of the work gets done in parallel, and all the CPUs are super busy, right? So try to enable asynchronous probing. That should give you quite a bit of improvement in kernel init time. But that's just one part. You can actually do even better depending on your system. If you have a fully modular system or mostly modular system where most of the drivers are modules, what's better than doing asynchronous probing is doing parallelized module loading. But this would need support in user space. In Android, it's supported since Android 13. If you set this in the kernel command line, android boot.load modules parallel equal to 1, that causes the init Android's init user space to start loading modules in parallel.
So
It's
Saravana,
better than
what exactly would be needed in user space? So if Kmod would like, what kind of modifications would we need to like get that sorted besides Android?
Number one, I don't fully know, like for example, systemd, how much parallelization is supported. But the main idea, and I'll kind of cover this in the next slide too, is you should be able to give a list of modules and it should just try to load them all in parallel. But also, at the same time, making sure you honor soft and hard dependencies listed in the module, right? So you don't try to like load a module twice because two different modules depend on it. Those are the kind of changes you might need. Does that answer the
So
question?
you need this kind of tracking. You need the tracking in user space for that to give like the correct ordered list already, or is that something on the kernel side that's handled?
You need a user space list of ideal ordering of modules, and then when you know the ideal ordering, you just load them all. So, for example, for a distribution, it probably wouldn't work because you can run this on any kind of device. But you have a very specific, say, commercial setup where you know exactly what board you're booting on. Then you can generate the module list and say, hey, these are all the modules I'm going to use. Load them all, and load them all in parallel, right?
Thanks. That's another
Yeah,
question.
I'm not
Sorry.
Go ahead. Yeah, please interrupt me.
You mentioned with yeah, you mentioned with systemd, you weren't sure on that. So older versions of systemd did the systemd module load. It would do it serially. The new, I think in 258, the one that just got released like maybe a month ago or a couple weeks ago, that one has support for loading all that in parallel. So just a heads up.
Okay, sounds good. I'll kind of go to this in the next slide because there's some pointers there too. But yeah, continuing on this one, when we do parallelized module loading, this was asynchronous probing. You can see it's even more dense and even more heavily used the CPUs. Because what you're effectively doing is not only like probing the devices in parallel, you're also like accessing flash and loading the modules in parallel. So it gets even more compressed, that timeline. So now going on to loading the modules in parallel in the right order, there are two ways to do it. And this is where I don't know what systemd does. One way to do it in parallel is, every time a device gets added, the kernel emits a U event saying, hey, this device got added. And I know certain systems, they load the module based on that because it'll emit not just the device, it'll also emit the compatible string, module names, or whatever. That I know some systems kind of load them as the devices are added. In that sense, it'll be kind of parallelized in some sense, but it's not fully effectively parallelized. The other way to do it is to list the modules ahead of time and say, hey, just load them all. I know they're going to be needed eventually. So depending on your system, number one, only one of them might be available and only one of them might be more performant. So you need to like play around with both. But I think in most systems, the second option is going to be faster. So going back to the somebody talking about system D, do you happen to know which one of these two options it does? I'm assuming it's the first one, but
Oh,
I can't
the
hear you,
system D
Doc.
module. It's the system. Oh, it's the system D module load. That's the one that they added the new feature, or does it in parallel? My understanding is with UDEV, I believe it also currently does it in parallel as well, but I'm not sure what versions on that.
Okay, so you don't know like which kind of parallelism is happening, right? Whether it's based on events or just ahead of time, right?
I'm sorry, I couldn't understand the question.
Somebody else is trying to talk, maybe. I think they're trying to explain it.
Okay. Oh, actually both, because if you do the system with the first one, yeah, there'll be the system D UDEV, and then the second one, the loaded modules ahead of time, that's the system D modules load. And that's the
Okay.
system D modules load. What recently added support for doing that in parallel.
Okay, that's great. Okay, then people should be able to use it in that case too.
Already does it in parallel, is my understanding as well. So I think both of those are now parallel.
Okay,
System
that's
D.
all. Okay, so yeah, if you can do the second method of doing it, where you can list the modules, please use that. Otherwise, for something like a distribution, you can probably use the first method where you just kind of do it based on events generated by the kernel. But if you do the second option where you list the modules, you want to make sure you load them where you load the parent module first, like a parent devices module first before you load the child devices module, right? Otherwise, once a parent device is added, if you haven't loaded its module yet, now it's just kind of sitting around, right? Same for like suppliers, right? If you have if you use a clock for your device, you want to make sure the clock device's module is loaded first before your device's module is loaded. So that way, there's no waiting around. As soon as the module is loaded, it already has the device that it needs to probe, and it finishes probing as part of the init call context. Because init call will register the driver. As part of the registration of the driver, if you already have the device, you're going to start probing the device. But how do you get the right order? That's where firmware devlink helps again. Firmware devlink exposes all the dependencies in sysfs. And I've already written a script called dev.needs.sh, and it's part of the scripts folder. If you run it, it gives you some help text. But the idea is you run the script and you give it all the devices in your system that you care about, and then your different flags you can use, and then it'll spit out the list of dependencies in the right format. And you can just pipe it to tsort, which stands for topological sort. And then if you just pipe it to that with a few right options, you can ask me the mailing list. I'm happy to help it. It might already be there in the mailing list. But the idea is that if you run dev needs and pipe it to tsort, it can give you the list of modules in the right order. So you don't have to figure it out. You can just kind of run the script, it'll give you the right order, and you're done. Okay, it's telling me lost connection, but hopefully people can still hear me.
I still hear you.
Yeah. So yeah, in Android devices, we know all the models ahead of time for every single phone. So people who want to use it on Android, they just kind of list the modules and it just works. So we talked about the kernel. We talked about using modules. Some obvious points for modules, but it's easy to miss. Make sure to strip the debug symbols. We actually saved several seconds of boot time when you notice that we hadn't stripped the debug symbols. It helps in multiple ways. It reduces the image size, so RAM disk and module loading from flash is faster. It reduces the amount of data to be decompressed. It also reduces the kernel module load time itself. So yeah, it'll save quite a bunch of time if you strip all the debug symbols. The other part is you want to avoid excessive logging in your drivers. And this is not just about reducing the size in terms of the strings you add to the driver that you're logging. It's also that the module load time can be significantly slower if you have a lot of, say, logging a print case in your driver. The reason is when, at least on ARM32 and ARM64, the kernel does the nlog and sort of all the function calls that the the module is making into the kernel. The more function calls you have, the longer the sorting is going to take, and actually adds up pretty quickly once you start having an excessive amount of logging. We actually saved like 300 milliseconds just by disabling logging on kind of like modules that have too much logging. Thankfully, this is not like an upstream problem; it's more of a downstream problem. But if you have modules with excessive logging, you might want to compile them out. It's not sufficient where it's like a dynamic logging, you disable it, it has to be compiled out. Otherwise, the module loading time can be significant. Like the one module took like 250 milliseconds to load just because of the logging. The other one, this is not a generic guideline. You really have to be really picky about it. Is try not to load large firmwares in your device probe because that's going to slow down the rest of the devices from probing, depending on how early your device is getting probed and what else depends on it. So it's not a blanket statement. Most of the time, you should just do it on probe. But if you have a large firmware and it's going to be happening early in the boot stages, try to do it on demand. So you'd probe successfully, but when somebody tries to access the device, then you might load the firmware. That kind of prevents you from significantly slowing down the rest of the stuff from happening. The other one is if your module doesn't need to be loaded for a user perceptible boot complete, don't load it before you start user space, right? You can you can continue loading these kind of modules after you kick off user space to start, like say, all the frameworks. So for example, in Android, you want to get the UI framework to run, just get that going before you try to load the camera module, for example, right? Because if you're trying to get to the lock screen or login screen, you don't need to load the camera module to get there. And if you're doing it in parallel with user space running, you're going to kind of hide the time. And like because you're doing it in parallel with the user space, you're kind of, for instance, hiding the time taken to load these modules. And then if you have a particular framework that needs a specific device to be working for it to function correctly, because you're loading these modules, say, later in time, for example, camera HAL, right? You might want to have the camera HAL wait for a particular file to show up on sysfs or a device to show up on sysfs before it actually starts running. You'll have to do those kind of dependency enforcement, but it's still overall, I think we say like a half a second to a second. I'm giving fuzzy numbers here because it's going to depend on the phone and I don't want to like give out the actual data. So I'm being careful. Right now I'm presenting everything as an individual, not representing any company. So yeah, long story short,
One second. We only have like 5 minutes left, so I just want to make sure that if there are any questions or comments here, we can get started on that front. If not, we can go further ahead. But I just want to make sure that if anyone has like what we talked before, any questions, comment on that?
But it's the last slide. I'll quickly wrap it up. Main point is counterintuitively, a fully modular kernel can be faster than a fully static kernel because you get to do a lot of them in parallel. Probing is in parallel. You can load the models in parallel with user space. So try to go for a fully modular kernel and you can get a faster boot time. That's all. Questions?
Yeah, so I'm an Android dummy. Does Android have its own bootloader, or does it use, U-boot or system D?
I think
to
every phone OEM or vendor, they have their own bootloader. But I think they're trying to converge mostly. There's like a GBL generic bootloader that I think Android is trying to converge everybody on, but there are definitely many parts of the boot stage that's specific to a phone.
Okay.
They're definitely
Now,
not using the hub.
So Chris Simmons years ago did a talk on something called Falcon mode, which allows you to boot straight into Linux without a bootloader. I don't know if that's anything that is even a consideration for Android, but okay.
But this is meant to be a generic, for all embedded devices. This talk is not specifically meant for Android, but yeah.
Okay, so U-boot can boot the Android kernel images. There's a command for this, aboot something. This is supported. The U-boot SPL can boot kernel images directly as well. This is what's called the Falcon boot mode. So yes, you can boot Android from U-boot. Whether U-boot is available on your platform depends on your platform. Mobile phones usually come with vendor bootloaders. Evaluation kits may come with U-boot.
Right, and then
Does this
independent of
answer
the
your question?
bootloader, the idea is the same,
And yes, the Falcon boot will skip completely the U-boot stage, so it saves you a couple of seconds potentially of boot time. That's correct.
Yeah, so independent of what bootloader you use, what boot mode you use, make sure to set the CPU, all the stuff I covered under bootloader, try to get to them.
Okay, on this slide with the fully modular kernel, does that also include modules such as like clocks and regulators and interconnects?
Yeah.
Or should those still be built in?
No, make them all modules, right? So the things that you would want to build in maybe would be frameworks. If you can make, so at least the ones we have done or I have experience with, we didn't convert any of the frameworks itself into modules. So the clock framework, for example, it's built in, and I don't think it can even be made into a module. But some frameworks can be made into modules. You can build them in, but all the drivers, they're modules, even a clock driver.
But you'd have to, like for clocks, you'd have to do like clock ignore, run with clock ignore unused, for example, in that case.
So that's where firmware dev comes and helps you. But there's another talk tomorrow or day after where we're trying to get those things sorted out. But general idea is that firmware dev will make sure the clocks are brought up at the right time. It'll also inform the clock driver when it's okay to turn it off, so that you no longer have to depend on clock ignore unused. So those things will still work correctly.
So one of the other things that's not in your slide is on the bootloader blob, a lot of vendors are putting a lot of other stuff into the bootloader, like especially loading firmware for other coprocessors or security processors or NPUs and DSPs and all that stuff, and that takes a long time. But the other thing is that because the kernel has been quote unquote slow to load, vendors have also moved stuff into the bootloader, like for early camera and for early display and things like that. So you end up with the reverse problem of all this bloat in the bootloader because of this problem not being solved, and then you're stuck with a big bloated bootloader when you go to try to solve this problem. So you have to go backwards a little bit as well. But yeah, I just wanted to comment. Having seen lots of vendor boot code, I see like a lot of the trends in vendor boot code is actually going the opposite direction from this, unfortunately.
Yeah, that's a very good point. And I think if you make it a fully modeled kernel, the main reason is that the kernel takes a while to boot, so it takes a while to get the camera. But if you make this part really small, because you kind of take everything out of it, then you can manually, because you're giving a list of things to load, you can say load the camera first. So ideally, I know it's not always possible because I know, for example, automotive, they need like sub 2 seconds, and maybe it's never possible in the kernel. I don't know. But there's still a room for like handling those things without bloating your bootloader. So again, you might want to look into a fully modular kernel and see if it solves that problem.
Yeah, I mean, I think your approach is good here. It's just that the industry is taking other shortcuts that make it even more work than just doing what you're doing. I guess that's my point. So.
Yeah, I understood that. Yeah, thank you. That's a good point.
So is there a plan to enable async probing by default in the driver core
So
at some point?
unfortunately, there's always going to be like one or two devices where it's not going to work because they haven't fixed up the device tree to make sure post internet providers is correct. There's going to be always some case where it's not going to work globally, or so it's unlikely it's going to get enabled by default. I would like to get there at some point, but I don't think anybody is brave enough to sign up for that.
So I was thinking for some classes of devices, like I believe there's a macro that goes a little like declare I2C device. Could we insert some compile time cookies to perhaps make the module loader aware that this is a device that requires this bus to be present first, and maybe make decisions on the order of probing based on that?
I'm not sure I'm understanding the question.
Sorry,
From
order
modeling
of
already
loading.
there's the right ordering, so I don't understand the question.
So would it make sense to spend time early on loading a module for an I2C device before an I2C bus controller driver is loaded? Or is that not predictable enough?
I think you mean the other direction, but yeah, no. Probing wise, it's already taken care of. We don't need to do anything special. For module loading, that's a part, like I talked about in earlier slides, about getting the ordering correct. Where is it? If you follow the steps here, it'll kind of give you the right ordering. So you don't have to like put any special macro stuff. Also, one other problem with trying to put stuff in the macro is that depending on your system, it could be different, right? In one particular system, you might be like the supplier. In another case, it could be the consumer. Sometimes it could be both. If it's an I2C, like a PIMIC, you could have one PIMIC feeding another PIMIC, right? So there's like in the module level, you can never specify the dependency correctly because the real dependency is between devices, not between modules.
Awesome. So I just want to add one more thing to the boot time optimization stories. Like the bootloaders initialize multiple devices. For example, it trains the filings and things like that. And when we hand off to Linux, we start again everything from scratch. So we are really duplicating that part. And if you could have a handoff mechanism from bootloader to device handoff mechanism from bootloader to a Linux kernel, it would actually save a lot of time. But yeah.
Yeah, it's a good point. Early on in my career, so I don't know, but one of the approaches was, hey, we couldn't trust the bootloader did it correctly. Let's just do it again. So there's also that aspect of it.
I need to cut off here. We're running out of time. Sorry for that. Any more questions? He's not here, obviously. We can see that. But I mean, reaching out to him on email or something should be one way of like getting things started as well. So okay. So we're switching over to the next session.
Just one quick
Guys.
point. My
Thanks a lot.
email is out of sync and maintenance file. I'll update it soon. Thank you.
Okay, and now we are moving away from making everything boot faster, and we're going to see how we can reuse code from Zephyr in RTOS if you're going bare metal again. So Kasim. So, as you have seen,
I'll make it very fast. Right? Yes. How do I go to slide 1?
You can just go back in the screen. Just the same. Just the arrows. It should be working.
Okay.
So let's give like 30 seconds or so to like come down.
Sorry?
Let's give a few seconds for them to like come down, and I will make sure that they are not making noise. I ask you to. If you want to discuss, could you go outside? You want to follow on with the next one. Okay, so let's welcome Kasim. Starting with the next session.
Settled. Okay. after a wonderful session on Android boot time optimizations, I'm taking everyone back to the world of RTOS. So this is like completely a other side of the world and dealing with MCUs and dealing
But
with
it's really fast. So
sorry,
your boot time is really good as well.
and it's a completely new and different world for us. And then starting off with Zephyr, there it's like a completely new approach and dimension. So I actually wanted to bring a different problem here to discuss, and then this is mainly towards MCUs and Zephyr. But then I was telling to Karim this morning, Android is being replaced by Zephyr in many IoT and embedded applications, even Linux in many places. So most of the concepts that we are discussing on boot time, on many things else like the low latency and such things are moving to Zephyr. And Zephyr coming from as a flavor of Linux, the adaptability is much higher. So let me quickly get into the slide. So I don't want to introduce TI, but I want to introduce a few things like where we are enabling Zephyr. So we are enabling Zephyr on processors, and which is like ARM A cores and ARM R5 cores, or it is your M4 cores and such things, and then application specific microcontrollers and general purpose microcontrollers, and the drivers for connectivity like Wi-Fi, Bluetooth, and such things. So Zephyr is running on all these places today. The scope of this presentation, as I said, like I want to bring and discuss a different set of problems here, which is mainly involving Zephyr and RTOS. And the focus here is to see like how we can enable Zephyr and compare it with any kind of bare metal RTOS or bare metal device drivers that we regularly develop on free RTOS. So let me go more deep into this and then come back to the actual problem. So where all do we use RTOS today, and what kind of RTOS do we use? Now, if I want to just give a very high level overview, in any kind of time critical applications, safety driven applications, low power applications, secure, connected, and which needs quick boot time and very easy to use. So in these areas today, we are using some kind of RTOS, right? And this RTOS, as I just said, it is not just running on microcontrollers, but it also runs on very high-end ARM Cortex A core, which is almost running at 1.4 gigahertz kind of thing. So it's not just a play of few megahertz kind of microcontrollers, but it is also running at gigahertz family of microcontrollers and microprocessors. RTOS also runs as a add-on module to A core. Like you have in a system, if you have ARM Cortex A core and then you have some MCUs, then RTOS is running on those MCUs as well, right? So Zephyr runs. So when you think of Zephyr, you shouldn't just think that Zephyr is actually running on a simple IoT standalone device, but you should also think like Zephyr is running on a microcontroller, or it is running on as an operating system, as a scheduler. It is running on a MCU core or an add-on module or an accelerator. It could be anything, not just a bare metal basic fundamental kind of device. Okay, so what is the traditional practice that any RTOS engineer or RTOS end equipment is following today? Like the stack goes from bottom to up. So developing bare metal drivers is first thing an RTOS engineer does, or an RTOS end equipment starts with, right? Simple C file, simple include file, and then you have some compiler and you just finish your microcontroller coding, right? And then when you think like you need a scheduler, because now I want to get into a multi-threaded environment and my application becomes multi-threaded, then you start applying a free RTOS or a ThreadX kind of simple RTOS as an add-on to my bare metal application, which I just wrote, right? When you think of like, okay, now I have added an RTOS and I have a bare metal driver, but it is a networking device, or it is a flash, or it is a file system based device or something, then I go shop for open source frameworks or commercial frameworks. Like it can be your TCP/IP stack, it can be your file system stack or USB stack, connectivity stack, Bluetooth stack, and such things. So you bring that kind of framework on top of it. So as you can see here, right, the complexity is growing from just a bare metal C code to making it like a productized end equipment, right? And as you go up into the stack, you will start seeing commercial operating systems, commercial real-time operating system, which I have given as an example there, right? So the bare metal driver to a productized thing, if you see, the foundational piece here is still the bare metal C code that I wrote. Okay, I'm not changing the framework, I'm not changing the real bare metal code here. This is how a traditional RTOS engineer or equipments which are dealing with RTOS or in real-time operating systems are dealing with. Now, when it comes to Zephyr, now what industry has done in last decade is they are treating Zephyr as any other operating system. The way I just mentioned or described, start with bare metal code and then stitch it into Zephyr with a very thin shim layer or a HAL layer. Now with this, what happens is like you are losing the entire benefits of what actually Zephyr is offering as an open source real-time operating system with all the benefits of Linux and Linux community ecosystem environment, everything. Like I don't want to get into describing the benefits of Zephyr as an open source RTOS, but what I want to highlight here is the approach that RTOS community has been following or engineering community has been following in dealing with free RTOS or ThreadX and such kind of real-time operating system. They are applying same terminologies or same flow to deal with Zephyr, which in my opinion is, I won't say fully wrong because I do the same in TI as well, but then that is not the right approach. I don't want them to go to the route of taking the RTOS approach into Zephyr, because Zephyr has a lot more for any open source any open source framework to offer, right? Like you have plenty of things as has device tree blobs or the West report tool itself or your frameworks that Zephyr is offering. There are plenty of benefits and easiness of things which are getting lost by following the traditional RTOS application development. Now, what industry has done is they have taken this bare metal code, added a shim layer, wrote a simple vendor HAL, and sticked into Zephyr and thinking my job with Zephyr is done, right? But then with that, what has happened is tons and tons of code has come into Zephyr on a separate parallel repository, which is like your vendor HAL repository, and it is staying there, which only the SoC vendor or silicon provider or the if it is a chipset, if it is a chipset, then the chipset drivers are sitting in a separate repository. It's actually not truly integrated into Zephyr, not reviewed by the open source community, not following the standard practices of any open source community. It is staying completely outside of the Zephyr world, right? Now, this should not have been the case. We should have really written native drivers for Zephyr. That's what I'm getting towards. Now, the challenge that we have is once we start writing native drivers for Zephyr, the thing that industry has, the challenges that industry has will not go away, right? Now, how do we stitch or balance between these two layers? Like why I mean industry is not going to accept this approach is because there are tons and tons of investments which has already happened in these RTOS operating systems, right? Like there are commercial operating systems, there are free real-time operating systems which are available in the open source world, and there is a lot of certification that goes here which these operating systems are giving. Now, the bare metal driver that I wrote can stick into any of these operating systems, right? Now, therefore, I need to find a way, if I enforce my engineers and the community to build and develop Zephyr drivers in the native Zephyr way of doing things, then I also have to show a path to them to how to take this bare metal driver and stitch into any of these traditional operating system. So the problem here is always, or in the last 1 decade, the industry has followed the other side of approach where they wrote the bare metal driver, considered Zephyr as another operating system, another real-time operating system, hooked that bare metal driver on a separate repository, calling vendor HAL, wrote a shim layer, and somehow fixed the Zephyr requirement, right? Now, how do we do it in a different way? Flip it. Start with Zephyr first, right? Write your bare metal driver in such a way that it starts with Zephyr, gets reviewed by the open source community, gets an ACK from open source maintainers and community that has its own value, right? And I will not get into that. Once you do that, then if you want to go for a safety certified operating system, or if you want to go for any vendor specific operating system, right? Okay, now you take this driver and put it in your other operating system. There is a path, and if we teach this path to the RTOS engineers, then definitely we can see more and more RTOS engineers joining the Zephyr community. And if you show the path how you can migrate those Zephyr drivers to the other operating system, then it becomes like, first thing, we are getting more community on Zephyr side. Second, we are also using the best of the other world, right?
So let me play devil's advocate here.
Yeah.
So why Zephyr first? Why not do it in ThreadX first and then export a bare metal driver from there and then do it in Zephyr? So, I mean, don't get me wrong, I like the approach, but it's more like, what makes it so beneficial to do it in Zephyr first and then do the export from there?
Yeah, today by doing in Zephyr first, by not adopting to Zephyr first, like as I was just highlighting, the code is not coming into Zephyr first. The code is coming into a separate folder and separate repo with vendor HAL. Like when I am any, including TI, any other organization, if you download Zephyr today, it is coming in 2 repositories. One, our Zephyr project, and then second, HAL project, right? You have to download these 2 projects, then it forms Zephyr source for compilation. Now, as I said, there is code which is directly coming in that HAL repositories, which has zero control from open source community, because the repositories are owned by the organizations which are pumping in the code, and it is not following any framework, it is not following any standard practices, coding guidelines, nothing, right? It is some code which was written for some other operating system is making its way into Zephyr, right? Now, how do you bring that kind of framework? How do you bring the open source beauty into Zephyr for RTOS world? There are so many benefits of Zephyr which are not getting consumed.
Basically, the biggest benefit for this flipping around, you see, it's more like that you have like the open source practices of like doing the peer review, making sure that you have like come to a point where the code is actually acceptable by most people.
Yeah.
And then from there doing the export. So that is, you want to use Zephyr for its community of reviewing and so on to get the practices in.
I can go more like the CI/CD, the tooling that it has, like the West tooling, which no other operating system offers, right? The Twister, the tool that we have for testing, right? There are so many things that Zephyr offers which RTOS community can use. They are not getting onto Zephyr first approach because they have a lot of their code written for some other operating system and then bringing in and trying to check mark Zephyr, saying like, yeah, we also have Zephyr operating system offering, and not making that as a true Zephyr development.
Okay, maybe we come to that later, but how would you make sure that at some point you're exporting that? And let's say you want it for some certification stuff, you want ThreadX or something, just an example, right? How do you make sure that this is getting updated as well? Because if you do this approach, your developers would work with Zephyr all the time, make sure everything gets supported, new boards getting added, bugs getting fixed, and so on, right? So there's a constant flow of like changes and releases coming out. How do you make sure that this is all going into the bare metal version and then flowing to the next, to the different consumer, basically, in a different one?
Yeah, I have listed down some of the things that when you start writing Zephyr driver, how you can structure it in such a way that it can become an easy migration. So I have some steps which I have highlighted here, which I'll describe.
Just wait.
Yeah. So hope, yeah.
Go ahead.
Yeah, okay, but if you structure the driver in some specific way, is it still compatible with Zephyr, or is
Yeah,
it
yeah.
some sort of a
no hack
strange
way.
HAL-based hybrid which doesn't really fit into Zephyr?
Yeah, it shouldn't be. That's the whole point. Like from my team and me, we have formed a skeleton with which, if we follow, we adhere to the best of both worlds. But then we need to improvise it, and there is no strict standard way that we are following today. But if we can come up with a common practice, so today Zephyr has not taken this requirement that the driver that I am going to write can be easily deployable in other operating systems, right? That has not been a requirement. If we can consider that requirement, put some standard framework around it, then it can be easy for us to migrate.
One more question on what you want to leave. So please, well,
You can do the in-room and then I'll ask mine.
Voice again.
This one?
Can you hear me? Yeah.
Yes, we
okay.
can.
Yeah. My question is the idea of the Zephyr using the Zephyr drivers as a experimental one is similar like some industry practice such as the AutoSAR CP. In the AutoSAR CP specifications, there have MCore specification that separated the driver layer outside the scope of the entire OS. So how to practice your idea? I mean, do we need to define a Zephyr MCore similar specification to separate the drivers out of the Zephyr code base?
Correct. Good question. I have a slide to talk about it. Give me 1 minute. I'll get there.
Yeah, I'll go next. So, by the way, this seems very similar to the same issues we had when Android was coming up.
Sorry,
right?
I lost connection, right?
Go. He said he'll get to your question in the subsequent slide.
Kazim will talk about the AutoSAR setup in a minute. So he has a slide about that. So let's wait for Sarvana's question and then he can follow up with the next slide so we can move on.
Because just a quick observation, all the problems you're listing so far seem very similar to when Android was coming up and people were starting to use Linux from the SOC vendors. So a couple of questions. One of the issues like SOC vendors have been always complaining about is like, hey, if you go to the open source community and review, it's going to take time before we can get our stuff done. Whether we agree that's valid or not, that's the mindset they have. Is that something you're not seeing here, or is that like, I feel like that's the biggest problem that needs to be solved, more so than these things, right? Because you to do Zephyr first they need to agree to do upstream first. Do you think that's not an issue of the Zephyr community?
No, that is a very good observation that you have, and that is one of the what do you say, the mindset or the challenge that this RTOS community feels, because they're not so used to this kind of upstream culture where they submit the code, wait for the response, see the response and fix it, and then absorb it into their internal SDK offering and such things, right? So definitely there is some kind of what do you say, hindrance there in accepting this approach. But somewhere or the other we need to start experiencing that and bring that methodologies of open source best practices into RTOS world, right? Definitely that is one of the key challenges that we will be having when we enforce this methodology.
Yeah, because what we used to see before was that they'll all be Windows mobile based drivers with HALs, and then they'll kind of wrap it into a Linux driver, try to ship it early on an Android devices. And as Android became more popular, it kind of died out. Linux became, those drivers became Linux first. So it almost
Yeah,
feels like it's
yeah.
going to just go where the market is going, but we can hope things are better this time.
No, agree. I agree there. So few things that few steps that we have identified. I can list those things, but these are not only the steps that are sufficient to make an RTOS development on Zephyr first. So few things that I can quickly highlight here in interest of time. First thing, like if you see any Zephyr driver here, it has three major components. One is how it is dealing with the clock framework and the device tree and the kconfig approach that it gets into, and then the device operate like the DevOps structure itself of Zephyr. So if I am an RTOS engineer who is starting my driver development with Zephyr first, then I would have written the Zephyr driver in this order, right? I would have used the clock framework, I would have used the device tree, I would have done all the configuration using kconfig structure, and I would have used the DevOps main device driver structure to fill all the configuration parameters. Now, when I have developed this driver, now how is it easy for me to take this driver and fit it into a FreeRTOS or ThreadX environment, right? Now that becomes a challenge. So here is where we are thinking how we can detach. So first of all, how do we develop the driver and in such a way that it becomes so easy for us to detach it from Zephyr and put it into any other operating system, right? So for all this, if you see all the previous presentations on Zephyr, it has always been told or taught to the community how to bring in RTOS drivers from FreeRTOS and ThreadX and stitch it into Zephyr. But this is first time I'm trying to say, like, if you have started your development on Zephyr, then don't worry, there is a path to take from Zephyr and put it into other operating systems as well, right? That's how that's the difference here. So first thing, the way we are trying to go do here is, like, as much as possible the device tree. So first thing is Zephyr completely depends on DT concept, right? Like you do all your configuration parameters, setting of all your fundamental IOs and things in DT. Now, how do you take this DT changes into an RTOS driver, right? It's very easy when you start with Zephyr, because Zephyr gives you build time script which can convert your DT into a simple include file. So that gives you all the macros that gets listed, right? That is the first fundamental thing that anybody can do, to just run the Python script, you get your include file. That include file can go into any of the traditionally available RTOS operating systems. Second thing, when we are writing our Zephyr driver, write it in such a way that there is a very clear differentiation between what gets hooked to Zephyr. Keep that as your high level driver, and whatever you want to carry into different operating systems, make as your low level driver. There are definitely lot of examples in Zephyr itself today which shows how to write a low level driver. Follow those. This is very easy way of dealing with when you are migrating or porting Zephyr drivers into other operating systems. The other fundamental challenge that we get into is like usage of sleep, right? Like Zephyr has different types of sleeps, like use sleep and K sleep timer, and there are so many different APIs that Zephyr offers to sleep in a function, right? Now, when you move that now I have written in application or a driver, and I'm moving this driver as is into another RTOS. Now that sleep function has to be properly dealt with. It may, like, you might be thinking that you gave 100 millisecond, and Zephyr might be dealing with that 100 millisecond in a different way. Now, when you take it into another operating system, you may not be able to measure that microsecond or millisecond latency, and that might make your equipment malfunction, right? We have to be very careful here. There are ways to deal with timers. This is one area that we can look into. And definitely there are various Linux best practices to follow for making your driver portable. Like any RTOS driver developer uses direct address mapping and things. So use structure definition so that you can when you are moving your code from Zephyr to another operating system, let the sections of your code where you are accessing the registers and memory area are very well segregated and defined so that you can easily migrate them. So I have given few examples here. I will not go into detail. And keep the portable pattern and non-portable pattern separate. That's what it means. And then clock and power, right? This is very important because Zephyr comes with very good clock and power framework. This is very, very important when you take it into any low power application. Zephyr is giving you all the framework to take to build an end equipment which is low power, but you will not find similar frameworks and hooks in any other operating systems because they are not so power aware devices. Okay, so when you move this clock framework into another place, you may not be able to easily move because there is no such clock framework existing in any other operating systems. So how do you manage that, right? There are few examples which I have shown here in the Git repository. But keep your code clock agnostic, right? That's what it means. So don't have static states defined in your DT, but you have to follow on one end the Zephyr clock framework, but keep your clock architecture in such a way that you can easily move into FreeRTOS world or any other operating system world. I will not go detailed into this because I'm losing time here. The other important part here is the ISR context, right? So in any sample driver that you take, there is one read function, write function, and there is an ISR, right? The ISR that handles all your interrupt thing has to be very, very low latency thing that you write. So make ISR very OS agnostic so that you can simply copy that ISR into any other operating system. Again, there are some good examples of these in existing Zephyr stack. The other part, when I write my Zephyr native driver, is I would have followed this device structure that I am showing here on the screen. Now, as I said, right, the clock framework that comes with the PM device structure and other things that you are seeing here on the config, the dev stats and DevOps, all these structures would have been filled to keep some state of the driver, right? Now, when you move these things into any other operating system, you will find it difficult to move the structure as is. So this is one area which we need to discuss and deal. So 3 to 4 topics, I don't have very straight answers. As you might have seen me jittering when I'm talking, there is one is the clock framework and second thing is the DevOps structure. These two things we need to understand how we can make it modular such a way that these drivers can be easily portable to another operating system, right? So I was saying all the benefits of Zephyr first, like you get CI/CD, you get Twister, you get robust framework. Like as I'm saying, right, like we start with RTOS bare metal driver and then we go into any kind of an end equipment, but then there is a very big vacuum in frameworks, whether it is TCP/IP framework or it is your file system frameworks, USB, Bluetooth, connectivity, WLAN, and these kind of things, right? There are a lot of gaps if you take any other real-time operating systems, but in Zephyr you have all these things solved and it is getting continuously invested and evolving, right? These stacks are getting matured. Now we can definitely leverage these stacks for other RTOS applications. And when you go into SBOM generation, CVE, CRA, and such things, Zephyr gives you a better hold on end equipment from safety point of view and CRA point of view. Now these things can easily be easily leveraged for RTOS based end equipments as well. And so definitely a lot of value add on Zephyr. Start your driver development by doing Zephyr first for RTOS engineers. Take those drivers easily and port it into any other operating system. So that should be the practice, and we are actually moving to that mindset in TI now. And earlier, like if you see, we have a lot of projects in Zephyr today from TI, which is following the regular approach where we have written the code for FreeRTOS world and we brought that code into Zephyr over a HAL and shim layer. But now we want to go do Zephyr native drivers first. And while I'm doing that, I also want to make sure like I have a path to move the driver to any other operating system, whether it is commercial RTOS or non-commercial RTOS. But I also want to keep my involvement in community, get the best things out of open source reviews and maintenance of the code for long term, handling of CV, CRA, and these things. Okay, so this is all ahead, and hope I have given some problem here and I have not solved everything here, but I have elaboratedly discussed the problem here, right? Open for questions.
Okay, I have so first I want to just say I do agree with the Zephyr first, and I'm not familiar. I'm not a user of Zephyr on there, or I'm a contributor to that. But part of like with Linux and the OS provides is the framework, like for the different drivers, and that's why like we as a community at Linux on average have smaller drivers than a lot of other operating systems because of all these frameworks that we have in the kernel. So when you see like common patterns, that's when you can add it to the framework. But if they're with this approach, and I do see value in that, but also they might be writing it to the lowest common denominator, in that maybe there might be some framework in Zephyr that's there, but maybe some other RTOS doesn't have it. So then they can't write the driver like that because of that.
Correct.
It's not really a question, it's just a comment on, because sometimes there isn't an advantage to, if you make it just Zephyr specific, you can use the Zephyr frameworks and everything else there, but then you don't get the reuse in the different platforms.
Correct.
So I don't know if you have a comment on that, or
fundamental thing is like I don't want to comment here because I want to move from all other operatings. Like I showed you the list of RTOS that I need to deal with, right? Like I want to move out of all those supporting 10 RTOS into one Zephyr RTOS, right? I want to move from all the traditional operating systems to a Zephyr-based RTOS operating system. But then these are the challenges that I just highlighted, right? Like I have all the investments made now, moving all those drivers into Zephyr native driver is very difficult for me. So I am carrying my HAL in a separate repo and managing that for Zephyr. But then I am not teaching the community or RTOS community to write a driver which is very open source friendly, right? That is the big mistake that we are doing here. And a lot of unvalidated code is getting into those vendor specific repositories, which we need to fix it, right?
Discussion over there. Just a quick reminder. So we are in the break right now. That is not a problem. We can keep going here. But if you leave, just be a bit silent so you don't disturb others. But we can keep going here with questions.
So in an effort to make things agnostic, presumably you're not using Zephyr work queues for threading and scheduling, right? So what did you guys do to, like, did you guys make your own thread scheduling or something else bespoke for that? Or how did you solve that sort of problem? If you're, say, like, you know, your software was relying on work queues, like what did you do instead?
Yeah, we haven't solved that problem yet. That is one problem that we need to solve when we move the driver from Zephyr into another RTOS. So today we are dealing, two ways to split this. One, like if I have written an application on Zephyr, right? If the application on Zephyr is following CMSIS standard, then you can easily move that driver to any other operating system if you are following similar standard. That is on the application space migration. Like you have an application written on FreeRTOS, you can move to Zephyr. That's one part, right? What we are dealing with is the driver layer, which is the lowest layer. Now, where is my diagram? Yeah, like we are not talking on applications and frameworks, not touching the OS hooks, but then dealing with only the driver portion of porting or migration or that part. But there are challenges there. I agree or understand what you are trying to say, but we haven't solved usage of work queues in other operating system.
Okay, cool. Thank you.
I had a question.
There you go.
Yeah.
Zephyr, maybe have you considered the other direction where if you, another way to entice is, hey, if you write a Zephyr driver, you can convert it easily to a Linux driver. Is that something that's realistic or is it true? Will that give any incentive to commercial entities to consider that as a reason to do Zephyr first? And with the AI being all the buzz, is it easy to have AI convert a Zephyr driver into a Linux compatible driver?
Possible. See, for AI conversion, you need to have a framework first, right? Fixed framework first. Today, by every every vendor is following their own methodologies. Therefore, you can't easily have an AI agent to convert a given driver into a Linux driver, right? If continuing to use Zephyr, it becomes more and more standardized, and then definitely there can be a way to convert a Zephyr driver into a Linux driver. It is possible, but through AI, definitely it is possible. And if we have a standard methodology to write any driver, I am adding an PWM driver or GPIO driver or a flash subsystem driver or a network connectivity driver. If I have a traditional structure or a standard structure and standard methodology, standard APIs, functions, and system calls, definitely it is very easy to port to Linux.
I mean, that is the crux of it, right? Because if you have everything standardized and so on, we don't have the flexibility we have in Linux right now, which I think most of the developers are actually enjoying and using. Brian was touching on that with the frameworks, right? So we identify problems across the board. We find ways to optimize that, like layers the code a bit differently and so on. And we are not able to do that if we rely on standardization. I understand that because, I mean, I've seen enough kernel abstraction layers and so on in my time to understand it is very interesting to on a vendor perspective to make one driver beat, in this case, Zephyr first and then export it over. But in the end, I mean, as I said before, I'm happy to see that going on, but I think only the time will prove if there's really something reliable other will actually can use and so on. And for me, it's not so much on the technology challenges you have here. It's more like how they're really adopting that over time. But I mean, that is future looking. I don't know about that.
Yeah.
Just a comment.
No, I think we will have more examples by next year. Like, as I said, we are starting that approach, we are on that path. More and more we unveil these kind of problems, then we will have some more data to share with the community.
I had one last question. That's it. No, so, if a vendor is able to get a certification on one RTOS, are they able to take that same driver and port it over to a different RTOS and keep that same certification?
No.
Okay.
They cannot keep the certification, but the advantage that you will get is once you get your driver, you will run some checks and tools like clockworks, you will do dynamic analysis, static analysis of the code coverage, and such things you would have done. Now, if you have written the driver in such a way, then if you migrate to another operating system, your code snippet would still carry all the fixes, right? Then when you apply for certification, definitely you will get advantage, but you will have to go for recertification anyways. But the effort would be minimal or zero.
So Jan, last question from you, and then I think we close it down for a break.
I was wondering if you have any license issues because of the Apache 2 license of Zephyr and other licenses in other operating systems.
For TI, at least I analyzed this. This was one of the key topics that I initially analyzed before giving this presentation itself. For BSD, right? We are carrying a lot of code on BSD. We are also carrying a lot of code from Apache in our SDKs. As I showed in my first diagram, though we wrote only bare metal code, but when we were bringing the frameworks, for example, if we bring in LWIP or we bring in a lot of these open source RTOS frameworks, they're all coming with different licenses, right? In the RTOS world today, we are already carrying multiple licenses to fix one problem or build one end equipment. So by taking this Apache code into any other free RTOS stack, or when I say free RTOS, I'm really not referring to Amazon's free RTOS. I'm saying open source RTOS stack. So taking this code into any other open source software RTOS stack is not a difficult thing, because Apache doesn't give you any restrictions in moving this code piece into another place. We won't have that legal challenges.
Okay, and with that, I would love to close it down here for the session. So we have 17 minutes for a break. Everybody enjoy that, and then please join us back. We have 3 more sessions coming up, and then the day's over. Okay, have a good break, everyone.
Thank you.
Thanks, Kasim. But I can't guarantee that, but at least make room for in my
So okay, then it's fine if you make a mistake with the problem. Yeah. The education is my solution.
Here several times, but people still, yeah. Also, sorry, was only LPC for like last 2 or 3 years. Anyway, so the point is that tell them what right already, like it's acceptable, if you think, as you said, like shit or good, but you like get more important. So that is the only optional. Often enough they come up with from projects. But that's okay. I mean, some people are flexible enough to like I can jump around and build that's okay, that is working. They won't have but I don't want to see like just or that like forcing everybody to like listen instead of like so we had this morning we had like a session with Rostad with all the students, and it was like very clear on that as well. It was like people on stage with me, like make sure that the action is happening, and if someone they don't know. Yeah, I know I'm coming to say yeah. Okay.
Yeah, I mean, it's when it takes like 5 minutes. It's not actually that
that is why I said, are they available? Here, I saw that you sent all emails like to make sure that people are aware of that. I mean, that's not the point. I mean, it doesn't help if you make them 5 or 6 times. It doesn't help. More like make them aware, remind them that interested here. Like, there's so many things that can give you just like people who are looking for the info, but then there's a lot more that you didn't expect, like getting stuff from there. all the people here that have like so much knowledge about it, like their own experience, but also like working with all this.
Let's see what happens.
Yes, there we go. You're the last session.
Yes, is. I'm the last session, yes.
Everybody wants to go to, yeah, sorry about that, but I had to somehow always, so.
Just.
It's not, oh, yeah.
It's not Snap, it's not like it's not that police. That's done.
Yeah, next, I mean.
No, it's just being behind it, yeah.
But, I mean, it could be also Bruno or someone else. That's, I mean. Bruno was a.
Yeah, it's 9.4, yeah.
I mean, that's more citizen. That's why
Just to be sure, thank you. That's.
Yeah. Look at the iron.
Like I say, the extent the first summer go backwards, marking.
Then I moved to near like no problem. And then I moved to things like we started together. Did something together. But then our work life, I mean, still the same location, right? Because I'm moving. But funny enough, he's looking for, I no longer build a house. But the thing is, but when it goes in work, I see Jan walks at a conference. I see him in my own hometown. So that's like really great.
Yeah, no, I mean, we. Yeah. Okay, we'll say that you.
Yeah.
Actually, yeah. Checkpoint employees. Okay.
Also, we need to mention that maybe also tips just
yeah,
but later I figure out how to do the trace.
Yeah,
there's some in line, so very useful. And I only in my local plan one static train point. And there I have some doubts, like does it make sense? Would it make sense to maybe try to push it upstream?
we do any fixed points in the arch.
Yeah. In general.
Yeah. If you look at later, just I can't any.
Is that like a reason for it? Don't do this or
so there's concerns about fixed points coming in the eye. Being stuck with like the detail of implementation being fixed. Or you could try if it would be more than enough, like if there were other local already.
no resistance.
Oh, there might be like people might do it.
Yeah.
I definitely assume that it would work because, like I say,
Yeah.
it would be using the article would typically do that. So I would.
No, understand.
Yeah.
So where I added that was just when Cap told me it was compared to
Right.
and there with the debugging it's really useful to see the
while you're making the
because I would maybe clearly inject this capital in sometimes I make mistakes with.
Yeah.
I think the ESR.
You know, like when it reports to teacher space, it's give you like the.
Yeah, it was just I think.
Yeah.
Minus 22 or something.
So what we, so what I was thinking of was like when polls. Yeah, you get a CPR, take me CPR. So you can tell if it was a GCF validation failure.
I'm more expensive than I'm still.
You could also get, yeah, it should only be for the comparison because if you fault due to an invalid GCS pointer, you have overrides that will give you a. Yeah, so that's, I guess I was thinking about, yeah, if you get a fault generated by the hardware, because this is a software generation. Yeah. Yeah, the stack switch. Yeah. So, that's the whole, yeah. It was more than like whether you had all the facilities you needed to hook everything, so we thought you did, but we weren't 100% sure, we never got like a confirmation from anybody, that everything was there.
Sure, and I saw that, your discussion.
Oh, yeah. Yeah, clone free, yeah, that's annoying, yeah.
That was, 50 threads or something.
Yeah, it's been going on forever.
But interesting,
yeah, it's annoying, like, if that got merged sooner, Savile has to being able to get in without the review, so.
Cool. I'm gonna go over.
Yeah, you get some shit. Yeah.
Thank you for your help.
No worries.
Be curious to see how many people come for the later sessions.
That's a break right now, but let's give it a moment, maybe start 2 minutes later or something. So, yeah, I mean, that's one of the problems. People are getting exhausted. I'm sorry that I scheduled you at that point, but it's fine. I had to make decisions somehow.
Yep, that's fine. I'm not planning to show all my slides. I left some ones at the end. I like discussions, kind of like my stopping point, and I just have like the other ones so in case like someone asks
That's
something.
fine. I mean, I just talked about that this morning. So whenever I do this, I tell employee comes 5 slides. That's good. What I don't say is like, if you have more, then it's fine. I don't mind that as long as you really work with the audience here to be interactive. Sometimes it's difficult if you're so many slides, even if you want to be interactive, but you don't have a good stopping point, right? So you need to like stop at specific times and look, okay, this I described that so far, any questions, any comments, and then to get that started. Because normally people only start really with the slides because they're polite and everything, they want to wait until it's finished. And if you're like, when you're slides, that is not going to happen in time.
Yep.
So that is a problem I saw a little bit with Sarabana and I mean, they have the actions, so it's all good, all fine. But if you come with too many slides, so that's why I'm only, whenever I have that, I say, oh, bring it down to a few. I understand, people have that. They have the slides already, maybe for something else, explain it, or want to have like backup slides and so on. I fully understand that one. It's more like, if you want to keep it on the discussion, yeah. It's the point. I was not my explanation here.
How long have you been in Japan, in Tokyo?
Right, yesterday.
Okay.
So not that long, but I will take a bit of time this holiday. I take the Shinkansen to Hokkaido, up north away, and I go to Sapporo, bigger cities there, and that will be on snowboard on Sunday.
I am skiing but I'm going to Aqaba.
Phil already told me that. He told me that we are going to. I'm doing that. We're going by 2012 or so.
Yeah. Yeah.
So Sunday.
Sunday. I'm doing Sunday and Monday.
And the thing is, I wanted to see the stars when the correct families of
Yeah.
So I wanted to like start it like going up there Saturday, playing Sunday, and Monday.
So are you going to the far north or are you going to Aqaba?
No, I'm going to Hokkaido, Sapporo, and then I go just to the Sapporo.
Stefan, should we get started again?
Yeah, but there's not that many people here yet. The break is spilling over. Let's wait 1 or 2 minutes. But I can announce that to the internet. You're right. Sorry for that. Okay, guys, let's wait 1 or 2 minutes for all the people to come in, because right now we have like 7 people in the room. So not even the speaker is not even here. So let's wait a moment until the break is over. Sorry for that. Let's try like 2 minutes or so. let's say 1 or 2 minutes.
Right.
So the slides are loaded. Back and forth over the cursor keys.
Left and right, right? Yes.
Okay, so I think the break is still going on a little bit. So I think maybe a few people will sneak in over time. But to make sure that Sebastian actually has his half-hour time slot to get started, I think we would be a good time now. Okay, so the next session we have is from Sebastian. Yeah, let's give him a welcome and then we can get started here.
All right. Hello, everyone. So the title might look quite heavy. This session is about the Type C port manager, which is used by some of the embedded boards, and especially those boards that do not have any other power source. So we are effectively interested in these 2 pins from the USB-C connector, which are called CC1 and CC2. One of those is used to communicate using a protocol called power delivery, which you may have heard before. It's kind of a misnomer because it's not just used for power delivery communication, but also for, let's say, configuring the USB-C alternative modes. So it's kind of like a USB-C control protocol. And to handle these pins, both the source side and the sink side usually have something called a port controller, and there's 2 different variants of those. Option 1 is port controllers, which work autonomously, so they will handle most of the things by themselves. This setup is usually found on laptops. That has the advantage that it works even if the system is off or in suspend, because, well, as the name says, the controller works by itself. And then there's other chips which do not work autonomously. So the operating system or something needs to tell those chips what they should do. And this talk is about the second version of those chips, which in the Linux kernel is handled by something called TCPM, the Type C port controller manager, which is effectively a really big state machine. Right now, it's about 8,000 lines of code. And as I mentioned, the interesting part is boards which are powered over a port using this kind of chip and not having any alternative power supply.
So does the chip run no firmware at all? So is it like, or is it like how they are? So you mentioned the state machine being in the kernel. So there's no state at all on the chips or so?
Exactly. So the chips are basically dumb. There's no firmware on them. Some of them have support for automatically acknowledging messages. So the protocol works that you send a request or send a message to the remote side, and then it needs to be acknowledged by effectively sending back a checksum for this message. And some of those chips can automatically generate this response that they received the message and send back the checksum. Not all of them can, but most, I think.
But that's a hardware feature. You can.
Yes. So they do not have any proper state. One example of such a system is the ROC5B. It's not the only one, but yeah, that's the first one that I came in contact with. So the setup roughly looks like this. There's the USB-C connector, which can be used to power the board, which then takes the V-bus, which has the voltage to the system regulator, which then supplies the system. And then the CC lines go to a chip called FUSB 302. That's a really common one, and that's one of these dumb chips which does not have any firmware running on them. So it must be told over I2C what it should actually do.
And this chip specifically can do this automatic acknowledgement, but it also must be enabled first. So what happens now is if you plug in a power delivery capable power supply is that it will give you power. That part kind of happens passively if the resistors are there. The Raspberry Pi is famously known like the old one that they forgot those. But if they are there, it will give you 5 volt, and then it will start sending these kind of messages, which tell the sync, which would be the development board, what kind of voltages are available from the power supply. And it does this for some time. The specification says that after about 5 seconds, the source assumes that the remote side is not power delivery capable. So at that point, it will say, okay, let's just stick to the 5 volt. No.
Yeah, I see the problem already. I mean,
yes,
that is not a good thing.
Now, if the sync starts sending the power delivery messages later, the source sees this as an error because it expected this message to receive much earlier. And the error recovery for power delivery is, let's do a hard reset. And a hard reset means let's remove the power for a short time. So if we go back to the ROC5B and we enable the FUSB 302 driver in the kernel, and we put in the cable, the bootloader will, well, first of all, the DRAM will be initialized by some kind of pre-bootloader, then the U-boot will start over U-boot SPL first, then the normal U-boot, then maybe it will fetch the files from the network, whatever. So it takes quite a time before the kernel FUSB 302 driver is probed. Usually it takes longer than 5 seconds, which means if everything is following the specification, the board will just start rebooting, well, forced rebooting by having the power removed. So obviously that's a problem because this happens if everything follows the specification.
Who's in charge of the time here to make this hard reset? Is that like the chip itself? Is it counting?
Yeah, so I mentioned the state machine running in the kernel for the FUSB 302. There's a similar state machine running in the power supply, basically. And
so the reset, the reboot is only done when the message is received too late.
yeah, so if the message is received too late, the power supply state machine runs into an error state, and then it will do a hard reset.
And if it does not receive the message, then it will probably just stay in 5-volt default mode.
Exactly.
Okay.
So by not doing any power delivery at all, the system will run at 5 volt, and the amps provided depend on the resistor.
I mean,
in case of the ROC5B, that means it will run, and then it will still turn off because the amps provided will not be enough for the CPUs running at the high frequencies.
So you either get it done in 5 seconds or you're screwed.
Basically, yes. So there's a couple of solutions to work around this. Well, one is use different hardware, but it's kind of too late for that. There's a couple of boards available which have this kind of hardware design. For the ROC5B, I know that a huge amount of them have been sold, so we need some kind of solution. Then obviously one solution would be let's boot the kernel faster, which might work, but not in all scenarios. So that's not really a good solution. Then an option would be to fully avoid doing this in the kernel at all and kind of move this to the firmware, which probably works. I haven't really tested it. It's quite a lot of work. It means that the firmware would become board specific because, well, the firmware would need to know that there's an FUSB 302 on this specific I2C interface. And right now for Rockchip, the firmware is not board specific.
But that's, you mean the firmware that's
well, the really low-level firmware, because where does the bootloader fit, like U-boot? Is it also? Do you also consider it part of the firmware?
I will come to U-boot in a moment. So the idea here would be to move it into the trusted firmware A.
But if you do that, that would also mean that you need to synchronize state if you're handing it over to the kernel later on. And
well, the idea would be to fully handle it in the firmware and then have some
it
interface between the
in
firmware and the kernel.
Okay.
The last option is indeed to try to do it earlier in the bootloader, which means we need to add the full state, well, not the full state machine, but some kind of state machine in the bootloader. That is what the vendor kernel, the vendor image actually did. And I ported this over to upstream U-boot, which landed like last year. It's effectively the kernel state machine, but from a few years ago. I decided not to go to the latest version because it adds a bunch of features which are not really relevant in U-boot. For example, the audio auxiliary mode is not that relevant, and the state machine is already complex enough. What this means is that U-boot first initializes everything, which avoids the 5-second problem, and then Linux reinitializes everything. Something specific about how the power delivery protocol works is that it has an increasing message number. So this is a kind of a problem because Linux wouldn't know, like, okay, how much communication has been done by U-boot and which state is currently in. And to avoid all these issues, the Linux driver starts with a soft reset. And then the specification says that the messaging starts again at, I don't remember if it's 0 or 1, but like at the first message ID, and it should keep the power at whatever has been negotiated before, and then the kernel can start at the initial state with its state machine. Yes.
How does the kernel know that this U-boot has initialized PD and the driver should do a soft reset?
Doesn't the kernel always sends a soft reset?
Okay, thanks.
So it sounds like everything is fixed, but unfortunately that's not the case because a lot of those power supplies are not really following the specifications so closely or leave out some features. And this is especially around this soft reset. So what is supposed to happen is that after a soft reset, the power supply should start sending these source capability messages again, and the kernel is waiting for these. And when it runs into a timeout, it starts doing another soft reset. And when the soft resets are not enough, the kernel will send a hard reset, which is really nice because that means the kernel basically kills itself. Obviously, we want to avoid that. So I introduced a new state, which, well, basically when it runs into this timeout that the capability message has not arrived, it will send an explicit request to please send me what you can do. And like there's an explicit request message asking for the source capabilities, and then continue on with the state machine. This is a slight deviation from the specification because the specification describes how the state machine should look like. It does not describe this, but it works around the issue with many of those power supplies that are not following the specification properly. And additionally, I added an error print that when the kernel does a hard reset and it thinks that this might kill the hardware, it will print this error. The reason for that is that it's quite hard to know if this actually kills the hardware because we don't know if the board is actually powered from this USB-C port or if there's any other backup power source. Like the board might be powered from power over Ethernet and the USB-C is just there.
So you may want to send the hard reset for cases where you're powered externally.
Right. So the hard reset effectively is then necessary to recover into a known working state, which is kind of a problem.
So the hardware reset also resets the power sink, the power source, or how?
Yes, so the hard reset can be started from either side. So the kernel can ask for a hard reset if it sees that the connection is not consistent. Yeah. And also, both sides can ask for a hard reset. The initial problem that I described with the 5 second, in this case, the power supply will start the process of doing a hard reset. In case of the capabilities, the source capabilities not coming in, the board, like the ROC5B, the state machine that we are running, will notice, okay, something is wrong, let's go into a hard reset. Which, when the board is powered from USB-C, will effectively tell the power supply, please remove the power for a second or two, which then means the board will be reset.
And what if I power the board from some USB power supply which just delivers 5 volt at enough current to run the board, but without any USB PD capability?
Then everything is fine, because then you're not.
But then you're
PD.
expecting this message from the source, or not?
No, in this case, nothing will happen anyways, because the hard reset is basically using the CC pins, and if you're not using them on the source side, nothing will happen anyways. But the state machine explicitly has states for we are not doing power delivery also on the kernel side.
This is also specified how high you can go up for 5 volt.
Yeah.
How much? I mean, I'm not sure. Is it specified? Because
yes. I mean, if you're completely dumb, I think you can go to 5 volt 3 amps, if I remember correctly. It might be 1.5 amps. I'm not 100% sure.
Yeah.
Right. The thing is,
I know that part, but I'm wondering, because you're talking about spec compliance here, that I'm wondering, what is going on with that side.
The thing is, on this specific board, you usually want more than 5 volt. There's an onboard regulator which goes down to 5 volt. So if you're already supplying 5 volt, this will go under 5 volt effectively. So you usually want at least 12 volts, and you can't get that passively. For that, you need power delivery. Also, again, on this specific board, the Type-C port is capable of data transfer and DisplayPort alternate mode. If you want to use those, you definitely need to have something that speaks power delivery. And then it gets even more complicated, because you need some kind of hub in between, which is powered, which modifies the power delivery being spoken to the power supply. There's a man in the middle then from the USB-C hub.
I don't know if you come to that, and I don't want to steal your thunder, but this really looks like something that should not be in the kernel. So, I mean, we talked about, touched on that with TFAA as a firmware side. This really looks like something that need to run on a separate part, where you can then expose it in whatever API you're having. If it's use UCSI or something, what's the specification for that? But I mean, if this is the API or something else, it doesn't matter, but it needs to be something that is handling this part. Because right now it looks like you're papering over all the different issues. Get it kind of working, but it's, from an architecture point, that is not well.
Well, so I don't really have any good solution. I have some ideas. One of them is, I think it would be good if we can try to avoid harder not to do the hard reset, which means having a better detection of affected systems, which is not very easy. Right now, I'm relying on the self-powered device tree property, which exists and is properly documented, but I'm really sure that a lot of boards are not adding it, even though they are having self-powered connectors. Also, it's not always easy to figure out if the board is self-powered. For example, again, exactly this board, it could be powered from a GPIO pin or power over Ethernet adapter. And there's nothing telling the system if this is the case right now.
I can't believe it. There's no measurement possibility there to see current flowing into second input.
No.
Damn.
I mean, on some systems, you know that there is a backup power source. For example, if you have a battery, then you know, okay, there's a battery, then the system should be safe to do a hard reset. But there's definitely systems where you don't know this for sure. That's why right now I'm only doing a print, but then still do the hard reset, because the specification says do the hard reset. And on boards that are not affected, you definitely want to do it.
So could you persist I did a hard reset, did we reboot? Did do it only once, possibly?
I guess that would be an option, yes. I mean, it requires having some
it's nasty,
storage and... Right. One more.
This is also adding to the list of things you just papering over. I mean, so I'm sorry, I don't want. I mean, I understand that you have like you want to get a working solution with what you have there, but
well,
it
I
really
mean,
feels like.
I mean, the state machine issues itself. It's also something you have if you move the state machine somewhere else.
That is
right?
true. But I mean, I agree on that part. But still, the other things you can get solved. Right?
What we have right now would be compliant to the specification. The problem is that a lot of, especially the cheaper power supplies, they don't closely follow the specification. They have been tested with, let's say, a mobile phone, which has a battery, so it does not really care about the hard reset in the first place. But more interestingly, most systems do not use the soft reset and then assume that things start again. So ideally, we would want to negotiate everything once and then keep it at that point. That's why I listed maybe we can hand over the state from the bootloader over some device tree properties or whatever.
Just so I understand, in the autonomous case where it's all happening on the chip,
yes.
Is there no communication with the kernel, or do they still have to implement parts of the protocol?
It depends. Usually there still is some communication because the kernel is interested in what kind of alternate modes are supported. Especially if there's like DisplayPort alternate mode, you need to somehow get the graphics stack informed about it.
But in terms of the actual power delivery happening, does the kernel need control over that, or can the chip do it all with the firmware that's running on the chip?
Could be fully done on the firmware.
Okay, that seems to me like a more robust solution than having to do this whole kernel communication. I'm wondering why the people who make these chips don't. Is it just they don't want to put the effort into writing the firmware and want to kick it down to the kernel? Like what? Or they want to sell chips and
Well, so the FUSB 302 is like a really cheap, very simple chip, right? So if you have something with a microcontroller, this chip might be really useful because then you might want to implement the state machine yourself to have like fine-grained control. The problem is that vendors started putting this chip on single board computers.
And so that's not powerful enough to run the firmware that's needed to do everything.
This chip does not have anything to run a firmware on.
Oh, great.
So that's the problem, right? There's no firmware for the chip itself, and yeah, you're missing that part.
One more comment, I would say. So regarding the idea of handing over the state from the bootloader, aren't there any activities? I think I saw some people presenting something like a splash screen, so handling the display early on and then handing that over to the Linux kernel when it boots to keep the screen consistent. Isn't there any activities? So there some infrastructure to handle state over to Linux already?
I mean, for different use cases, people do that, but there's no common infrastructure to hand that over. I mean, you have that for all kind of like hardware in it you want to do, and you don't want to reset the registers or something like that, or like make sure the memory stays for like your splash screen or whatever you have, right? There's no common solution for that, at least as far as I'm aware of. I mean, there are different That is mostly something that is more done on the productization level instead of like on upstream itself, I would say.
On that topic, what happens in the either the soft or hard reset case if you are using your DisplayPort alternate? You lose that too, I guess, right? If your bootloader initialized your display and was hoping to pass it off to the kernel, but then your USB-C gets reset, you're going to lose your display then too, right?
Yes, you do. Right now, the state machine in U-boot is not capable of the DisplayPort alternate mode in any case, but if it would be capable of doing that, you would lose it, I think.
Coming back to the TFA thing I was poking around it, the reason you're not approaching that is because the complexity to get it all set up, right?
Well, there's the complexity bit and the bit that it results in the TFA becoming board specific instead of SoC specific.
Yeah, I see that.
Which kind of is again complexity, of course, but
yeah, I can see that. I mean, I see that you worked around a few of these things and you can get something working for most of the use cases you're having. And I don't know what these boards are used for, and if they're used like, it's more like catering the maker market, or like if that really like products they want to bring out or so, because to me, this looks like if there's a product and it's being deployed somewhere, that's just like a ticking bomb that just waits to like go into a reboot loop and not working successfully. So yeah. When, as I said, that's just a comment from my side. I would really look into something that is like a separately run firmware, whatever interface you have to the kernel that can be seen or so. Okay, I think we have like room for like one or two more questions if you have some before we need to switch over. Going 3, going 2. Going 1. Okay, so thank you, Sebastian. So the next session we are having is from Brian about clocks. So everybody make sure the time is correct. There we go. Right on time.
Okay. Awesome. Hello, everyone. Do hit spacebar for the next, or okay, there we go. Okay. So just the key questions I want to answer from this talk is 1, how do we build a consensus across the clock tree? And 2, do we need to keep backwards compatibility with the existing behavior? So you'll see that in a minute. Oops. So, okay. So quick introduction. So the common clock framework, it's expected that to keep the rate stable. So like when you just do clock set rate on some clock and some new rate. However, when clock set rate parent is invoked, there's several issues where sibling rates can be changed. So clock consumers, they don't know about the clock hierarchy or sibling clocks or the type of clocks that are used. So quick example. So let's say if we have a parent clock, the parent clock can do any rate, and then you have 2 children, and all the clocks are initially at 24 megahertz, and it's just a simple divider, the two children. And one of the children requests 48 megahertz. The parent is not able to do that rate right now, or the parent is not in the expected state. It's expected rate at the moment. And so the parent rate has changed, but meanwhile, the other sibling, the existing behavior today, it keeps the same divider value. And so the sibling clock has changed from 24 to 48 megahertz. And really what it needs to do is the parent in child 1 needs to change to 48 megahertz, and then child 2 will retain the 24 megahertz, but have its divider updated from 1 to 2. And the second issue is that there's when a child decides that it needs a new parent rate, there's no negotiation with the siblings about what that rate should be. So if we go back to, you have a the parent can do any rate, and then you have two child clocks, and they're just simple dividers. If one child requests 32 megahertz, and then the other child requests 48 megahertz, the issue today is that the last one that comes in is the one that actually sets the parent rate on there. So in this case, the 48 megahertz was the last one that came through in this example. That's what the parent's set to. And then child 2 also gets set to 48 megahertz. So one possible correct solution would be to set the parent to 96 megahertz, and then you can have the 32 and 48 with their respective divider values. So a high-level proposed solution. So to fix some of these, we're going to have to introduce a new rate negotiation logic. But some boards are unknowingly dependent on this existing behavior that the clocks are set on there. So the proposal is that we support a version 1 and version 2 rate negotiation logic in the clock core. And then we add a new member to struct clock ops that asks the provider about all the possible rates for the V2 negotiation. And the clock core then, it already knows the topmost clock it needs to change. So it goes to that topmost clock, and then it works its way down, and it'll pick the first rate, the first set of rates that's acceptable to everyone in that tree. One of the issues when I talked to Stefan before was he asked me not to add anything to struct clock ops. But right now, like the clock core doesn't know, and I don't think it should know about the internal state of some of these various clock providers. And then in child clocks right now, when they set the parent rates, it has to know some of the internal state about and details about what the parent clocks are. So for this V1, V2 negotiation logic, I propose if we do this V2 negotiation logic, it's only used if that new member's added to struct clock ops. But one of the problems is that there's multiple clock. So not one of the problems. Multiple clock providers can be used on the system, and so it allows for a mix of you can have some parts of the subtree can have a version 1, and then whereas some other parts of the subtree can have a version 2, and then but there might be a problem where when we introduce the version 2 that you're having to troubleshoot whether or not it's a problem with this new negotiation logic, like moving to version 2 or version 1. So introduce a new kernel parameter for the V2 negotiation. That way you can turn this off and go back to the existing behavior, just to be sure that we didn't unknowingly break a board. But if we do it this way though, you're still moving a large number of boards all at once. So like clock fix factor or clock divider, like if we add a negotiate rate ops to that, then large numbers of boards and SoC vendors are all dependent on that, and they're just moved in all at once. And similarly, like when one vendor adds it to their basically large portions of their drivers are going to get moved over to V2 as well. We could add a flag and clock init data or somewhere else. We could default the module the kernel parameter to off, and then at some point in the future turn it back on. But then it's like, when do we do that? Will anyone actually have used this and migrate by then? So anyways, I'll pause there see if there's any discussion, questions, or
so is the existing behavior, the current negotiation, is it a problem that
yes? So it affects. So it depends on some drivers. So like some drivers that require precise rates. So like DRM sound, it shows up in those cases there. But some other drivers where like some subsystems, they're able to handle it just as long as the clock is ticking and they're all in sync, it's fine. But It's the subsystems that need the precise rates where it's a problem.
Okay, so
And in fact, I have, we're not going to go through the patches, but yeah, right here, there's just I have a link on the slides. There's just like some example, like patch or where people are have been trying to work around this issue over time.
So, I mean, in a way, so you talk about, the potential to break existing boards.
Mm-hmm.
I mean, this seems to me like, this change is affecting user space. I mean, I know it's happening inside the kernel, but it's, the problems manifest themselves. Well, no, I guess they're not because they're drivers.
The problem is that if you have, we can't just willy-nilly just change it in the core to put the new behavior, is that like you have one board that works and it works today on there with this, and then, but they don't know that they're unknowingly set up these other clocks that were changed on their behalf. So if we fixed it so that it would do the correct way, those other sibling clocks are not set up in the way that they should be, and then you run the risk of that. Now, I don't have the data on how often that's going to occur. I don't think any of us has that, but it's it's a possibility.
Is the subtrees, is that a way to mitigate that, or be having like, one version and one subtree in a different?
I don't think that's gonna really.
Any good
Have you
feeling on the
considered
number
adding?
of affected systems?
Sorry.
Okay.
Go ahead, Maxim.
Oh, so I start. Have you considered adding loud warnings in cases where sibling clocks, which are active already, get their rates changed?
We could do, yes, we could definitely do that. Yeah, that's definitely one option. That probably is something that we should probably look at doing.
That would at least be a way to reduce the problem for a future change.
Okay.
If people fix their parent clocks with assigned rates or something.
Because as part of like the patch series I have right now, I do know one block of code where it triggers this.
Any good feeling on the number of affected systems? And the second question related to that, if a board is broken by this, how does it get fixed? Is it a change to the device tree or something else?
It would be some of it could be a fix in the device tree just to make sure that the clock is set to the correct value. Yeah, what was the first question? I'm sorry.
Any good feeling on the number of boards that would be affected?
Oh, I don't know.
Because if the change to fix it is in the device tree, that's problematic. If the change to fix the problem would be in the kernel, then that would be a usual kernel regression that we could then fix in the kernel. But the DT ABI stability could cause problems.
Yeah. So yeah, most of it.
Have you considered, for the cases like you mentioned where setting like a clock fix divider or the very commonly used clocks could cause issues, using the negotiate rates callback to apply some sort of filtering on whether, like, basically emulate the V1 logic using inside the negotiate rates callback where necessary?
Oh,
something like,
I don't know. Yeah, that might be ugly.
Or not necessarily, emulate the same, but basically have a way to, filter, like, based on the, the board information or some other information you have, whether, reject all changes, right? For example, or accept all changes.
Yeah, I see what you're saying. In that case, we would do, if we wanted to do that, if we added it as a flag, if we added a flag on the clock, and then whether or not it was supported, but then we'd have to get that in the init data somehow. I don't know what that would look like. I guess that'd be in the macros with more macros. Stefan would love that.
There's a question coming from, I can't read the name from here, man, I'm getting old. Dan, go ahead.
So I'm wondering if in the V2 model, if you have a sibling which needs to get its rate changed, for example, it's an audio interface, it would need to change its own dividers to end up with the correct output rate in the end. So drivers supporting this new model would need to have some way to cope with upstream clock changes at any point while they're operating. Is that something you find realistic?
What was the last part of the question? Sorry.
So do you expect the drivers connected to those clocks to be able to handle runtime clock changes? Because at any point, a sibling clock could request a new rate, and then they would need to reconfigure at any point in time. And I don't see that could be done in an atomic way. So you would need to stop somehow, reconfigure your internal driver state, and restart after the clock tree has changed. It seems to be a lot of complexity.
Yes, and that's what's done to the, Stefan, you can correct me on that, but that's what's done today. It takes the global clock lock, and then it sets those new states, and then that's when.
So this problem, like you're talking about consumer drivers, right? Like some UART driver, for example. Yeah, so like either the hardware itself can do it in a glitch-free manner, so it can switch the clock or change the divider, and there's no glitches, or it has to be turned off. And so there's only two options, really.
Yeah, one back there.
I think the situation is, say, where you have to like double the parent rate and then you have to double the divider. That change itself is not atomic, so the rate is going to temporarily double. So like, do you call like the clock rate change notifiers, even though the rate isn't actually changing or shouldn't actually be changing, you know, at the end of the process, but you still call the rate change notifiers so the driver can handle that? And then do we need more rate change notifiers in drivers that currently don't expect the rate to change because the parent rate isn't going to change?
My recollection of the way the notifiers work is that you're not going to get it until after it's done, after all these on there.
I think there's both a pre-rate change and a post-rate change.
Okay, okay.
But well, I guess maybe the point is that you might need more of these notifiers for drivers which previously didn't need them.
I would like to go back to the previous comment about the warnings. So if you ever implement the warnings, pay attention that some platforms panic on warnings. So maybe you shouldn't panic them. And then still they should be.
Oh, so go back to a specific slide? Or?
No. The question from Maxime, I guess, was that maybe you will implement warnings to tell that your clock hierarchy is mixing the method. So if you warn, you might panic the machine. There is a panic on warn, right? And Android uses it, right? So you shouldn't. Another thing is that if you ever do the warning, it should be understood as early, because I cannot imagine that I plug them some type C, whatever display port, and then I get a warning, right? And then if I type different display, maybe then I get a warning, right? So there should be the clock tree should be analyzed very early if you want to ever warn. That's your mitigation of the problem.
So I'm not sure this is going to be a real problem, but if the parent comes from a device that has an OPP table that would contain different, let's say, power requirements for a clock rate, can we account for that during the rate switching of the parent?
Yeah.
So I don't know if you should really focus too much on this generic clock stuff initially. I think you should probably try to just solve your real problem, because the generic stuff, like, we're not going to know in those drivers that, oh, I have a sibling X, Y, or Z to actually, change or even or I am a sibling and I need to not change. So like that kind of information is not really going to be there. So maybe what you should do is instead just focus on a particular SoC and see if you can have it all coordinate the rates between siblings inside some clock controller.
There's actually,
on that.
we're not going to dig into the code too much. There's actually one part in the clock core that's like that problem one, that it's actually like this. The problem one, you can solve it with this, because that lists two problems. The problem two is the no rate negotiation with the siblings. But the problem one of just the dividers like suddenly changing underneath them, if I do this patch to the clock core, then problem one goes away. And that's just from when when that is from when the code was first introduced and the clock core was first introduced to the kernel, like back in 2012.
Sure. I'm just saying that you don't want to, I don't think you want to focus on these basic building block stuff.
Okay.
At least initially. I would not.
So just pick a SoC and.
Right. I wouldn't worry about them, because like we're all going to have to work on that problem together. And it'll require some modifications to like the clock divider, for example, to say, oh, I don't want this rate to change if my sibling changes. And that sibling change causes my common parent to change, or my common ancestor, really. Right. So like you have to add that feature to the clock divider to say, stay at what rate you are. We never guaranteed in the clock API that, oh, you set that rate on that thing and that stays there. Right. We just let that side swiping problem exist.
Mm-hmm.
And that's been how it is forever. Mm-hmm. So maintaining that behavior is not hard, right? You just keep the broken behavior or the existing behavior.
Mm-hmm.
I'll bring it over because your neighbor was skeptical last time.
If you're trying to, see how many boards you might break with a change like this, I guess one possible thing you could do, you're asking like, oh, if we turn it off by default, how will we know when it's safe to turn on? You could like run both paths in parallel and say, oh, if you turned on the V2, you would get this different change, or like have some sort of way to simulate what the difference would be. That way someone could see if it's likely to break their board.
Like this right here, it'd be in kind of this block. It would just detect. That'd be the main place to check to see on this area. There. But that would only do problem one. It wouldn't do problem two. But problem two, you just kind of would know, well, I didn't get the rate that I wanted. It'd be possible, but you would just get a rate that may be close, may not be what you want.
The first problem is you need to decide if you're going to call determine rate on siblings. Right. And then when you're a sibling and you're being called for determine rate, maybe you need to add some flag to the clock rate request saying, hey, this is a sibling clock and it wasn't in the original path. Right. And so now this is the V2-ish behavior, or you're a sibling and I want to know if you can accept this new rate or if you cannot. And so if you cannot, that's the old behavior of V1, right? So if this flag is set in your determine rate, then you know, okay, I've not updated any of my code, and so I just assume it's going to take whatever new rate it's going to be.
You talking about in the clock rate request structure?
Yes.
Okay.
Yeah. So like you do that change, right? And then you don't have to do anything different. You just call determine rate on the entire subtree once you walk up to the top and you find out what's going to change.
Mm-hmm.
And so then I think you can do all the changes completely seamlessly in that design. You just have some flag in clock rate request. And then now you're calling determine rate for every single clock in the subtree, right? And then once you do that, then you can figure out, okay, this clock needs to change here. And so the sibling clock, right? Like your A and B, right? That sibling changes. And so it opts into the new behavior because the new flag is set. And then it says in determine rate that I have to be set to this frequency, right? So call my clock set rate function, which is not happening either for the sibling. Right?
And you're talking about doing this for the clocks that we need precise rates for. So like DRM and sound.
Yeah, we'll have to do it for any driver that wants to opt into this new behavior.
Okay.
would that be checking the final rate or checking for transitional glitches? Because if you care about this stuff, you probably can't like your audio. If the clock's running, you absolutely will not be able to tolerate a transient change in the rate for any period of time. It would be immediately obvious to end users, and I imagine similar things true for DRM.
Both. I mean, it's up to the SoC clock provider, right, to decide what they want to do. So it's not like a either or. I agree. Yeah, like the audio will not want to change the rate, right?
But I think for some of these situations where we're thinking, oh, well, you know, we might have transient rate changes, but for like the problem one case you're talking about, there's already a rate change, right? Like we're not adding more rate changes. For problem two, where we do the rate negotiation with the parent, that might add more rate changes. But for problem one, the rates, like we're not causing any more transient rate changes or causing any more permanent rate changes than were already there. So that's not a new bug you would be introducing with this change.
Yes, correct.
How many cases do we have when we need to reconfigure the parent like that, where the clock rate of the parent will be fixed for the lifetime of the system compared to needing to change dynamically? Because I do understand that one of the problems you're facing is you end up having the wrong rate when two child clocks will request a rate and then another one. But maybe in a large number of cases, you could assign the rate of the parent in the device tree, for instance, and then those problems would go away.
Yeah, correct. If you use the fixed rates in your tree, that would fix the problem. Any other questions? Okay. Well, thanks for coming.
So to surprise, we finished 5 minutes earlier. So we have like wait a few minutes here before we go over to Marek, just to make sure that the schedule is like for everybody like listening in from remotely. So but we can get started here. So thanks again, Brian.
So.
Just now, we're just complete opposite. Still get up an hour, sleep an hour and a half, wake up for 20 minutes, then wake up again.
We sent them.
I've been on some boring podcasts, so I'm gonna fall asleep pretty quick.
I tried that too, but I had a hard time.
It can't get worse. Like this thing we see.
I have but one question. How do I flip through the slides? Left and right arrow? I guess so.
Give a minute until it's 6 and then you can.
It is 6 now.
It is now.
It is now.
Okay, so hello everybody. We're going to the last session of this of today and for the whole day, and everybody's eager to get to the social event. I know that the beer is waiting. Everybody's like, Christoph looked at me like, beer? What beer? Okay, so Marek has a last session of the day, firmware ABI stability. He taught me only like a few slides, so really bring in your questions, comments, and so on to make that an interactive session. Thanks.
Okay, yeah, so let me start. Indeed, I have only a few slides, so I depend on you, the audience, to actually discuss, because otherwise, this will be a very short presentation. And that's the plumber's spirit, that's right. My name is Marek Vashud, and I do bootloader stuff. And today I'll talk about firmware ABI stability and the problems we have in embedded systems. Yeah, pretty much embedded systems, because these are the systems which are being hit by this right now. Let's see. Yeah. Okay, so problem definition is basically this. In the embedded systems, in the last few years, it just started happening that the bootloader layers started exposing some sort of services to the upper layers. By upper layers, I mean the Linux kernel. It could be an RTOS, it could be something. By services, to make it a little bit easier to understand, I mean, for example, on ARM, PSCI, SCMI. These services allow the upper layers to request start of CPU cores. They allow the upper layers to manage clock, power domains, resets, and so on. And this is done by the upper layers. That means Linux, RTOS, whatever. By calling these services, that means invoking some resident bootloader functionality, and the bootloader functionality then does the actual hardware operation. The issue is that this establishes some sort of an ABI requirement between the bootloader layers and the higher layers. That means the Linux kernel, the RTOS. Now, one would expect that this ABI would be stable and immutable. And this is actually the case with, for example, UEFI. With UEFI, the design was done very well in that the ABI just doesn't change. And it's set in stone and there are no issues. But on the embedded systems, on ARM, maybe also on RISC-V, problem is that sometimes vendors modify the bootloader layers in such a way that they break the ABI stability. The ABI is not really stable. And they break it in two ways, give or take. One of them is they extend the protocols themselves. That means they add new commands to the PSCI, which are not in the ARM standard description, or in a second way, if, for example, SCMI has some ID lists, they maybe don't retain the stability of these ID lists. So when you update a bootloader, suddenly some IDs means something else. Sadly, this happens. Yeah. And yes, of course, this causes chaos. The implication of this is twofold. The implication of the first part is that if some sort of a core kernel driver depends on the non-standard extension, say to PSCI, this kind of a patch to the core kernel driver cannot be upstreamed. This will just be rejected because it's some sort of a vendor-specific extension, and it's just not going to land in Linux kernel upstream. Since other drivers then usually depend on such kernel drivers, on such core kernel drivers, this non-standard extension then transitively blocks all the other driver upstreaming. That's not good. The other problem is that if vendors cannot use stable ID assignment in the firmware, say like SCMI IDs, then it is not possible to design device tree bindings properly because these SCMI IDs are often encoded in the device tree bindings. And if you cannot design stable DT bindings, then you cannot really finalize your drivers, which will then use these bindings, and you cannot upstream those drivers, and you cannot upstream your device tree, and basically your upstreaming completely grinds to a halt. It's catastrophic. Now, I've been pondering about multiple solutions, although I don't have a good one. This is where you come in. There are two potential partial solutions to this, which I came up with. One of them would be to take the bootloader layers, which actually provide this unstable ABI, and boot them together with the Linux kernel, or potentially together also with the RTOS, which is the consumer of this unstable ABI. This solves at least part of the problem, because then if you do a software update and you update all these components together, then you will at least be sure that the Linux kernel will boot. But it doesn't solve the upstreaming problem. The other alternative, which may be kind of complementary to this, maybe, is that the firmware and the Linux kernel DT bindings and the drivers are basically developed at the same time. And when something is tested, then this piece of code is added into the firmware layers, the DT bindings are finalized, the driver is finalized, and all these components are developed in an incremental fashion. Maybe this can be also combined with the previous point where the firmware and the kernel is put together. This would at least solve the problem of the unstable ID assignment, because the IDs would eventually be developed together with the kernel side and with the RTOS side. And once everything is tested, then the bindings and the IDs are released. Yeah, but it doesn't solve one remaining problem, which is if you make a mistake in this process, then you cannot fix it anymore in the future, ever. So you will end up with some sort of an ID which maybe is broken, and it will be there forever. This can be, this sort of development process can only be done incrementally, but it will potentially leave behind some mess. Now, I am wondering, the question is effectively this. Do you have these kinds of problems with PSCI, SCMI, or whatever firmware to kernel ABIs? And if yes, how did you address them? Or do you have anything else to add to this? Questions?
Conrad knows that we only have problems. I think our problems also goes beyond the bootloader. We have our SCMI stuff on the controller, like MCU on the other side, like a server runs on that side, like we call it CPU, CP or CPU.
SCP, system control processor,
kind of stuff.
right.
And so it's, for mobile, for example, our UP EDK2 doesn't remain as resident, so it's pretty much goes away. So we had also SCMI has also, I don't know why someone did a vendor protocol there, but maybe there's an intention there. So, and that also we have a vendor V1, vendor V2, and we do not maintain that. And again, the second point you mentioned, 2.2, like bundle ABI server, and no, in the same slide.
Let's see.
You mentioned the point of, okay, bundle everything together when you're testing it. That's what we are doing in downstream. When we break something, we kind of bundle so that everything keeps working. You know? So we have this problem on a mobile, just to confirm. And also we have problem on the computer as well, I guess, because Windows does the development differently, Linux comes later, and then we have kind of incompatibilities as we go. But what I was thinking, maybe, but do you think if you do upstream early, while we are doing a development, and get this fixed early, will that solve a problem a little bit? May not be completely, but that's what we are trying to push for, so that, okay, some of this protocol stuff or SCMI or vendor protocol, or even for the VM, for PKVM or some Ganya or hypervisor, where we are also an ABI there. If we get the specification out and if we upstream also early, maybe this can be a little bit solved. Otherwise, in the downstream, I don't think we have any good solution. It's just about one team works differently than other team, and then it's also kind of the spaced out development. First Windows development happens, and then Linux development happens, and kind of stuff. So there's no good solution. At least in Qualcomm, we had maybe, unless Conrad, you want to add anything on the Windows experience.
That's actually a very good point, by the way, with these cross-team cooperation.
So in the first point on this slide, you mentioned that older broken entries cannot be fixed. Could you go a little bit more in detail what you have in mind with that?
One more time, please.
You mentioned that older broken entries cannot be fixed.
Yeah, the thing is, say, if you develop, I don't know, a UART clock driver, right? Or if you develop like a UART driver and it needs clock, it may have to use some sort of an SCMI ID to enable those clock via the SCMI clock protocol, right? And now you realize, okay, so I have a firmware which implements the SCMI clock protocol, and it exposes, say, SCMI clock ID, which is, I don't know, 5, and that's the UART clock, right? And in your DT, then you describe, okay, my UART node and clock property, which says, okay, SCMI clock 5 to operate these UART clock. And then you realize, oh, so, okay, my UART actually needs maybe another clock, which were somewhere hidden, and it was not clear from the documentation. And now you have to somehow say, okay, these UART clock are actually broken, and I need some different SCMI IDs, maybe 2 of them, which implement the actual UART clock management, because maybe one of the clock actually gate the register access, and the other clock actually drive the serializer in the UART IP, right? So you will end up with one clock which are actually broken and exposed via SCMI, and then two more clock which are the new clock, which are actually the right kind of clock. And how do you deal with this? You will effectively end up with these old broken clock which you cannot remove, because you may end up putting some old Linux kernel on the machine which depend on these old clock. So you have to keep them around forever.
So if that's DT, then this is, I think, another layer, because it happens, the situation you described happens even without firmware involvement. We quite often run into this where, for example, when you try to suspend the platform, it turns out that you relied on some clocks being on from the previous boot stage. And then if you come back from suspend, they're not on because they're not described. So I would say that your DT was never proper, and the solution to that is unfortunately to break the bindings, because there's no other way. Now, if there's firmware involved, I believe that the expected fix would be to update the firmware without altering the clock index. Because if it goes to the UART clock, you would normally think that if you turn on the UART core clock, you're going to use it for the UART. So you can then assume that on that platform, this should also turn on another clock as a workaround.
So basically what you would suggest is to quote unquote fix it up on the firmware side and create some sort of a compound clock on the firmware side.
Yeah, if you don't want to alter the DT, that's pretty much the only way, and you have to change something either way. For the next platform, where you now know better that you're going to need more clocks, you can do it properly, but perhaps contain the workaround to the one that's insufficiently described. Krzysztof, do you agree?
The problem is not different than what you said, that it's the same as hardware, right? So if you didn't describe properly the hardware, you have to deal with it, live forever. And your benefit is that you could change it in the firmware, right? But if you claim that you cannot change it in the firmware, then it's exactly the same problem as you are upstreaming early. And turns out that hardware operates differently than you thought. Then do the same as that case. And answer for this is platform maintainer decides what is stable, what is not stable in his platform.
That's correct.
Yeah, declaring DT bindings as unstable maybe is a good topic for next plumbers, because
No, this was rejected because they are never getting stabilized afterwards.
Hey, so there was one more idea which I was maybe I probably should have added it into the slides. And I was thinking, okay, so if we maybe have this kind of a SCMI ID mapping issues, say like the firmware has unstable SCMI ID mappings, what would you say if we had a kind of a remapping driver in the kernel? So basically, we would say, okay, in the device tree, we have a clock driver, which would bind, say, to the clock IP, and all the other IPs in the device tree would refer to this clock driver with the clocks property. And the clock driver would do remapping from some internal IDs which would be used in the device tree to the actual SCMI IDs, and it would probably carry around tables in it and do the remapping based on the firmware version. Because you can retrieve the firmware version from the SCMI base protocol. So in the kernel, you would have this kind of a, effectively a ID mapping driver. Would that be something which would be workable?
So this would essentially be creating another clock provider driver, but it would just so happen that instead of writing registers, it would make SCMI calls.
Yeah, it would effectively be some OFX-lite or something like this.
Yeah, so it's up to the clock maintainer whether he's going to carry that, I think. But it is a solution, but I would keep it as last resort, really.
What I like about that idea with the intermediate driver is that it might support different kinds of firmware, because I can imagine setups where the same SoC is used, like, say, in a community board, and then you have maybe an open source firmware, and the same SoC is used, I don't know, somewhere where certification is needed, and then you might have a proprietary firmware. And so with that, you could, like, maybe describe the firmware to be used in device tree, and this intermediate driver would still have the stable public IDs and map it to whatever firmware is in the back. That's what I like about this idea.
You also assume in that case, the firmware developer increments the firmware version. And we have seen the case, actually. By the way, yes. And there's an active discussion on SCMI part, I guess, and part of the Qualcomm too, in my view. And it's okay to take blame. That we have seen that the version even doesn't get incremented. So then what we will do? So that's another problem we have. So when there's a major changes happen, we need to increment, right? For example, that's kind of a binding. We have seen that version even doesn't get incremented. So now how do I discover the differences? That's one more level of problem. So I'm not sure that will impact your remapping driver again.
Is this maybe something which you can do in this kind of a proxy driver probe, this kind of a discovery / probing of the SCMI server implementation to figure out whether it's like this version or that version, even without probing the SCMI base protocol? And maybe do something like a poking of this SCMI server and figure out, okay, it's this old version, it's this new version.
That's kind of back. I can send you that on the Sudeep and us on that. So
Yep. I'm actually in touch with Sudeep already, so I was hoping he would join today, but I'm not sure if he will. Maybe he's there. I'm not sure.
You would essentially implement TCP/IP fingerprinting, but
Disclaimer, I've been discussing with Marek before, but another nice thing of this translation thing is that we can actually describe the hardware again in DTS, because, for example, the module clocks, they are actual numbers that come from the datasheet, from the hardware datasheet, while the SCMI IDs are invented by someone who wrote the firmware. And this would also allow us to run these systems without SCMI if we want. If we have a clock driver that drives the hardware directly, it can use the hardware IDs as specified inside the DT. And if you run with SCMI, it would use a clock driver that notices that the system uses SCMI and then translates the IDs and call into SCMI.
The same problem would be RPMI. Because it's just not a SCMI specific problem, because in RISC-V we have RPMI. So I'm sure the similar problems are going to be occurring on RISC-V firmwares too, pretty much soon enough, I'm sure. So it's not really a SCMI specific problem.
It is definitely not an SCMI specific problem. Yeah. It's firmware ABI generic problem, no matter how you call it.
Well, lucky for me, this is a great argument why do you need specific compatibles, because ARM SCMI compatible does not have a specific part. So you cannot override ARM SCMI easily from DT. There's only ARM, SCMI, right?
Yes.
So you are screwed.
One more time, please.
You cannot override the clock driver.
Oh,
you cannot bind it. You cannot bind other driver. There's only one compatible. This is why you need specific compatible. Then you can always override.
What you can do is you can describe the clock controller node in device tree, and this will have some sort of a compatible.
Look at the device trees. They don't have. So you can fix it for the future device trees, but if you look at the current DTS, neither the protocol has the compatible, nor the parent has specific compatible. So I'm just saying that this is a nice argument why you have to always use a specific compatible.
But what you can do is you can have the clock controller node in the DT, and this will have specific compatible.
So open DTS, existing DTS of IMX. Do you see
I'm
that
not talking
specific
about
compatible?
IMX. I'm talking about other device, and the device tree will only be upstreamed in the future. That's kind of work in progress right now. So I have the possibility to actually do it right this time. So my hope is that I'll be able to have like a clock controller node there with a specific compatible, and that one will refer to the SCMI clock protocol. And every other node in the device tree will actually use clock property and refer to the clock controller node. Does that work?
Yeah, if my understanding is correct, you would describe the hardware clock controller, which the SCMI server calls into.
Yes.
Under the hood.
But I'll actually bind the remapping driver to that.
Okay. The only concern I have with that, because it sounds like a great idea overall, but in implementation, I fear that if the SCMI server operates on multiple different clock controllers, that may go south a little.
That is actually a good point.
Including potentially clock controllers that are outside of the SoC and that are board specific. Yeah, I know. It's horrible, but I could imagine an SCMI server with a specific firmware version that would be board specific and control external clocks as well.
That's a good point.
This will show my lack of knowledge about the standard, but does SCMI allow for controlling per board specific add-ons like that? Or is it like guidelines to be towards SoC more?
The thing is, with the clock protocol, they basically say the IDs have to be starting from 0 or 1 and then monotonically increasing, which means there is no way to say, okay, I want to control this or that controller. It has to be just one long run of integers, which is unfortunate.
And I think to expand on your question, I don't know if the standard would allow that, but it's also a question of whether it's going to be, the server will be implemented that way or not. So even if the standard doesn't, I'm pretty sure some people would want to.
SCMI is modeling the system clocks, like the system as a whole. It's not modeling a clock controller. So there's no the question of where the clocks are physically provided is orthogonal to SCMI.
That's not necessarily a problem. Like if we're saying represent the hardware clock controllers in the device tree, even if there's not a one-to-one mapping between clock controllers and SCMI, you could have several clock controllers in the device tree that all point to say, well, actually, you can't touch this register interface because it's behind some bus firewall. You have to go through SCMI, but that's okay. You could have 3 or 4 clock controllers that all go through SCMI and have their own mapping table to that SCMI interface.
That's a good point. Indeed.
But the problem I see with that is if you have, let's say, clock A with indices 0, 1 to 3 as DT bindings and clock B with the same indices, and SCMI, the SCMI, they both bind the SCMI remapper driver, they would still have to be aware of the firmware node or the DT node that is coming, where the request is coming to make sure that they can point to the actual thing. Because otherwise, my understanding is that on clock A, you would have indices 0 to n, and then you would have to start from n+1 to n+m on the other one.
Right. For each clock controller that forwards to SCMI, it would have its own mapping table from 0 to n maps to SCMI indexes A to B. And where each A to B from all the different clock controllers is non-overlapping because that's what the SCMI clock ID space is.
For the on-SoC clock controller, it's rather simple because that has a really specific compatible value. But on the board, you may have some generic Versa clock 5 clock for example, which uses the standard compatible value, but then you need to know that on this board it should not use the standard driver, but something else. And it's kept even more complicated if you have two instances of them.
Oh, it gets actually even more fun if you have, for example, IDT Versa clock there. Because say if the SCP, for example, controls the Versa clock and it mashes it into the SCMI clock IDs, and then you would have to have one remapper driver for the SOC clock controller and another remapper for the Versa clock. Yeah, probably for the Versa clock.
Or it might not be possible to represent the hardware typology in a AP-centric device tree because the bus the clock controller is on is not accessible in any way to the AP.
Ouch. But then maybe the nodes can be reserved and it can still be described in the DT, technically.
Right, but like the reg property would be meaningless because it's on some bus that you don't have access to. It's on some like I2C bus that you don't have access to, and the I2C controller is only visible to the SCP or something like that.
Mm-hmm.
All these solutions are taking only the simple case of the ID-based SCMI ID-based ones. There's also things that are not ID-based, like SCMI also does regulators and pins, and also all these things can have hierarchy, which also is another thing that's we haven't talked about yet. So there's a lot of the solutions that have been tossed around so far only tackle the easy process,
the flat ID,
flat space.
Correct.
Not,
I'm definitely not an SCMI expert, but during the past few days we looked at it, and SCMI also exposes clocks, resets, sensors, and things like that. And most of these use hash something cells equals 1. The only exception seems to be pin control, which uses string names. But that's probably like sensors. This is the sensors. You mean?
No, there's a separate telemetry.
It's a separate one. I don't know about that. But for pin controls, even the string names are very similar to what we use on the existing SoCs. There we also have function group names. The actual names may be different, but
yeah, but again, if those groups get changed in firmware, it's easier. It's not as easy to adapt to as just a simple remapping function.
So maybe going away from that clock controller example a little, I was thinking that if the platform software development happens in the open, or at least somewhat, maybe perhaps we could share the headers and sync them between TFA or what have you and Linux, so that the IDs would come from a single source always.
Yeah, which kind of brings me to the kind of a next question, which probably is, how do we get everyone on board from all these different teams, all these different stakeholders?
So I believe that the only answer to this is do it and reject work from people that don't comply, because otherwise people won't agree voluntarily.
If you reject all patches from an XP, they will comply. I mean, we need to
take the hard lesson learned from the DCVS code. So it's kind of almost from 1.5 years or 2 years we are trying to upstream, and kind of we are doing reworking because of this vendor protocol version 1, vendor protocol version 2, and the firmware is completely in a different world. So yeah, I think we have a nice threads with Sudeep. So I think, yeah, maybe that's one way, because getting everybody to do even early upstreaming is very difficult, particularly in the embedded world. So because the SoC starts from somewhere else, mobile, and then comes to IoT, so which is probably pretty late by that time. But the firmware doesn't change on that, so only Linux kernel changes.
I think getting a header out in the public should not be super difficult, though. No implementation, just share a header and stick to it. That should be possible to make people agree on. Ish.
What do you do when that header is wrong, right? You still have some of the same issues. It's like, it's not just that we can't agree, it's that we make mistakes, right?
Well, if it's coming from an SoC vendor, you would probably have to either do the sort of dance that was proposed with the remapper clock controller driver, or you would have to say that, make it work.
Yeah, the problem with this is that when the SoC is being developed, sometimes there really is noise happening. That the header is not directly coming from the HDL, but there is some intermediate layer which can mess things up a little bit.
Okay, but
I would argue, yes, it would be fantastic if we can basically say, okay, we generate from the HDL some sort of a header, and then everyone just uses the header, and it will always be right because it comes from the hardware design. That would be super, but I have a feeling it's not necessarily happening always like this.
Right, but I think we can't support platforms that are in active development, though. Like, that's a little too far, I think. The target would probably need to stabilize, let's call it, before a software interface can be deemed stable.
Correct.
The problem with the hardware example is this: some of these chip vendors are using SCMI precisely to hide what the hardware is doing. So you're getting an SCMID for something that might not be one clock. It might be a few clocks that the firmware is managing together. Or in the case of power domains, I've seen it where there's a flat SCMI definition of power domains, but in the hardware there is actually a hierarchy of domains. My talk in the power management conf tomorrow is about this and how to work around a SCMI that defines everything as flat, where the hardware is not flat at all. Right. So you're not getting hardware descriptions in these abstractions is, really the root of the problem. You're getting an abstraction that you have. So, and then you're taking this abstraction and trying to define it as ABI. And so we're building problem on top of problem.
No, I agree with Kevin. I guess the other way is like we are trying to model ACPI with the SCMI. Okay, and we have done some very innovative solutions around it. Okay, so which is like performance leveling and 0, 1, 2, 3, 4, 5. You just do, and then this does basically over SCMI, and we have a VMs or MCUs doing basically that pretty much same thing. And there is no easy solution for that. But I think the first your point is to hide this. It's also like going like something like a server where we do a lot of stuff in a firmware. We do not want Linux to do this, so that we can boot the newer Linux much faster. So we don't want to have all this complexity of embedded systems on the Linux side, if we can do it on firmware. So more of emulating what server does. So.
I believe it was last year there was a talk about a device PM driver doing some of the similar thing where he's saying, instead of like, I don't know if this is the remapping driver or helps, it at least concentrates the complexity in one place, even if it doesn't decrease the overall complexity of now there's one driver that has to deal with all of my firmware changed out from under me, or I have the vendor firmware versus the open source firmware. And then all the other drivers in the kernel just see a power domain that's provided within the kernel, and they don't have to care about what's happening underneath, whether you're using the SCMI or the native driver or anything. All they talk to is the device PM driver, and that sort of models what ACPI does. But the problem is that driver is still in the kernel, which means it can still get out of sync with the firmware. So no, because it's just within, well, yes, because it's in the device tree. Well, it depends on how you do it. Today, it would be in the device tree and it would be ABI, but the idea is, that's high level enough that like you're not dealing with whether it's 1 or 2 or 3 clocks. You're just saying, well, here's the device, here's the power domain for this device, and all the magic happens inside the driver.
see all these discussions here. But I mean, the beer is waiting, so I would suggest we bring all the further discussions over to the beer event, the social event. Sorry for that. So thanks all for being here. I think what. All right, Marek first.
Thank you for your attention. It's fine.
So just one comment. So there are notes. Jan has taken notes of all these sessions. So they are in the big blue button thing. We will find some way later to attach them to the schedule or something like that. So in any case, for everybody who wants to get some of the notes there. Okay. Thank you. Bye bye. Good. So you have your session.
Question.
How do I?
Brian was fighting for the current, but this may be provided by a device that for that clock, one current clock change.
How do you?
I got